Welcome to the University of Kentucky's Center for Applied Artificial Intelligence. Visit us online at caai.ai.uky.edu to learn more.
Good morning, everyone. Thank you so much for joining us here today. I am excited to be here with all of you, and I know we have a great agenda for everyone. But to get started, I'm going to hand it over to Dr. Handy. Thank you.
Hello, how are you all doing this morning?
Morning.
I'm Ty Gandy. I'm the president here at Jefferson. And on behalf of the students, faculty, and staff, let me welcome you to our campus, our rapidly growing campus. Hopefully you didn't have any trouble finding parking. Fridays are usually pretty good. The rest of the week's really tough these days. We haven't quite taken over the new parking garage that we're building, and that's 500 and some odd spaces we're lacking right now. So it can be a challenge. So hopefully you found a spot well. I did see the parking authority writing one ticket out on the street. So if you parked out there on a meter, be careful about that. They're pretty aggressive. But hopefully you didn't have any trouble there. A lot of people know a lot about Jefferson. We're the largest of the 16 community colleges in the state of Kentucky. We're 14,800 students this fall. Makes us the fourth largest college or university in the state. So that surprises people when they think about that. UK, U of L, Western, and then Jefferson. And then we've really been focused on student success. So we're transferring more students than ever before. We're graduating more students than ever before. We've almost quadrupled our graduation rate in the last 10 years. And every year, for example, there'll be 700 to 800 students who start at U of L who have a Jefferson transcript. There'll be a couple hundred now at Bellevue. I'm not sure the Spalding count. I think it's just over 100. IUS gets a lot. WKU gets quite a few. And so we're transferring students all over, and we track them to see how their GPAs go, because our goal is for those students to go to your institutions and succeed at least how your native students are succeeding. And our data shows that that's happening. Slightly higher GPA for our students transferring than the native students at those institutions. And so we're pleased with that because we know that means we're hitting the mark in terms of preparing students. Have over 70 programs, and about 50% of our students, it's actually 52%, 48%, 52% are intending to transfer for a bachelor's degree, and 48% are getting a credential to go right into work. So it's pretty balanced in that way. So that's who we are. That's what we do. We're in the midst of a $100 million capital investment. We just opened our Center for Science and Discovery, all new science labs. If you get a break and can drift over, maybe, I think the doors are locked, but somebody will let you in and you can look around that brand new state-of-the-art facility. And then we're getting ready to take down the 12-story building that's against the interstate. So that'll be exciting. We drop a building that's pressing up against the interstate. We'll start that this spring, and we're replacing it with another STEM building, a math and some humanities, but primarily math on that side of First Street. So we're growing up over 10% each of the last two falls. I'm rounding a little bit. We were 9.8% this past fall, but that's a couple thousand students over the past couple of years that we've grown. So lots more students seeing us and coming to us, and I'm sure hoping to transfer to some of your institutions. So with that, let me just say welcome. Glad you're here. Enjoy the day, and I'll hand it back over for the real meat and potatoes. Right? Good.
Well, thank you, Dr. Handy. I appreciate the warm introduction, and thanks again, everyone, for joining us today. My name is Caroline Leach. I am the program manager for this NSF-funded NAIR pilot expansion project. Before we get started, I just want to give a quick disclaimer about this work. The material that you'll see today is supported in part by the National Science Foundation. Any opinions, findings, and conclusions or recommendations are those of the authors and presenters and do not necessarily reflect the views of the NSF. As you all know, and the reason you're here today. AI is booming. I work at the Center for Applied Artificial Intelligence at the University of Kentucky. We operate at the intersection of AI and translational science. We kind of function as a problem-solving think tank on our campus, supporting individuals or their teams in successfully leveraging AI across a variety of domains ranging from healthcare to agriculture. We're conducting a series of events around the state to connect with new and emerging researchers and innovators in the Commonwealth of Kentucky. And it's our hope that by attending this workshop today, you'll better understand core AI concepts and how it's used in real-world settings, gain insights into how AI is shaping research and the workforce in Kentucky, gain confidence in foundational ideas like machine learning, large language models, multimodal AI, experience AI in real time. We have a couple of demos we'll walk you through today. Obviously, to spark new ideas or connect with potential collaborators here today, and build an AI ecosystem within the state or further develop that out. I mentioned that this was a series of events. Today is our first in the series of 5 separate events we're conducting across Kentucky. Each of these workshops, though, has the same goal: expanding access to AI training. And you may be wondering, why do these goals matter and why do they matter for Kentucky specifically? Well, I know people come to an event like this for a bunch of different reasons, but at a high level, I think this is about access and opportunity, knowledge sharing and collaboration, understanding how AI works and how to successfully and securely apply it is increasingly important these days. But I know that in reality, many researchers or educators, especially those maybe in some of our more geographically isolated areas of the state, or if you don't perhaps attend a major research university, can face barriers to applying AI in their own work, whether that's access to compute power, software, tools, or just training on how to successfully apply AI in their own workflows. We hope that by attending this workshop today, that helps you overcome some of those barriers. That really is what the NAIR pilot program is all about. NAIR, or the National Artificial Intelligence Research Resource Pilot, is a federally supported pilot program designed to build capacity and broaden access to or training on AI infrastructure. Through support from the National Science Foundation's Educate AI initiative and the NAIR pilot program, we were awarded a conference proposal to help democratize access to AI training and resources so that people could be empowered to engage with AI and use it in their own research or workflows. Regardless, like I said, of location, funding status, institutional size, things like that. I do want to give a shout out and a big thank you to our partners. We worked with the Council for Post-Secondary Education on our grant and are connected with the KCTCS system, hosting all of our events at community college campuses around the state. We'll talk more about the NAIR pilot program and what it is later. So if you don't know some of the words I'm using right now, like compute or infrastructure, that's okay. I hope by the end of this presentation and by the end of the day, definitely, you will. Right now, I'll just say NAIR makes AI more accessible. Maybe you're wondering, who are these guys? Why are they qualified to talk to us about AI and teach us? And so I wanted to take a moment to tell you a bit about our center and some of the speakers that you'll hear from today. Our center, the Center for Applied Artificial Intelligence, was founded in 2023, and since then we have a proven track record of building secure, interoperable AI toolsets that are adapted across domains, identifying and overcoming bottlenecks in data, modeling, analytical workflows, and working on cross-disciplinary teams to combine AI expertise with domain expertise. Throughout the day today, you'll hear from subject matter experts from CAI. Aaron Mullen will be talking about AI-ready data and machine learning, drawing from his extensive experience working on projects like Radar, Kentucky, an effort that is addressing the opioid crisis in the state, as well as his work augmenting researcher workflows through forecasting and detection methods. Vaden Logan will be talking about computer vision and generative AI. His background is in computer engineering and networking. He works on multimodal research sandboxes and addresses challenges like data security and domain-specific fine-tuning. Mitchell Clusty will be talking about foundational models, which are a really promising frontier in the AI space, as well as creating robust and successful AI pipelines. He brings extensive experience in full stack development, executing projects like the Brain Digital Slide Archive, which is an internationally federated platform for AI research and diagnostics using neuropathology data. He also works a lot with agent-based systems, which are critical in the advancement of AI. We are also joined by a colleague from our partnering institution, CPE. Dr. Chris Ledford is the Director of Data and Advanced Analytics at CPE, and he will be presenting on AI, higher education, and the workforce. We also are joined by U of L's Dr. Adel El-Mahrabi. He is a professor of computer science and engineering, director of research for the Digital Transformation Center, and CyberHive director at the University of Louisville. He will be speaking about digital innovation, cybersecurity, history, and perspectives on AI. And I, again, just want to thank these folks for joining us today, and I'm really excited for you all to hear their presentations. Quick housekeeping. Hopefully you all had a chance to grab a coffee or beverage when you came in. Those are out and to the right. Restrooms are out there as well. And then we'll be having lunch this afternoon, which will be in the atrium space, which is downstairs. And there is an elevator if anyone needs it. Again, I just want to thank all of you for being here today. As you listen to presentations, I want to emphasize that there's more to this initiative than just this workshop today. Beyond this event, there's a suite of resources that we've pulled together for you that you have access to. We've created some videos which are available on our YouTube channel. Some are short introductory videos on AI concepts or data considerations. There are longer form videos that dive deeper into what AI is and some future trends. So I encourage you to check these out. And then I also wanted to mention, if there's any specific topic that you or your team are really interested in learning more about and you think you would benefit from a video, let us know. We have a survey that you'll be asked to fill out at the end of this, and if there's a demand for a topic, we are happy to make a video on it. We have a great content strategist on our team that helps us pull together some really nice videos. You will also have access to an online forum. This QR code up here will actually help you sign up right now if you're interested. This is available only to workshop participants. It's a place to engage with your peers here today and those around the state as our series of workshops continue. You can ask questions, brainstorm ideas, connect with others who may be working towards similar goals. Our subject matter experts will be monitoring the forum, but I think the real value there comes from those peer-to-peer interactions. We are also planning to roll out a Nair pilot virtual assistant. This is a chatbot that we developed that's designed to help you navigate the AI resources that are available, provide on-demand guidance on some of the available compute, data, models, training opportunities through Nair, and as well as connect you to some of the curated documents and resources that I've mentioned here. We also have pulled together some demos. I know people have varying backgrounds and levels of comfortability with coding. In the second half of the day, we'll dive deeper into some more technical concepts, but online you can check out some of these Jupyter notebooks to help you learn how to apply these concepts, support your application, guide you towards actually implementing them within your own unique workflows, and continue learning at your own pace. We will also be offering office hours as a part of this event, or a part of this initiative. One of the cool things about that is, I know from my own experience attending these things, sometimes questions come up more so in the days or a week or two after attending, and so this provides another opportunity to connect with the CAEI staff that you'll be hearing from today, ask additional questions, and we hope that you'll join us there. There is a registration required to get the Zoom link for that, but it is on the second Monday of each month, and that runs from February through May. I also wanted to mention, if you're interested, our center has a few open source tools that we've developed and we use ourselves. These are also available on our GitHub, so if you're interested in exploring any of these, they are out there as well. I know that was a lot of information and you didn't have to be taking notes or anything, because it is all on our webpage. All of these resources are linked there, as well as there's a link to the NAIR website. So if you're ever looking for something, that's a great place to find it and access those things. As attendees, our hope is that today builds momentum for you, sparking ideas, maybe lowering barriers, giving you multiple pathways to keep learning and engaging and collaborating long after this workshop ends. But perhaps one of the most important outcomes we want you to walk away from the workshop with today is awareness of the NAIR pilot program. So with that, I just want to tell you a little bit more about NAIR. Again, this is the National Artificial Intelligence Research Resource. It's led by the NSF, and it brings together a coalition of federal agencies, industry partners, nonprofit organizations to make advanced AI resources available to the U.S. research and education community. NAIR aims to accelerate AI and AI-powered innovation, expand AI and the workforce through training the next generation of AI researchers and educators, increase capacity, integration, and use of these public and private sector AI resources to create a more accessible AI ecosystem, and advance AI interpretability for building responsible and transparent AI systems. You can read about some of the projects around the nation that use NAIR resources on their website, but overall, NAIR exists to address a common challenge. Some researchers and educators, many in fact, don't have access to the resources they need to fully conduct their innovative activities that will help advance research and train the next generation. So NAIR exists to bridge that gap. Through NAIR, you can access resources like large-scale compute, data sets, software, and models. I know there are a few educators in the audience today, so I also wanted to highlight that NAIR offers a variety of classroom resources available specifically for educational purposes. But before I dive into an overview of how you access these things, I wanted to pause and offer a quick frame of reference. Terms like compute or AI infrastructure can feel abstract if you haven't worked with them before. Even if you are familiar with these terms, you may be thinking, I already have a subscription to ChatGPT. Why do I need this? So imagine a researcher in this room, maybe that's you, who has an idea, but maybe they don't have a dedicated AI expert on their team, or they don't have funding for their project right now. They're in a experimentation prototyping stage. NAIR is really great for moving into that advanced stage. So everything we're showing you today, from the presentations to the videos themselves to talking about NAIR, is designed to help you move from idea to experiment to prototype, so that you can leverage these state-of-the-art resources. It really is a great opportunity. When we talk about resources, these are often things that are cost prohibited on an individual basis. For example, if you're using a large language model, that's commonly measured in what is called tokens. A token is simply a small chunk of text, roughly part of a word or a few characters. Even small experiments with large language models can consume thousands of tokens, and when you scale that up to, using a really large data set or having a couple hundred people use that model, that cost of tokens can add up. But through the NAIR pilot program, there are inference and model services such as OpenAI token credits, and these are allocated in units of $5,000, $25,000, $50,000, and $100,000. So that's significant. What other resources are available? Well, I did mention resources for educators. There's something called the NIH Cloud Lab. This is a cloud-based training environment for biomedical research and education. Out of Indiana, there's something called Jetstream 2. These are GPU resources that offer large memory and high-speed networking to support everything from interactive experiments to scalable AI workflows. Those are just a few. Again, I would encourage you to check out the catalog online to review the opportunities yourself. But if you're working with AI, these resources are for you. No prior experience is required, and it is all available at no cost to you. There are some restrictions. For instance, you do have to be affiliated with a higher education institution or a nonprofit organization to apply, but any or no source funding is acceptable, and there aren't restrictions on application domain as long as the work aligns with NAIR and NSF priorities, which I'll highlight later. It is, fair game. So as you listen to presentations, especially in the afternoon, you will hear us reference or highlight specific NAIR resources. Again, these are all available in much more detail than we could explain them to you today online. And so they have a catalog. I have included the link there if you want to explore all of the options there yourself. I also wanted to highlight there is something called NSF Access. This is a sort of sibling program to NAIR. It is also led by the NSF, but it's been around for a few more years, and it's not specifically AI focused. It supports advanced computing broadly. So I'd encourage you, if you're looking at resources, to check them out as well. You may not have an understanding of how to use some of the resources that I've mentioned at this point, and that is okay. Throughout the day, we hope that you will learn and leave this event with a clearer understanding of what these tools do, what they enable, and how you might begin to use them in your own work. Wondering how you can access them, there is a brief application process. The terminology that NAIR uses is allocation request, and these are accepted on a rolling basis. So they're typically reviewed around the 15th of each month, and review is a two-phase process, first by staff from the NAIR pilot program, and then by the resource provider. The full process from submitting your application to actually beginning to use these tools can take a couple of months, but access usually lasts around for a 12-month period. I have put together, if you picked it up when you walk in, kind of a high-level overview of some NAIR resources with important links and more information on that application process. So if you didn't pick that up, it is available as a handout, but it is also on our website. I mentioned a few requirements. The main thing is that as it relates to NAIR, the research or work must have a clear AI component. And then there's also restrictions around performing the work specifically within the U.S. But you can find the full list of requirements for application and use on their website. It does say that proposals are the most competitive when they clearly align with the NAIR pilot focus areas. These are objectives such as accelerating scientific discovery through AI-enabled automation, or creating open source tools and models, data sets, or methods. But these are all pretty broad, and I think it's important to know them so that if you are writing an application, you can use some of their own terminology. They also have put together their own community learning resources, so I strongly encourage you, if you're interested in applying to NAIR resources, that you check these out. They have a great YouTube channel, including a video. It's a webinar, I believe, on what a successful allocation request looks like. They point out, for instance, the main pitfall of applications is they aren't quantifying their need. And so as part of their way to help researchers and those who are applying for these resources do that, they even have a calculator on their GitHub that can help you quantify some of these things that you're asking for. And then they have their own office hours as well. I believe theirs are twice a month. So these are some great resources by the NAIR pilot program themselves. I'd encourage you to check them out. I know that was a lot of information, but these slides are available on the website. So if you want to go back and reference anything, it'll be there. And then we have a couple cameras in the room. We're recording our workshop today, and it'll be posted on our YouTube channel. So if you want to go back and listen to anything that you hear today, you'll have the opportunity to. Again, our website is the best place to access these things, but we're really excited to be here with you today. I really appreciate all of you joining us here. I hope that you learned something, that you connect with someone while you're here. And now I'm going to hand it over to Erin Mullen, who's going to start us off talking about what AI is and what AI-ready data looks like. Thank you.
All righty. Good morning, everyone. As Caroline said, my name is Aaron. I'm part of the CAAI team, and I'm going to be giving kind of just an overview of AI as a whole, as a concept, as well as talking about some of the data types and importances about data when it comes to actually using AI. So when we think of AI, the definition has kind of changed a lot over time, I feel like. Back when we didn't really have AI as a concept, it was more of a science fiction thing with, robots and Terminators. And now, how many people have used ChatGPT here? A lot. This has kind of become widespread. It's become a part of our daily lives. We've seen self-driving cars now. And so a lot of times it feels maybe more like a buzzword than an actual practical thing that we know and understand. But it has been integrated into our lives a lot more than most people realize. The thing with AI is it's kind of a moving target. It's more of a broad frontier than a specific goal. Back in the 70s, we developed this technique called optical character recognition, which could convert an image of text into the text itself. So think of with your bank app when you're scanning a check and it extracts all that info. When this was developed, it was magic AI, never before seen. Now we kind of think of it more as an algorithm than even any kind of AI. So there's a lot of different meanings, a lot of applications potentially. And I want to talk through just a couple examples of ways that AI kind of affects us that we might not realize. So for example, everybody probably uses some kind of Google Maps, Apple Maps, Waze, something like that. And it doesn't just use an algorithm to figure out the shortest distance between 2 points. That could be very inaccurate because there could be changes in traffic conditions and things like that. And so what these apps actually do is analyze a lot of historical data and modern user updates to make their routes and their predicted ETAs more accurate. So you can think if you were going on a 4-hour drive and leaving at 2 o'clock, if it assumed that the traffic conditions would be the 2 o'clock traffic the entire way, you would probably get a different ETA than you would if it takes into account like driving through rush hour. And so taking into account all of those potential future trends allows these systems to be a lot more accurate. One of the kind of like classic ideas with AI is, it's used by streaming services to, recommend you shows and movies that you'll like based on the things that you've watched before. And that's true, but it actually does even more than that. For example, when Netflix was promoting House of Cards, their last season, they created 10 different trailers that all kind of emphasized different aspects of the show. And what trailer you saw when you logged onto the app depended on what your like user profile was to them. So for example, if you were like a user who watched a lot more content with like strong female leads, the trailer emphasized Robin Wright's role in the show a lot more than the other characters. So they were able to kind of tailor what each person saw based on what they thought they would like. They also do this with like color palettes. So when you see like a card or a poster for a movie on Netflix, they have different versions with different color palettes because they have determined that certain people who are fans of certain genres like different color palettes more than others and would make them more likely to watch it. And one final example here, a lot of like modern John Deere tractors all use cameras that have advanced computer systems that can identify like weeds and compare them to regular plants to spray herbicide essentially only where it's needed, which saves a lot of the resource and helps protect some of the crops. So as you can see, there's a lot of ways that AI can be used, and it's done in both like everyday uses, like your home voice assistant that turns off your lights, and very like groundbreaking technical advances, like being used with drug discovery. So what do all of these different use cases really have in common? Well, one big one is they're all about kind of analyzing and making sense of data. Because as humans, we have already developed way more data than we could ever actually manually look at. And so we develop these systems so that we don't have to. We want to be able to analyze all of the trends and patterns that we can find without having to do it ourselves, essentially. They're also good at responding to more unique and varied situations. So, imagine instead of having AI do it, if Netflix had some intern that was looking at every single user's profile and deciding what shows to recommend them. It would obviously be impractical because there's way too many different situations that you would have to account for. So we have AI to be able to respond to that. And then it's used a lot with kind of automating manual burdens to help improve outcomes. And the word automation is a little bit scary with AI because nobody wants their jobs to be taken. And so the goal is really more to improve lives by kind of making processes more efficient and building systems with more like human AI interactions rather than actually just replacing jobs. So I want to take a step back and kind of look at how AI systems that we have today were developed and how these kind of computer-based decision-making systems have changed a lot over time. And we start kind of all the way back in the 50s when computers were first being developed. They were very rudimentary, very simple, and didn't have a lot of processing power. And so the way that you would have a computer make a decision was to essentially meticulously code it in like a big sequence of if-then rules. So for example, if we wanted to make sure that we only sprayed the correct plants, we would say, is the plant a weed? If it is, we spray it. If it isn't, don't. But how do we determine if a plant actually is a weed? Well, back in this era, what you would have to do is essentially define an enormous flowchart that decides what makes a weed and what doesn't. So how many leaves does it have? Are the edges serrated? Well, what if a bug ate half of it and it looks different than the others? Like there's so many situations that you would have to account for here, and you would have to manually code in every single one to get a system that would work. Obviously, this is not very practical. These systems were very rigid. They required a lot of definitions ahead of time for every possible scenario. And that makes it not very scalable to real world situations where you can't code for every possible situation and every exception. And if a situation was encountered that didn't fall into their rules, they would just completely fail. And so they did prove, though, that we can use computers to make logical decisions using kind of human knowledge. As we get in towards like the 80s, we started to develop the first initial machine learning techniques. Our computers have gotten stronger, they have more processing power, and they're still too slow to process a lot of raw data, but they're better than they were before. So essentially, we need to do what's called feature engineering, which is basically telling the model what it needs to be looking at by defining kind of features or aspects ahead of time. So if you imagine we have our picture of our weed, we can't just feed that into the computer and have it determine anything, because it's not powerful enough to look at the entire image and figure out anything about it. So what we'd have to do instead is extract a bunch of information about this picture manually. So we determine the stem length, the number of leaves, the location, all of that. And now that data we can then feed into our machine. And our machine is now able to kind of determine what is important out of those features that we give it. So we don't have to define our flowchart anymore. We don't have to tell it what to look for. It can determine that itself, but we still have to kind of take that initial step and decide what categories we're giving it. So that gives it a lot more flexibility. We don't need to define things for every possible scenario, but we still required a lot of human involvement to develop those features. And this is when some of the kind of initial machine learning architectures were developed. So some phrases you might have heard before or might not, like support vector machine. It's essentially just an algorithm that finds the best boundary to categorize data by if we were to plot it on an axis. Simple neural networks, we're going to go into more detail about neural networks later, but you maybe have heard that before as just kind of a big system of nodes that all connect with each other and somehow mean something. Then in more of the modern era, we have more of what we call deep learning. So this is where we have our computers are advanced enough. We've developed what are called GPUs, or graphical processing units, which are essentially devices that are optimized to perform the kind of machine learning AI common operations very, very quickly and efficiently. So it makes us a lot more powerful with what we can do. And so now we can feed our raw data directly into the model and allow the model to basically develop its own set of features rather than us having to do it ahead of time. So now we can take our image of our weed and just pass it in directly to the model. We don't need to extract anything, and we allow it to determine what is important about this image for classifying it as a weed versus a crop. And that led to kind of an interesting question, which is if we have these powerful computers and we have our model and it knows everything about what makes a weed based on the image, then would it be able to generate its own image using that same information? And that kind of leads into the modern generative AI systems that we have now. The way that some of these were kind of initially trained is they basically use two models. One is called the generator, and that's actually creating the image or creating the text or something like that. And then we have our discriminator, which is trying to classify which ones are real or fake. So basically, over a bunch of iterations, they kind of go against each other. And you hope that the generator basically gets better and better at fooling the discriminator as it trains more. And that kind of makes sure that what it's creating is realistic and can be believed by this discriminator. We also had more advanced models like transformers. These have what are called attention mechanisms, which essentially just lets it relate every aspect of the input data to each other. So if you give it a sentence or an image, it's able to look at each word or each pixel and kind of understand how they're all related to each other to get more context and to get an overall kind of impression of your data, which means you can now train it on huge amounts of data and you can have the models kind of learn from all of it. So where do we go from here? Just in the last 10 years, we have developed techniques that kind of seemed like science fiction a while ago. So where could we possibly still be going from here as this development of AI keeps getting faster and faster? Well, one big kind of limitation, I guess, with AI still today is that it's narrow, which means that we develop systems that are designed for one task, and they're really good at that task. They can sometimes be better than humans at it. So we have AI systems that are able to detect breast cancer using X-rays, and we have found that this can improve compared to a human doctor in false positives and false negatives. But these systems don't have any knowledge outside their own domain. So our X-ray, identifier cannot identify weeds in a field. It can't recommend us shows on Netflix either. So these systems only have kind of one domain that they are built in. We have this idea of general AI, or artificial general intelligence, which is that we can develop AI that will be able to accomplish new tasks in completely new contexts without any human intervention. So allowing it to basically reason and plan with the same way that a human does. This does not exist. It is purely theoretical. People sometimes like to think that it is around, but really we just have better and better multimodal systems. So when you think of like ChatGPT, this seems like a system that has knowledge of everything and you can ask it all kinds of questions, but it still exists only within this text domain. It's a chatbot and that's all it can do. Even when you like ask ChatGPT to generate you an image, it's not actually that doing the image. It's a completely different model that's been connected with the same system. So these AIs still really only have like specific use cases that we can use them in. And I want to give some kind of important caveats and ideas about AI before we go too far into this. The biggest one being that AI does not know anything. This is a very important concept because it's a little bit hard to understand. But when AI is generating text, when you're talking to ChatGPT, it doesn't really understand what it's saying in the same way that a human does. It's really just using an algorithm to predict each word, one word at a time, based on whatever's most likely to come next, given all of the data that it's been trained on. And we'll go into more detail later today about exactly how they do that. But it doesn't have the same like inherent meaning or understanding as a human does. So if you think of like training a dog, when you tell your dog to sit and it sits and you give it a treat, it learns that it should sit when you say that and it'll be rewarded, but it doesn't inherently understand the meaning of the word sit. It wouldn't be able to use it in other contexts. So you can think of it kind of like that way. It's been described as like a stochastic parrot, meaning that these chatbots copy what they already have seen, but they can't really understand really underlying concepts. They just kind of rely on probabilistic information about how words are supposed to combine to make sentences that sound right. And this goes for non-generative AI too. So if we have our AI that identifies breast cancer, it doesn't know what breast cancer actually is. It just knows the certain features of a data input that make a certain response more or less likely to be rewarded as correct, given all the data that it's been trained with. And this doesn't mean that we can't use AI or that it's not useful at all, but we have to be cautious with how we interpret what it says. And there's a lot of caution right now because AI is a new developing field. We want to be able to use it ethically, and there aren't a lot of like strong ethical guidelines that have really been developed yet since this technology is so new. A big problem is, AI reflecting problems with the data itself that it's trained with. I'll talk about this more later, but since it's essentially copying what it's trained with, well, if the data you give it is bad, then what it copies is going to be bad too. And we also tend to not have a lot of explainability with AI. So why does it predict the thing that it does? This was advantage of our early, flowchart systems from before. You could at least follow a flowchart and understand exactly why a certain decision was reached. You can't really do that with like a black box AI that just spits out an answer. And that is a big problem if you want to actually like use AI with high stakes decision making. You have to consider what are the consequences if this is wrong. A big thing with that is hallucinations. So you maybe have heard this term before, but basically the idea of like an AI generating something that's simply not true. And this happens, and you have to know how to handle it and understand what the consequences are of hallucination. So there was a case a year or two ago with Air Canada, where basically a passenger was talking with their chatbot on the website, asked if he could apply for a refund for a bereavement fare after he'd already traveled. And the chatbot said, yes, you can. He went and did that and then was told by the company, no, you can't retroactively apply this rate to your ticket that you've already bought. And so they went to court over it and essentially battled over kind of the interesting idea of, well, who's responsible for the content that the AI produces? Air Canada argued that they had other correct information on their website. And the defendant kind of argued, well, how is a person supposed to know that the info on the website is right, but the info that the chatbot gives you isn't? And in the end, Air Canada was held responsible. They had to pay the difference. So that's just an example of, there can be consequences to AI being wrong, and you have to consider that when you're using it. Especially with generative AI, there's a lot of ethical problems nowadays. We've heard of deep fakes, fake images or videos. So how do we trust any of the media we view? Because it's harmful to believe something to be real that is fake. It's also harmful to assume everything is fake when it might be real. There's also a lot of copyright conflicts now. So OpenAI has been trained on millions of New York Times articles. Is it learning from those in the same way that a human kind of learns from everything that we've seen, or is it just plagiarizing them when it repeats information? We don't really have clear answers on a lot of this because again, since it's such a black box, we don't have a great understanding of how AI is really using the information that we train it with. It's the same thing with like image generation. Is AI plagiarizing, other artists that have created art that it was trained with? There's a lot of interesting debates here, and I don't really have answers for any of those questions, but what I do know is that AI itself isn't inherently good or bad, but how we use it can be. So today we want to learn a lot more about how to use AI effectively and ethically. And because AI is so powerful, it obviously makes it frightening. And there's a lot of bad use cases that you can imagine for this kind of technology. But I did want to highlight too, so it's not all doom and gloom, that there are good use cases that AI is currently being used with. So these are all real cases where we have developed systems that allow blind people to take pictures of things and receive like conversational descriptions of what they're seeing to help grant them a lot more independence. There's technology to allow patients with ALS to record their voice before they lose it so that they can preserve their identity with generative speech. We have students who can't afford private help being able to get help with their classes because of like AI tutors. And we have the ability to forecast floods and natural disasters in countries without the same infrastructure as like the US and other countries so that there's a lot more equity and safety. So there's a lot of potential use cases here, good and bad. And so we want to figure out how we can use this technology basically for good. So how are these AI systems created? How do we develop them? It all comes back to data. The data that they are trained with and used with will determine how they are used and how they can function. And so transitioning kind of into the second half of this talk, where I'm going to focus a lot more on data. Data is very important. All AI systems require it to train and evaluate them, and because the AI learns from the data itself, again, rather than any predefined rules that we establish as humans. We let the model figure out those rules itself based on the data. And if you have bad data, you're going to have a bad AI model. We have the phrase garbage in, garbage out, which is if you put in bad data, you're going to get bad results. And when I say like a bad AI model, what that can mean is it doesn't do the expected task well. Maybe it doesn't generalize well to new cases. There's a lot of ways that a model could underperform. And so what makes the data itself bad, though? There's a lot of different ways. I'm going to go over 4 kind of main rules for like good versus bad data. This isn't necessarily an exhaustive list at all, but these are just four main important points to keep in mind. If you want to develop AI systems or use them in any way, you have to think about what data you're giving it. So the rule number 1 is very simply, you have to have enough of it. Your data has to be sufficient. You need enough good data. And the reason for that is that AI trained on very little data is not going to generalize well. The less data you have, the more likely it is to just kind of memorize the data that you do give it. And then when you want it to expand out to a new situation it hasn't seen before, it won't be able to, because these systems only have knowledge of what they were trained with. And we've seen this in the real world. In 2016, Tesla's autopilot caused a fatal crash because it did not detect a tractor trailer turning in front of the car. This trailer was bright white, the sky was very bright, it couldn't tell the difference between the two and didn't see it. This was kind of a rare condition that was just not accounted for at all in the training data, so the system didn't know how to respond to it. So it's important to keep in mind all of these possible scenarios that you might have to account for in your data. And how much is sufficient is a very common question, and the answer is everyone's favorite, it depends. But 3 things that it kind of mainly depends on. One is how narrow is your task. So if you have an AI system that needs to look at x-rays to detect breast cancer, well, you only need to give it x-rays. You don't need to expand past anything outside of that. If you're training a self-driving car, you need a ton more situations that you have to be able to account for. And so you have to think about kind of what its task actually is. You also have to think about what the domain is, because kind of the more complex the data is, the more you need of it. So you could train AI with images, you could do text, you can do numbers. And if you think of like an Excel sheet, which is containing all your data, if you have like a single cell of your Excel sheet, that just has a number, well, that number is the only thing it needs to learn from that cell, right? But if you think of like a database of images, where each image is basically one cell, well, there's a lot more info encoded in a single image than there is in one Excel cell. And so you need a lot more of those images for the model to really learn what it needs to look at and interpret from those images, what features it needs to extract. The last big thing is thinking about how complex the problem is. So, if you have a more uncommon or difficult task, you're probably going to need more data. If you're trying to diagnose a very rare condition, you're probably going to need more examples of that than you would for something that's more common or easy to determine. Rule number 2, your data has to be free of other confounding variables. So there was a time where researchers were building a model to identify images of huskies versus wolves. Okay, so they found all these pictures of cute huskies, all these cute wolves. They label them, give them to the model, and say, learn the difference between these two things. And they found that when they were testing it, the model didn't work very well. They would have, this image of a husky, it would say wolf, this image of a wolf, and it would say husky. And so when they looked at the data more, they were thinking, could this model be learning something unintended? So is there anything else here that we think this model might be learning other than what the actual dog is? The background, right. So we have all green and grassy backgrounds with our huskies. We have all white and snowy backgrounds with our wolves. So what they found was that this model was not even looking at the dog at all. It could just tell grassy landscapes from snowy ones. So this is kind of an important lesson to examine all aspects of your data. You have to think about, are there other factors aside from your primary focus that might be affecting your results? And how can you, remove those? So in this case, to remove that, you would want to make sure you're training your model on images of huskies, both in the grass and in the snow, so that it learns that that's not the important thing it needs to look at. Rule number 3, your data has to be unbiased. This is difficult because all AI requires basically human data, and all human data is biased. And any AI that you train is going to reflect the biases that are present in its training data. And that has to be removed to create any kind of fair or equitable AI system. So, a famous example of this, there was a time when Amazon wanted to automate recruiting new employees. Okay, so they built a model that would take in all these resumes, and each resume was basically classified by whether or not that person got hired by the company. And so the AI took that in, and they were like, okay, it's going to learn, what factors of the resume make a person more likely to be hired, so then we can automate these decisions. So it used all these previous recruitments, and they discovered that immediately it always favored male candidates over female ones. Resumes would be completely discarded just because the candidates went to women's colleges or participated in women's clubs. And so, the important thing here is that the AI system isn't inherently discriminatory. It's not the model they use that's the problem. The problem was the data, because all of Amazon's past hiring practices always favored male candidates over female ones. And so when they trained the model on that data, it learned the exact same bias and reflected it, essentially, when they used it. And rule number 4, final of the main rules here, your data has to be appropriate in scope. So we remember Watson went on Jeopardy, did super well. Well, IBM wanted Watson to be able to do more than just compete on game shows. They wanted it to be able to help the world. And so they developed what was called Watson for Oncology, where they trained it on a bunch of medical literature, treatment protocols, emerging research, so that it could recommend kind of treatment plans and help oncologists with their jobs. So they trained it on a bunch of data from the Memorial Sloan Kettering Cancer Center, and this was high quality data, but it only reflected, the patient demographics and the treatment practices for that specific area. The problem is that then they took Watson for Oncology and shipped it to a bunch of countries like Thailand, India, and South Korea that didn't have the same healthcare resources and could benefit more from having this kind of AI system. And it would give very unsafe or irrelevant recommendations because the important demographics and treatment practices were just different in those areas. Certain drugs were maybe just not available, or the different patient population would just react differently to the treatments. And so they discontinued it a couple years ago. It was basically looked at as a big failure. And so the lesson here is that the scope of your data needs to match the scope of your system's intended usage. So if they had developed Watson at this hospital and then only used it at that hospital, it would have been seen as a big success. But because they tried to expand to new patient populations without including data from those populations, it was a big failure and didn't work. And so, again, that's not to say that a model trained on local data only is inherently bad. Getting data from all the countries of the world is very, very difficult and makes your project a lot harder to implement. But you have to match the scope to what your data is. Keep your system local if only your data is local. So to recap here, our good data is large enough for whatever domain or problem we're in. It's free from any other confounding variables. It doesn't have any human biases included, and it's appropriate to the scope of the usage. To give a good data example of how this was done, Google developed an AI-powered diabetic retinopathy detection model. This is caused when high blood sugar damages the retina's blood vessels, which can cause blindness. Almost half of all people with diabetes are at a high risk of developing this, but very few people in rural areas actually get screened. And so they trained this model on data from underserved countries like Thailand and India, where healthcare resources are a lot more scarce. And the model works very well, has 95% accuracy, which is a little bit higher than actual retina specialists. And they've already used it for hundreds of thousands of screenings. They're going to continue to use it in those places for years to come. So why was this successful? Well, they had a large data set. Their initial training data consisted of over 128,000 images, and it was very high quality. They had very standardized labeling to make sure that the ground truth was accurate. So when they had these images, they had these expert teams look at every single image and make sure that it was properly labeled about whether or not this person had diabetic retinopathy. And this created kind of the gold standard validation set. If you're training a model on data that you're not sure is accurate, then you're not going to be sure if the model is accurate. But knowing that the data that you're feeding in is correct is going to maximize your chances of success. And it was also appropriate to its scope. The models they trained, they use data from those countries, and it's only been applied in those countries. So they make sure that it's consistent with the patient populations that they're looking at. All right, so that's all very high level of general categories. But what does AI-ready data actually look like? What format does it take? How do you know it when you see it? How do you use it? And that depends on the domain and the intended goal of your project. But there are three main types, which are structured, unstructured, and semi-structured. So structured data is what we think of as a spreadsheet or a relational database. It's rows and columns, and it's typically more quantitative rather than qualitative. So it's numbers or true-false values more than words or images or stuff like that. And there's a lot of use cases for structured data. So for example, forecasting, this uses time series data, measurements gathered at specific intervals. And this could be used by a hospital to forecast how many people are going to come to the ER on a given day to determine their staffing and transfer decisions. So, just an Excel file with dates and values and any other variables they want to use, you could very easily build a forecasting model with that. Classification is more about a single point in time where you're applying some category to each sample. So if you're an educator and you want to predict which of your students are going to pass or fail their final exam based on all their prior performances so that you can give assistance to the right people, you'd be able to do that with a simple spreadsheet containing all of that info. Regression is kind of a mix between those two. It's just predicting a number instead of a category. So ride-sharing apps use this a lot to determine what dynamic pricing they should charge for a ride given current traffic conditions and location and things like that. And then anomaly detection is taking data generated by actions or events and flagging a very small proportion of them. So the classic example of that is credit card fraud. It's a very rare occurrence, but you want to make sure you're right when you do have it. And so it's able to kind of look at those rare cases and determine if they're different from the usual or not. So some advantages and disadvantages of this kind of data. It's very easy to use due to its rigid structure. Computers love rigid structures. They love things to be nicely formatted and consistent. And so it makes it very easy to pipe that data into a model and train with it. It's also pretty easy to interpret as a human. We know how to look at tables and spreadsheets and really understand what they mean. But some disadvantages. Realistically, a lot of the world's data is not very structured. We'd like to gather data in very unstructured ways, and that can lead to requiring a lot of pre-processing to make sure that your data is formatted correctly and consistently so that you can actually use it. And then if you have problems like missing data, how do you handle that? There's a lot of considerations there. The other one of the other main categories is unstructured. This is the data that you can think of that is not stored in a traditional database structure. And the struggle here is that, like I said, computers demand structure. So typically some kind of transformations are required to convert your unstructured data into a structured format that a computer can actually use it in. So we start with like text data. This is very interpretable to humans, but to a machine, it's viewed more as like a sequence of tokens, which again, we'll talk more about later, that can get basically embedded into numbers. And this can be very practical. You can build a model to analyze the reviews of a business and flag, common complaints or things like that. And again, it's not really viewing the text as text. It's kind of converting it into numbers, which we'll talk more about how it actually does that. Audio data can also be used with this. So you measure it with things like amplitude and frequency. It can use it to like automatically transcribe meetings by listening to the dialogue of the people, in the meeting. Image data is interesting because to a human, it seems pretty unstructured, but to a computer, it really is structured. It's a giant grid of numbers. That's basically all an image is, where each pixel is one cell of your grid, and each pixel, has a number representing its color. And so that's kind of how a computer looks at an image, and it has to figure out how all these colors and pixels relate to each other to form something. And the goal might be to classify an entire image as a certain thing or to segment just specific parts of it. So, like the X-ray example, to identify tumors would be used with images. And then you have video, which is really just a sequence of images where each image is just a frame of your video. And so by analyzing each frame as well as how they change from frame to frame, a computer can kind of get a sense of motion and change in the video. And so that can be used to monitor lab rats to identify when they are having seizures. And so the pros of unstructured data, it's very common and easy to obtain. We have a lot of unstructured data in the world, and it covers a huge amount of different data types and domains and pretty understandable to humans. But some big negatives with unstructured data. One is that it's very burdensome to actually review and analyze. So if you think back to the diabetic retinopathy example, I said there was 128,000 images and they had expert teams review every single one of them to make sure that they were accurate. Obviously, that's a huge undertaking, requires a ton of time and effort to make that data, good enough to build the model out of. So there's a huge kind of initial burden to review and analyze all of your data and make sure that it looks good. It can also be very computationally expensive to use. So a lot of this unstructured data, like I said about the comparison of an image to just a cell of data in an Excel sheet, that image contains a lot more data. It's going to require a lot more processing for the computer to really understand what it means compared to just a number in a spreadsheet. And we'll talk a little bit more in a bit about, those computational resources that are available to help kind of alleviate that burden. And the last main data type here is semi-structured. This is the one that's just kind of in the middle of the two. It doesn't follow a rigid format, but it does have some kind of looser structure that can still be analyzed and parsed. And so a couple common forms of semi-structured data, you could think of like HTML text that builds a website. So, the back-end code to decide where things are on a website and what gets displayed is all done in kind of this HTML format, which is very flexible, allows for a lot of variation, but there are still very key structured elements that you can look for and kind of rely on, like nesting and tags and things like that. So if you were building an AI to scrape the web for ticket prices, you would need to be able to have it understand what that website code looks like and how to parse it and understand what it means. Another very common one is JSON or JavaScript object notation. This is essentially a list of like keys and values where each value could be anything. It could be, a word, it can be a sentence, it could be a number, but you can always reliably index it using the key associated with it. So like a lot of smart devices, like a thermostat, for instance, will send data in JSON format. So they'll have, a key for the temperature and the humidity and all these things. And the AI system would be able to use that to kind of intelligently manage the heating in a building. And the last main type of semi-structured data is graph data. And a graph in this case is kind of a system of like nodes and edges, where each node is just like a thing, and the edge is what's connecting two things together. And so there can be different kinds of nodes, different kinds of edges. You can think of like with a search engine, a lot of the knowledge that they have is represented basically as a giant graph, where if you ask about something, it will be able to pull all the nodes kind of related to what you're asking about too, to give context. This is also how a lot of patient data can be stored, where you have like a node for a patient and it's connected to, a node for a surgery and a node for a treatment and things like that. So a lot of the world's data is kind of structured in this way too. And the advantages of the semi-structured data, it's easier to produce than fully structured, but still rigid enough to be analyzed well. It still can require some pre-processing and cleaning of the data, though. It's not always the most interpretable to really look at as a human, and it might require some kinds of custom solutions to work with. And I want to touch on here how you actually store this data, right? So these are all our different types of data, but like, how are you representing that? And there's a lot of different database management systems out there. That's kind of the standard like platform for storing data, depending on what your kind of data is. So for structured data, you have things like MySQL, Oracle, Postgres, which store tables of rows and columns, and you can connect those tables together with different keys to store a lot of data. Unstructured data tends to be more like stored like objects in a data lake that could be organized into like buckets or folders. So you can think of like just the storage on your own computer, right? That's basically an unstructured database management system where you can organize all your files into folders and things like that. But what each file is doesn't really matter. It's an unstructured data form. And there's a lot of cloud solutions for these from like popular providers like Amazon, Microsoft, Google, things like that. And then semi-structured data has a lot of custom solutions as well, depending on what your data type is. So the three I have here, MongoDB is good for like JSON-like documents. Neo4j is built for graphs. Redis is for like key value pairs and things like that. And so some of these resources are available through Nair. So a lot of those unstructured data systems that I mentioned, like Amazon, Google, Microsoft, it allows you kind of access to those cloud platforms. There's also a service called Databricks, which is a big data lake for reporting and analytics of your data. So if you have data, but you're not sure how to store it, or you want to gather data, but you don't have anywhere to store it, these can be some very good solutions for you to allow you to use those systems and have a place to actually store the data so that you can build an AI system with it. And the last thing I'm going to touch on here is some data concerns. I kind of already mentioned like bias and fairness being important with developing any kind of system that you're using. Obviously, you want to have good high data quality with accurate labels, complete records, things like that. There's also obviously a lot of privacy and security concerns now because people don't always understand how AI is using the data you give it, and that makes it a little concerning to give it certain types. So that's why data anonymization is very important. There's a lot of techniques out there like data masking to replace identifiers with codes. So there are programs that can identify proper nouns and remove them from a text to make something not identified. There's suppression to reduce kind of the details or group values for measurements. There's also synthetic data generation. So that can sometimes be a really good solution where you have some kind of like identified data that you want to use, but you can't obviously use it. And so you can generate synthetic data that matches the same overall trends and characteristics of your real data, but without actually including that identified information. And so there's a Nair resource for that too called Lexet Sea Haven, which is meant for custom visual synthetic data sets for like computer vision model training, so like fake images and things like that. So that's worth looking at too. But there's a lot of techniques out there for basically any kind of synthetic data. So overall here, AI is essentially as diverse as the data we use to create it. There's good and bad models, there's good and bad data. So hopefully I've given you things to maybe consider if you are hoping to build or use any kind of AI system. You have to understand things like bias, confounding factors, the scale of your data. You want to be able to tailor it to whatever your individual use case is. And data can take a lot of different forms. So rather than thinking about, oh, how do I structure this into an Excel file, is there a better way to represent it? Because there's machine learning techniques for just about every kind of data that I talked about here. So just think through how your data can be best represented. And that is all I have. So I am going to go ahead and hand it over to Dr. El Maghrabi from the University of Louisville. Thank you.
There's a clicker if you want it, and a handheld microphone. Wherever you want to stand.
Okay. I'll stay here. Can you hear me? Okay. So essentially, I'm thankful for Aaron for what he presented because will save me a lot of little details that I was gonna talk about. My talk would be more entertaining than learning. So relax. I labeled it digital transformation, AI, and cybersecurity. The reason is very simple. Digital transformation allowed us to have more data that's digital. And AI became a tool of choice to collect data and take it. And now that you have everything digital, it's not secure. Okay? So that's why I tie all three together. Since I'm one of the people who have been in this area for too long, I'll talk about history, challenges that may cross time over the period that I've been working in this, and highlight some technology and actions that are this. Since I've been at U of L for so long, my email uses my first name only. Okay. They don't allow this anymore. And if you are a member of a professional society like IEEE, my email there is adel@ieee.org also. So very simple to find me. Okay. I just want to give you a little background about myself. I did my undergraduate in Alexandria University. It was the very first computer science in an engineering school in the Middle East and in Europe, actually. Do you want to guess when did I finish my undergraduate? 1973. And it was fun. I was an odd engineer. I wanted to learn about other things, which kind of, when you work in AI and other areas, it helps you because you know more about other things. I had to do military service. I work in surface to air missiles, so give me an interesting perspective. Then I went to graduate school in Wisconsin, and it was a very interesting liberal school at the time. Lot of demonstrations, lots of fun. At U of L, depends on who you ask. I'm a professor of computer science and engineering with a chair. I direct this industry research at Speed School. I have my kind of place, I call it Hive. Now they say you call it Cyber Hive. It's an AI innovation studio with focus on different things. And I work with the U of L Digital Transformation Center as the director of research. So it depends on who is my boss of the day. You just okay. What got me interested? In 1968, I was a high school kid, and they took us to visit Alexandria University Engineering, and we got to see that amazing IBM 1620, very powerful machine, and they got it to play a matchstick game to print the Mona Lisa with X's and O's. And they did a hack. They put a transistor radio. Some of you will never know what this is, but doesn't matter. Something that provides sound, okay, on top of the machine. And the things that shouldn't happen, which is noise, the radio could decipher it and play music. So they knew exactly what program to play, say, the national anthem or a particular song. So it was a hack. And that really got me very interested. Music, games, and art. Does anyone know what computers are used for nowadays? These are still the same things. You know, ironically, what attracted me then is what's keeping me interested in this field. Obviously, there are a lot of things in the middle that are happening to improve it, and you know, you cannot stand still. Obviously, if you are not in computer science, you should know that our challenge is the moment we blink, we're behind. You know, it moves so fast. So I made that choice in the 70s. I love being because of the constant challenge and creating new things that affect the real world. So that's a field that blends logic and creativity and appealing with those who have a strong desire for complex problems. That's really the biggest issue. I heard about complex problems in AI, but complex problems are everywhere, you know? So complex problems require complex solutions. You cannot just, however, I still believe that the most beautiful truths are the simplest. So a simple solution to a complex problem may be what we need. Why digital transformation is important for us to talk about? Because all the data that was collected, now we want to optimize businesses and we want to kind of just use it. Why? Because there is, I call it a fallacy, that decisions based on data are the best. Okay. I think it's a fallacy because decisions based on your intelligence and experience are usually the best, you know? But data helps. I'm not saying you shouldn't collect data. So there is a lot of data explosion, but organizing the data and leveraging, that's what got AI its second breath, in addition to the availability of equipment and algorithms that evolved over time, and we'll talk about it. So a few years ago, I would say COVID helped with the digital transformation because people didn't go to the office. They relied on digital, you know. Now we got used to it, okay? So essentially, it's a critical framework that we have to use things and use AI to leverage it. It creates challenges because of privacy and security, as we heard earlier, and these are definitely important challenges. But everybody knows who invented the internet. Huh? Al Gore. But that's very important, seriously, because legislation that allows the digital data to be allowed was missing. So you had all this digital world and it's not legal to use. You see that? So this joke has a truth that organizations that are using digital data but don't have processes and legal internal even processes that allow them to leverage it, it's kind of doesn't make it useful. So you have to integrate this with the actual regulations and rules. So that's a very important thing that people miss a lot. So I kind of like Bill Gates more than Steve Jobs, so don't ask me why, but although Steve Jobs went to Wisconsin and I went to Wisconsin, so Bill Gates says the first rule of any technology used in a business is that automation applied to an efficient process will make it better, applied to an inefficient will make it worse. True. And that's what I see a lot of. You see that? People are only digitizing and applying what was manual and without thinking. So I say we cannot simply, that's my automate manual processes. You need to create a new architecture and new process flow. And that's what people sometimes skip the thinking and use the AI. You see, there is a step in between. You have to think about what should be done. That's why I insist that in this field of digital transformation that uses AI, we have tools, we have processes, and we have people. And tools are AI, IoT, automation, doesn't matter, you just, but policies and processes are very important. Because, for example, you already know which university I work in, but doesn't matter. We have 3-4 steps that used to be manual, but now they are electronic. And there is no intelligent way to make them useful with the electronic approach. You see, they didn't rethink it. So they just mapped it into just, you sign it here, you sign it here. This, without thinking, could have been done in a different way. So Why? Because nobody has time to rethink the process and to rethink the policies of how to change this. So you need the deployment, that's what I'm saying. So deployment are people. Which people are we talking about? The people who build the tools, we have to re-educate them that that's a new world. The people who are doing the policies and processes, we need to re-educate them. And the users, the end users. So, you know, people are embedded everywhere. So without remembering the people, the digital transformation experiences, I don't know how many of you love having customer service with some of the companies. I mean, anyway. Obviously, we heard a little bit about the birth of AI. In 1956, there was a conference, and two seniors, Claude Shannon and Nathan of IBM. And Marvin Minsky and John McCarthy were really leaders, and they asserted a name that every aspect of learning and any other field can be specifically described that the machine can made to simulate it. And I'll tell you that anyone thinks science doesn't have politics, it does, even at that time. They insisted on the word AI not to be absorbed in a trend that was called cybernetics, yeah. So they didn't want to be absorbed in cybernetics. And they wanted to differentiate. Cybernetics had a lot of the robotics aspect and a lot of the other things, and they wanted to differentiate themselves. And that's a very important thing to realize, that things take different directions by decisions. And we heard a little bit about how machines learn, so you saved me some of this. Algorithmic, then knowledge. And algorithmic was very important because you had to think, and you had to know and could explain what's on. Then the era of knowledge-based systems had different stages in it, but we are feeding knowledge to the machine. We knew what to educate it. It's coming back now. Anyone knows what you call this nowadays? RAG. You see? So don't ignore the past, learn from it, and use what is relevant from it. You see that? So then logic programming was a big challenge. Japan spent a lot of money on this, and this was called whatever generation of AI. They had specific AI machines, and it didn't work, but it's very good theorem provers, and some of the ideas are still valid. Before that, in the era of knowledge-based system, Lisp was a big language. Anyone here heard of Lisp? Well, some of you did. Okay, I went to California for a reception by the company that built the Lisp machines. Lisp machines were a very big thing. We had two in Yeovil, and they were like $250,000 each. This company made lots of money, and the reception was unbelievable, you know? So trendy things bring money. Then came the area of, I call it learning from data or data-centric AI, and we heard a lot about the data and all these things. And now LLMs and agentic AI, and I will not talk too much here on the generative AI, so all these are the current kind of ongoing. And I just will highlight that agentic AI is what good software engineering is. It's breaking the problem into pieces. You see that? You have one piece that is orchestrator, and many pieces that kind of know specific things. So it's a good approach, definitely. It's for scalability, because you don't have to have one big brain. And I call it that it's tough to create a superhuman, but you can create a super team, you know? So why not have the AI do that? So now we are taking these challenges. Oh God, that messed up the N, went to the next line. Sorry about that. Acceptance, computation, and data. All three are needed. You see that? I put in green data. There is a lot of data, and computation is unbelievably growing. But acceptance is kind of depends on the field and depends on what you're doing. You see that? So we need to work a little bit on acceptance. And I blame engineers like me and scientists that we don't tell our story correctly. Sometimes we leave it, any salespersons here, okay, leave it to the salespersons to exaggerate what we do. And then when it doesn't work the way they said it, we get a bad rap, you know? So kind of sometimes acceptance is a very critical in our time now. So we have to be careful because AI had a peak and fell. So we don't want to have this happen again. Another thing about data, which I will probably talk a little bit about it, is available. And look at how much data. I don't even know what these numbers mean. Okay, I just grabbed this because numbers are huge. So the data is there. Even on your phone, anyone takes pictures on their phone. Did you find an AI that analyzes it in a way that you love it? It will highlight you stories and things like that. That's AI. You see that? But the amount of data is so much growing, even on our own machines, phones. Machines, phones, whatever. Okay. So, however, the data that is being collected is not always in the way that we want the AI to use it. You see that? So a lot of data, I worked with some healthcare, I know you worked with healthcare companies, was collected for billing, not for real medical reason. You see that? ICD codes. I mean, if you ask a doctor, they do it because that's what they are forced to do. You see that? And then we want to use it for AI. Then we complain that the AI didn't do the right job. You know? So, have you ever went to a doctor and they measured your temperature, unless you went there saying, I feel I have a high temperature? Missing data. It has a meaning. You see that? So sometimes we don't understand even how the data was collected because it was not collected for what we think we are using it for. So simple things like that sometimes take you a long way. Computation. By the way, that's actually me on a hybrid computer in Wisconsin. And believe it or not, we had a helicopter company that's based in Milwaukee come and use it for simulations and testing their physical controllers. So these were real use machines. They were very useful. So Sikorsky, if you were thinking which one, if you know of. So then we had PDPs, VAXs. The PC appeared, and I was one of the people who ran and got one. I even got Lisp and Prolog on it and C, and boy, I was so happy. And then we had the Lisp machines, and the next one, these are the Lisp machines. And the Lisp machines, I said, were very expensive. Now we have NVIDIA, we have the cloud, we have all of this, and we have quantum. So we're using quantum. Actually, I'm collaborating with people in quantum. We have some access to the IBM quantum. We tested some of the algorithm on the AI. And you see, sometimes the simulation and the reality are not exactly the same, but it's important to start early rather than wait till they are a commodity. Actually, since I mentioned Wisconsin here and I was working on this, my advisor got small funding for a parallel computing from HP at the time in the 70s. And they stopped the funding because they realized, oh, it's too far away, it will not happen, you know? We developed some models, we called it WISPAC, parallel computer. One of the faculty at UK in CS was a colleague in Wisconsin, and he was on that team. So ideas sometimes can be too early, and that's a problem. You see that? If your idea is too early and you have no persistence and no funding to pursue it, it doesn't go too far. So beware, even in the hardware field, if you have an idea and you cannot, can quantum help? This is work that we did about dementia prediction using variational quantum classifier, and it was reported, actually our paper was kind of reported in a Swiss quantum hub. So even Switzerland is following quantum. You see that? You think of Switzerland as only about watches, huh? AI acceptability, I quote a lot of people here. My colleague also has weird books, Dr. Roman Yampolsky. I put two of his books. He thinks AI will kill us all. I love him. Actually, I was a department chair and I was the one who hired him, but we disagree all the time. We love AI, but we disagree about the future because I believe in the I before the AI. If your intelligence is dumb enough to make the AI kill you, then we deserve it, you know? I mean, you get what you do, what you build. So if we do not have enough ability to build an AI that is controllable, then, you know, goodbye. Okay, you know, and these are different quotes from different people, IBM, obviously. You know these people if you follow AI, and it's interesting. This actually is from ChatGPT. I asked ChatGPT about the human cost for AI, and it came up with this displacement, de-skilling, and loss of agency, which to me is considering some of us educators feel that our students are coming with less willing to put the effort to learn. And if they don't put the effort to learn, then they'll be replaced by AI. You see that? And okay, then also not just replaced by AI. Who will build the next AI? You see that? And if you haven't heard, the biggest challenge in the job market is for what? Entry-level jobs. They want people with experience, and hear about that. If you're only hiring people with experience and not bringing people to get experience, think about a few years later what will happen. You see that? So you're already building obsolescence in the field. You see that? So there is a weird thing. AI future, innovation is the ability to see change as an opportunity, not a threat. So that's why I disagree with my colleague who says that AI will kill us. I think if we have that fear, it's an opportunity for us to learn how to do AI that is secure, AI that is ethical, AI that will not overtake us. And this other guy, Sundar, artificial intelligence will have a more profound impact on humanity than fire, electricity, and the internet. Yes, all these are very good, but all these had challenges. Fire, we still have fire departments, okay? Anyway, so electricity, we get people electrocuted. There are lines that fall and create problems. So yes, all these technology, even internet, we have abused. So all these are very good transformative technologies, and so is AI, but we have to put our intelligence to safeguard them, okay? As much as I hate to say that, people tell you guns don't kill, people kill. AI doesn't hurt, people may use it to hurt you. You see that? You know? So we have to educate the people and create the moral, ethical attitude as well, not just the technical training. And I'm an engineer, I'm teaching technology, but I believe that our graduates and students, we are training them to be what? Citizens, responsible citizens, not just engineers. An engineer is one dimension of their ability, an AI expert is only one dimension of their ability. So Why AI and cyber? I put them together. AI is supposedly to increase productivity, boost industry growth, and more AI jobs, but cyber reduces the productivity, consumes resources, disrupts businesses. So you see, they are working in opposite directions. The issue becomes, can we get them together? People are using actually AI now for cyber attacks. So we're putting them together sometimes in the wrong direction. You see that? Rather than using AI to defend, which is another business, AI threat to cybersecurity warning, but AI could boost capabilities of hackers, all of this. Then there are emerging businesses for security that will use AI in some of them. You see that? So yes, it's a weird balance. Should we be aware of it? Market projections of these businesses, AI and cybersecurity, is big. So if you have ideas, it's a big market. The challenge is how to bring these two people to talk to each other. They are two different cultures. The AI tend to be geeks, nothing. And the cybersecurity people are like cyber cops. They are very tight and very controlled. So we need to bring them together so they can learn from each other and leverage the team mentality. To me, this is as much a challenge more than a technology challenge, is the mixing of culture. And I'll tell you something about culture. I've been very involved in, particularly my professional society, IEEE, in conferences and things. We created a conference that over 30-some years ago, which brings people from communications and computers. Do you know what communications used to be? A phone. Anyone saw a phone? A regular phone, not something you put in your pocket. And it was a clash of culture. The people from AT&T came in big kind of wearing suits and elegant, and the people from the software companies were kind of just casual, to the extent that we were in a conference on a beach in France, and the guy from AT&T insists we have to wear a suit for the reception because the keynote speaker is so important. It's a clash of culture, but this conference survived for 32 years now, actually. And one of the clash of cultures were arguing about would voice over IP survive or not, believe it or not. People from AT&T at the time were in denial. No, that can never happen. It defies all physical properties. At the time, yes, but not when the internet is faster, when you see that. So bringing cultures together is more of a challenge and require persistence. That's why I tell you these stories. But if you understand that it's needed, you keep going, and little by little, now we go very happy, we're all friends. I attended it last year and will this year, you know. But you had to overcome that, the clash of cultures. Okay. Any questions? Because the next step will be bragging about some things we do at U of L. You know? Okay. No questions?
Is the conference still in the south of France?
This year will be in Algarve, Portugal. No, we move in the Mediterranean. We choose nice places. Yeah. You know? Last year actually was not on the Mediterranean, was in Bologna, Italy. And by chance, out of all the places in the world, in February, I went to Italian cybersecurity conference. I was invited to speak in it. Then in July, I went to that conference, which is called Computers and Communication. So I went to Bologna twice in 1 year. And guess what? I hear Bologna has what this coming now? Some sports events. Yeah. So apparently it's the oldest university, Bologna University in Europe, by the way. Yeah, it's an interesting area. And they claim they have the best food. Okay, yeah.
And Dr. Ellen. Good to see you, sir. How do we solve the human problem? Of course, the weakest link here, especially with ethics. How do we solve the human problem? How do we fix the people?
In the teaming or in the ethics?
With regards to this, is was just mentioned a few minutes ago with
Okay.
the training.
Okay.
There are so many threats out there with poisoning and et cetera, and using AI for unethical purposes. We need to train this into society before we
Okay. Okay.
count on the outcome.
Sure. I tell you, I wanted to be an economist. So I did a graduate minor in economics, including human resource economics and a lot of courses in economics. I almost finished a master in that. Part of it is economical and part of it is technical. The part that is economical, why do people hack? Because they have time and don't have enough money. You see? So if you don't solve that problem, there will always be people who will tinker with technology to bring money, and there will always be odd people who will tinker with it because they are tinkerers, but there will be, some of these will be ethical. If they don't have the money, they will tend to use it for unethical purposes. We have a criminologist there who wants to comment.
Well, for a related issue to what he raised, how do you deal with the human problem with administration? It's not just like the idea of the human in the loop, you gotta hire someone. They prefer to build these big systems and ignore the human check or the human audit, and thus produce huge disasters. How do you anticipate the administrative plan?
I believe that people learn by experience and by seeing positive examples. So if you create platforms for kids to practice and ethical hacking and practice AI and practice this and embed in the experience teaming and embed in the experience the positive aspects of, oh, you see, you did something good. You see that? And gamification is obviously the approach that people talk about. Believe it or not, some years back, I had a Google director of software give a talk in Louisville, and they had gamification for debugging the Google code. So it's like if you find a bug, you get points, you see? So gamification will help, particularly, but you have to be purposeful in what you want. Choosing the right outcome is more important than how you do it. So you do a game, you do a training, you do a summer camp, you do a lecture plan that has this built in as an emphasis is important. But then the issue is you train people in technology, and I'm not talking about the United States, because there was one slide, I think I skipped it, is where do the attacks come from? From other countries, including the United States, by the way. And these are people who are desperate. And they have nothing better. So if people have nothing better, what do you expect them to do? They have the skill and they don't have enough jobs.
Maybe this is an opportunity.
That's why I say.
Because philosophy can be introduced and you get into...
Or rewards. Many people used hackers. Actually, I hate to say, some of these three-letter organizations hired hackers and give them incentive to discover attacks and things. So yes, you can leverage their skill by rewards, by competitions, you see that? So there are ways. Yeah. Other questions? I'll move forward. Okay. Okay. UofL, I told you I'm part of something called the Digital Transformation Center. So the center idea came a few years ago, and idea is, from my perspective, we succeeded in some things, but not in everything I wish we would. You see that? To increase awareness of digital technologies, including AI and cyber and this. The team is mostly, the leader is Dr. Carrick and Dr. Wright and myself, and we have an executive director. Okay. What did we succeed to get? Okay, we succeeded to get a lot of funding to train people and develop cybersecurity modules for education, including ones when we applied to the NSA to get the funding, we were unique. There were two other clusters, one in Purdue Northeast and one in West Florida, and us. Ours was unique that we included areas like AI, cognitive computing, data mining, post-quantum cryptography. The others were focusing on more traditional cybersecurity. You see that? So we wanted something for the future. We called it pathways, cybersecurity pathways. So we are now in a new incarnation of this, started recently, to modify it to a new standard, because if you know about cyber, there was something called the NICE standard and NIST standard, and now the Department of War wants it to be focused on job titles in the Department of War. So we're trying to map it into a different area. They gave us money, so I can't complain. Okay. Meanwhile, we created a lot of badges. So we realized that also we're an educational institution which we do degrees, but we can train people outside of the institution or within the institution as well who are interested in what micro-credentials and badges. I don't know about UK, I'm sure you have some of these, because that's a trend. And as much as I'm a traditionalist in some aspect, I'm also adapting to what people want. You see, people have short attention span. They don't always want a 5-year degree or a 4-year degree. They want a few weeks kind of badge to get rewarded. So we created a lot of these badges, and we led the university in having internal badges that can be extra for departments or courses that require badging. We created our own modules, 23 training modules in cybersecurity areas, and this is the map for that original grant. We broke it onto explorer, practitioner, and professional, and this would lead you to either depend on your ability, or this is a pathway, so you can go based off, if you only had a bachelor degree, didn't have a bachelor degree, you had high school, maybe you get to a bachelor degree. And many of these material were ACE approved for kind of course transfers. And we also worked with industry because we believe that some people need for job-wise these industry training and industry certifications. I'm not the best person to tell you I love industry certifications because they expire and they are only focused on something. I prefer first people to have foundational knowledge than do them. You know, but that's okay. You need both. So this is the team that's part of the Digital Transformation Center, okay? And the Digital Transformation Center is active. If you want to know, like it's a secret, it's not a secret, go to UofL. There is now a center called Kentucky Center for Digital Innovation. So in the wisdom of the university, they decided to create an umbrella on top of us called the Kentucky Center for Digital Innovation that will include this, which is the Cyber Hive that I lead, and the Digital Transformation Center, and any potential future AI initiatives, okay? So the university decided to create this bigger umbrella that will hopefully put all these things under one umbrella. the good news and the bad news is we're doing this all anyway. We talk to each other. We are cross-fertilizing and working together. A lot of us are on both sides of this, but that's the next thing. So if you get a presentation next 6 months or something, will be called Kentucky Center for Digital Innovation, okay? We'll have the training, which is like the digital transformation, the research, which I do in the Cyber Hive, and another probably expected AI Center for Healthcare, which I was asked to help prepare a plan for it. I don't know if they'll use it or not, but we're trying to build that, okay? So the Cyber Hive, it started as a partnership with Kindred Healthcare in 2017. And if you are from Louisville, you may know downtown was a company called Kindred. Kindred was so successful that it doesn't exist. No, that's a success story. It was bought by private equity, and broken into pieces. They sold the pieces and made a lot of money, you know. So the leftover was till 22. I was working with them till the end of 22 with some of the pieces that was left over. But 2023, I decided to take that building, which I invested a lot of my life creating it as a nice environment for work, and I called it Hive AI Innovation Studio. So we work with industry, and I have students, undergraduates, high school, postdoctors, other faculty collaborators. And most of the focus is on applied AI, but obviously when you do applied AI, it can trigger theoretical AI too. You know, it's kind of, we have contracts with companies like Yum, GE Appliances, things like that, and other companies, you may have not heard of them, but we do a lot of applied AI. With Kindred, for example, one of my biggest success is we would every day, all their hospitals, they upload they are post-acute care. And in post-acute care, if a patient returns to acute within less than 30 days, they lose all the insurance money. So every morning they load their patients' information in 70 hospitals, and our AI was on the cloud, AWS, and it returns to them for everyone which patients are more likely to return to acute with an explanative why this patient will possibly return to acute to let them address these patients. It worked for about 7 years. Now that there is no Kindred, I have no way to know whether it's running because there is no one from the team we know that's still with the pieces, so we don't know. We developed for them, for some of their nursing care, a full prediction for their customers, and we presented it for Association for Nursing Practitioners. So we developed many applications that were applied. For Yum, we developed kind of document analytics to map a document. And by the way, this issue of document analytics is a big issue. We heard of OCR as one of the first successes. I just this morning saw one company that's very good posting a video. I didn't watch the video yet, but OCR is still a challenge because we're pushing OCR beyond OCR. You see that? We're pushing OCR to understand the document, not just to take the text. You see that? So that's the type of things we were doing with them. And we are looking for a renewed contract with them. Actually, I just got an email last night that they are working with to get budget for renewal. So these are the type of applied things that we train our students to do. And in a way, we offer a service to companies. You see, I talk too fast. So, I mean, if it's boring, don't ask. If it's not useful, don't ask. If it triggers some questions, please ask. So I have She won't kick me out for a few more minutes. Any questions? Oh, Dr. Michael Lozaviuk again.
What are the options for, she's not the one that.
Okay, I put it this way. I have a vision. I was part of the vision where we got $10 million from the state to enhance our cybersecurity, but I'm not authorized to talk on my vision because it's now assumed as part of that bigger center. And we are in the process of hiring a director. So until we have a director, he or she will be the spokesperson. So I cannot. Hypothetically, we collaborate with everyone in the state in cyber and AI, no different than this group is doing, but in a different way because everyone offers different experiences and different skills. And I like to have it including regional centers, collaborators will have some of the cyber equipment and some of the cyber training there. So people don't have to come to Louisville to work with us, so they can work with all our regional collaborators, okay? That's my vision, but anything I say does not represent the University of Louisville or its board of trustees or anyone, okay? Yeah. No. We can listen to someone else. He's a U of L guy.
Your and technical background as well as is working in this area. So I'm in the school of business, not
The school of what?
Business.
Business.
college.
Okay.
What do you envision from an academic perspective in terms of multidiscipline? Because AI is no longer just here.
Okay.
It needs to be here.
That's a very important question. Michael Lozavio was involved with me on the first grant on cybersecurity, which included, I was leading it from the engineering. He is in criminal justice, which is in our university, arts and science, and we had people at the time from business school. It took us to get my dean's assistant, to call the dean's assistant of the business school to tell the dean there to sign, because they didn't understand what we're trying to do. So part of it is creating this shared knowledge of where we are going and what the possible benefits of collaboration are. Another challenge is, is budgeting systems in universities do not encourage collaboration. Reward systems are based on the quarterbacks get more money than the rest of the team, you know? You understand? So you have to create a system of reward and collaboration that goes beyond the individual or the college. And we've been working on that, believe me. I've talked to vice presidents, I talked to presidents. Yes, they all agree. I wish someone didn't agree, then I'd understand what's going on, you know? But you business people could understand the business structure maybe better. How do we create a business structure, you know, that allows for more rewards and more enhancing the collaborative nature? The Center for Digital Innovation, they put a board of advisors that has a dean of arts and science, dean of engineering, dean of business, but we don't know what they want, how they will do it, you know?
Yeah, my experience in academia does not like being compared to a business.
No, and I don't disagree. You see, business people also sometimes are too, and that's a very good point, are too short-term focused because someone destroyed the U.S. businesses, and you know who he was. Who was the most famous CEO in the U.S.? Jack Welch, huh? What did he do? He fired every time the lowest performers, which may not be because of their fault, because people were forced to create that hierarchy because he needed to get a bonus. And that influenced the management structure of all the US businesses, that they are short-term oriented. Every quarter, they need to come up with something. And to me, because I studied economics, not business, economics looks at 3 to 5 years. And when your vision is only on the quarter, you're in a rush and you don't invest for the future. And universities are unfortunately learning from businesses to be in a rush in terms of rewards. You see that? So departments are rewarded based on enrollment. And that creates duplicates of courses that if I have an AI course, you may have an AI course because you want enrollment. You see that? So without the system that allows for these changes of attitude, it will not go forward as fast as it could. I mean, we're doing it despite all of this. We have a group of friends across U of L. We work together, education, business, criminal justice, engineering. We love each other. We work together regularly with or without support. We get very nice words of kind support, but the system does not change. You see, I want to differentiate between a system and people telling you you're doing good. You see that? I'm a systematic type person. I like to have, as I said in digital transformation, you have to redesign the whole system. You see? You cannot just do small fixes. Yeah.
You brought up an interesting point here, especially with regards to Hive and the collaboration. Who owns them? Who owns the out?
Interesting. I am the director. I signed on my personal risk as a faculty a 5-year lease from the university foundation. So I'm the university renting it from the university foundation. And I have to bring money to pay all of these expenses. You see, who owns it is the foundation. Who is responsible? It's me at this moment. You know, it's fun. It's like running your own business inside the university. I mean, I always wanted to run a business, never had the guts to do it. So,
Currently work for a small company, and you mentioned the best way to help people adapt to the usage and acceptance of AI is like doing learning sessions and doing fundamentally. To that extent, is it better to use readily available AI resources like ChatGPT and
okay, I'm working with GE appliances, and they insist that they want to build their own, for example, but they are bigger, okay? Others, like Yum, they didn't care what we use, so we built our own because we have more fun this way, you know? So it really depends, but I recommend don't start from scratch if you can. But be aware of what you're using. I looked at, they have a very nice LLM factory. I mean, they have very nice resources. I told my students, these people about an hour and a half away did this. Why can't you guys do something better? I mean, I don't look for as good. I look for better. No. But you understand. But I'm not as in doubt in terms of resources because, you know, I'm kind of in a weird situation. I told you how many bosses I have, and I mean, so it's, yeah, there was a question there, yeah.
Yeah, I'm interested in maybe more ideas about the AI Center of Healthcare, AI Center for Healthcare that you so to speak. That would be more.
No, I'll tell you what it is, and you didn't hear this from me. All universities go to the legislators looking for money. And this is one of the money we are hoping to get. Okay? I'm doing AI for healthcare even with U of L right now. So I'm working with dementia images. I'm working with people related to autism. So I'm working with people related to nail fold analysis for rheumatismic thing. So I have a lot of collaborations. But I'm not a center for AI for health. Okay? And they would rather make something clear. Okay? By the way, hivehub.org is an illegal site because it's not in the university domain, but we run it ourselves. My students do it, okay? And we have a series called CHAI, Cybersecurity, High Tech, and AI. It's a fireside chat, and we are restarting another series. We'll post it in February. Like there are events during lunch, and we usually buy lunch. We bring someone, and it's a chat. It's a fireside chat. It's just fun. Okay. Our space is not that big, so we get 20, 30, 40 people. That's about at most. Okay. Thank you. Thank you so much.
Thank you, Dr. El-Maghrabi. We have one more presentation to wrap up our morning session here. Dr. Ledford from CPE, and I'll hand it over to him.
Nice to meet you in person. Let's see. Thanks. Morning. How's everybody doing? Morning. Good. My name is Chris Ledford. I work with the Kentucky Council on Post-Secondary Education. And I wanted to talk to you all and have a conversation this morning about AI, the workforce, and post-secondary education. And I think the big question, if I sort of took a poll, is what does this AI revolution mean for our workforce, for students who are entering the workforce, and sort of what all this means for Kentucky broadly. I think if there's any key takeaway that is on our minds as the state's coordinating agency for post-secondary education, it's that we've got to get state leadership, state agencies, state government, our institutions, 2-year and 4-year institutions together to have a unified and cohesive approach to what we need to answer, what we need to understand, and then what we're going to do about it. To that point, it's a perfect segue to say thanks to the people who've organized this. So this is what I'm talking about, right? This is what we have to be doing. We've got 4-year public institutions, 2-year institutions, some of our independent colleges and universities working on this. And of course, some of the researchers that we have in the state. So Caroline, team, Miles, wherever Miles back there, University of Kentucky and KCTCS, of course, and all the institutions that are presenting here. This is fantastic. So thanks for that. I'm taking 2 sort of approaches to this through our work at CPE. One is AI in the workforce and implications for Kentucky. You've probably heard a lot about sort of the early signals of disruption. Jobs are being replaced by AI. What does that mean for Kentucky specifically? We've got to be able to answer that question if we're going to do something about it, right? How can things that we're observing at the national level across the country inform what we need to be thinking about and doing in Kentucky? What if we're not prepared? What does that mean for Kentucky? And finally, how do we get prepared? And something that's interesting, that's the whole point of what we're talking about, what we can do with AI. AI can actually help us answer these questions. And second, which is more explicitly what I'm interested in, what my team is interested in, our data and advanced analytics team, is sustaining student success in Kentucky. I wish I was doing a key performance student success indicator talk right now, because we are moving the needle on so much stuff in Kentucky. Every year we set new high marks, or in this case, low marks for student affordability in the state. I just published or finished a draft of a report yesterday that shows that 74% of KCTCS students graduate with no debt. Zero. A big zero. That's remarkable. I count 15 percentage points over the past 5 years. Our four-year college, four-year university, public universities, we're down about 6% percentage points over the past 5 years. That's remarkable. We're setting new retention. I guess I said I wasn't going to do this. I'm doing it anyway. We're setting new retention and graduation high marks every year, including this year. And on I could go. How can we use AI in our student longitudinal data system to sustain that momentum? That's what I'm thinking about every day. And then finally, how can we use AI to inform the public about all of those things that I just said? How can we get that information to people who need to hear it? Legislators, we're going into a budget session right now. How can we easily get this information to sustain the legislature's gracious reinvestment in higher education over the past couple of bienniums? So let's start with the workforce. You've heard a lot of this stuff, but I think it helps, to repeat it and contextualize what we need to be thinking about. So recent research suggests that AI is performing about 16% of our labor tasks today. AI writes over 1 billion lines of code per day, something that would take all the humans on this planet a year to do. Everybody who writes code, it would take a year to do what AI does in one day. AI reads over 150,000 words per second, something that would take one person 1 hour to do. It's transformational. What are the implications of that? Companies are laying off thousands in customer service, HR type positions, entry-level IT positions. Hundreds of thousands of engineers were laid off over this past calendar year, and there's national hiring freezes in place in this area. It's crazy to think about. We've been talking about this stuff for years, and here we are. Some data corporation like Salesforce, whose big product is Tableau, estimate that 50% of their customer service and sales operations were done by AI just last year. That's astounding stuff to think about. What do national trends, national insights tell us about Kentucky? And I've kind of zoomed in on a few things here very much on purpose. By 2030, it's estimated that 30% of our workforce will be unmeasurable in terms of humans in actual employment positions. So if you think about all these amazing longitudinal national data sets, the United States Census, the Bureau of Labor Statistics, all the longitudinal studies, data that are out there that help us track who are in various occupations across the country, 30% of that's going to disappear because it's going to be accounted for by AI. Manufacturing, a 50% reduction in production jobs by 2030. Customer service, kind of get already 60% of customer service transactions right now are automated. I had a friend and a colleague going through a Taco Bell the other day, throwing an absolute fit because the drive-through asked him if he would like to use his mobile app, and he said no, and it never came back. Man, that guy was throwing a fit. 60% of customer service transactions now automated. And you think about transportation and logistics. If you've been to some of the major metropolitan areas out on the West Coast, I'm thinking San Francisco in particular, there's autonomous vehicles everywhere. last year, autonomous vehicles, and just think about this. These, again, metropolitan areas, these are not everywhere yet. Just a few places. Autonomous vehicles logged 71 million miles last year in just a few limited places. So what does that mean for Kentucky? Again, I cherry-picked those three buckets, sort of the manufacturing, the customer service, and transportation and logistics, because these are our three biggest and most core industries in this state. You think about just our transportation, logistics, and manufacturing occupations, that's 750,000 jobs in Kentucky alone there. If we don't find ways to address what the implications of AI are for our workforce, experts estimate that we could have a 10% reduction in median income in Kentucky. And that's a typo there, not a double-digit spike, but a spike up to double digits in employment. 250,000 jobs and $11 billion of revenue at risk, imminent risk. And we can pinpoint these to certain counties, right, in terms of the transportation and logistics piece of this, the I-64, 71, and 75 corridors, the counties throughout those areas, which include our metropolitan areas. As my boss and good friend Travis Muncie likes to say about the AI problem for many state agencies, state government, it's like trying to understand and study water while holding it in your hand. It's big, it's complicated. What do we do about it? The first thing that we've got to do, and by state government that I talk about a lot, I'm talking about myself too, and our agency and the work that we need to be doing. We've got to create statewide AI labor indices to quantify and understand the problem that we're talking about and how it's impacting Kentucky. Measuring AI job loss, where it's happening, who it's happening to. If we don't do that, how are we going to do anything about it, right? Measuring and understanding, again, the industries at risk, and then more crucially, understanding how we can upskill or reskill folks in those positions so they can continue employment in other areas, right? And then risk modeling. Like I said at the onset, AI can actually help us with a path forward by testing, retesting, simulating how reskilling and upskilling and doing different things in different areas of the state can help us secure our workforce for the years ahead. Transitioning to post-secondary education a little bit, which again is more sort of at the core of what I'm interested in and what I do. One of CPE's statutory responsibilities is to approve or reject and maintain the quality of academic programs across the state. Are there opportunities to reprioritize certain academic programs and focus perhaps even legislative funding for scholarships and other opportunities into certain programs so that we can produce more degrees and credentials of value that will have us a prepared workforce for tomorrow and the day after, because this is literally changing on a daily basis. The good news is that a lot of this stuff is already going on. We don't have to start from scratch here, but rather be flexible and adaptable. One thing you've probably, hopefully heard about in your time here this morning or just in other circles thinking about Kentucky's workforce is the Healthcare Workforce Investment Fund, which is a partnership between CPE, our state institutions, and the state government. They, in the last biennium, poured $10 million into the Healthcare Workforce Investment Fund to upskill our shortages in nursing and other critical healthcare fields. This is a field that for now is less threatened by AI. There's still a need for human beings to communicate with other human beings about treatment, about prescription, about ways to get healthier. Skilled trades. Hopefully, folks, a lot of folks in this room, given that we're at the KCTCS institution, are familiar with the Kentucky Work Ready Scholarship, which is very flexible, it's very adaptable, and constantly changing to pour money, scholarship dollars for students into programs that are high wage, high demand. Something that's great about this is it can be changed, through legislative processes in a way to sort of reflect things that we're talking about here in this room over the course of today. We can identify work fields, important high wage, high demand fields of tomorrow, and move legislative support to those areas to ensure that we're producing the degrees and credentials that our workforce needs. Teacher scholarship, teacher program scholarships, that's a big focus statewide right now. How can we funnel more dollars and more resources into shoring up our teacher workforce shortage? And the big thing, early post-secondary opportunities. In Kentucky, we have a remarkable dual credit network, again, which ACTCS sort of sits at the epicenter of. A few years ago, Kentucky was the first state in this country to set a dual credit attainment goal, which says that 50% of all of our high school graduates by 2030 will graduate high school with one successful dual credit course completion. Why is that? Because it lowers costs of college. Well, first, let me start at the beginning. There's a pipeline sort of. Students who take dual credit, accounting for other factors, at least one dual credit course, are 19 percentage points more likely to go to college than those who don't. Holding constant, a big one is academic success, prior academic success. The magnitude of that impact is greater for under-resourced, low-income, and other sort of underrepresented groups. That's huge. A lot of our dual credit across the state is focused in these three areas right above it: healthcare skilling, skilled trades, manufacturing work, and education. Back to that 50% goal, we're at 47.5 right now. 6 years ago, the year prior to the establishment of that dual credit scholarship trust fund, we were at 22.8. 7 years, over double the percentage points, over a doubling the percentage point of student graduates coming out of high school with a dual credit completion. That's remarkable. So more on student success. My big questions, if you haven't noticed already, is how can we better understand how key factors, affordability, the success or the ease of transitions, and so forth, impact student success. And finally, one thing we're really interested in is how can we leverage AI and some of that customer service facing potential to get some of this information that I'm telling you today to lawmakers, to policymakers, to university presidents in a quick way so that they can advocate for what we're doing right now for higher education more broadly. One example of something that we're doing, and I'm so proud of this, kind of related to this is sort of a leading indicator or a leading approach to that debt graduation. We're trying to get that down, right? So we have to look at student costs when they're in the pipeline, right, before they graduate. Shout out to the University of Kentucky LEADS program, which is where we sort of modeled this approach and took it statewide. We were looking at how student out-of-pocket costs, so not net price, not cost of attendance, not all these sort of financial indicators we hear about all the time, but after all the tuition, all the fees, all that stuff's accounted for, those sort of big bucket metrics and scholarships and financial aid, when you look at, when you do all the arithmetic on that, and you get to the student's out-of-pocket cost, that metric, at which a student makes a cognitive decision. Do I need to take out a loan to continue on? Do I need to find some other way to pay for this? Or do I drop out? Am I a 1 or a 0? How does out-of-pocket costs in the first year of college impact retention to the second year of college? 1 or 0? What we did, again, sort of looking at what UK has done so successfully with their students, their first year students, is turn an inferential model, an inferential study, into a predictive model that we have then deployed to all the institutions, or will be shortly deploying back to all the institutions across the state. So the first part I said, the inferential study, we looked at, and we're using machine learning and AI in this. CTE collects all individual level student data for every student in this state. If you're a student sitting in this room, we have financial aid records, enrollment records, course grades. We have the best longitudinal data system in higher education in the United States. And it's awesome. What we can do with that, for this example, we looked over 15 years. It's population data too, which is also killer. Population data to understand how first year out-of-pocket costs, the balance that a student and their family has to pay, impacts the likelihood of retention. It goes down almost over time about 4 to 5 percentage points per $1,000. Significant, right? Leveraging that 15 years of data, hundreds of thousands of first-time student records, we turn that into a predictive model, machine learning model. So every time we get a new year of financial aid data, that model retrains itself. And again, the institutions are able to use it. So let's say, I'll go back with UK since they're already doing this. Let's say we have a list of students with balances, identity balances. Let's say President Capilouto's considering a new type of grant that we can give to students to help them transition into a second year more easily. Who would give that to? UK, in this example, could go into the environment where this model lives, upload their Excel sheet, and get predicted retention scores for all the students. And that's exactly what they're doing right now. What's cool is then you can take the results that it takes back, the predicted probabilities of retention, and change that unmet need cost based on, let's say we plug in, subtract out the amount of grant we're considering to give. So we'll go through every student in the list, and we'll say we'll subtract 1,000 from that unmet need balance. Put the data back into the model. It takes it 2 seconds. 700,000 rows. Just think seconds, and you get back instantly how that predicted retention score changes based on if you were to administer that $100,000 grant package. Here in just a few weeks, every IR office that we liaise with at a public institution will have access to that. It's game-changing stuff, I think, and I hope. We're looking at, again, what UK's been able to do so well. Just 5, 6, 7 years ago, UK was already up over 80% in student first to second year retention. There's not much further you can go from there, right? In terms of a 4-year public R1 university, and if I'm not mistaken, up around 86, 87% fall to fall retention. What they're doing, they continue to go higher. It's remarkable, and other institutions across the state are doing the same stuff. But how can we deploy that to every institution trained on every student financial aid record over the past 20 years? Powerful stuff. finally, how can we do other stuff like this? What I'm really interested in right now, and we're trying to work out some of the security considerations with this. Again, we got millions and millions and millions and millions of student administrative records. How can we, in a secure way, unleash some of these machine learning and AI models on that best longitudinal data system in the nation and let it tell us, let it find patterns and things that we're not thinking about? What should we be thinking about? We're very focused on affordability, the seamlessness of transitions, things that increase retention and graduation rates. And we've got a pretty solid list of things that we look at, such as out-of-pocket costs due in the first year of enrollment. But what are we not talking about? What's on the cutting edge? What should we be looking at? We can leverage these tools to understand better. But our big question right now is how can we do that in a secure environment, in a secure way that's not endangering to those sensitive data. Finally, one thing I would love to get this sort of question to the finish line, because we get the same questions as the state's sort of hiring coordinating board every day. It's like, what were retention rates for my institution last year versus 5 years ago? Probably 3 or 4 times a day. How can we leverage AI tools against those administrative data to answer these questions and increase public awareness about all that good work I was crying about at the beginning to legislators and the public? One thing that I'm thinking about, again, we have all the administrative individual level data, but what I'm focused on right now is this third bullet, taking that data and aggregating it so it's not sensitive and putting it in its own server, its own warehouse, if you will, and then letting that interact with interactive AI. So what I'm kind of really focused on right now, say you're a legislator, you can go on our website to our data center, and instead of filtering our tableaus that sometimes, we slap 100 filters on to the point that it's actually not very useful, you instead can just go to a chat bot, just a prompt, a window at the top. What were retention rates for 4-year public universities last year compared to the year before? How do those compare to national level data? And then go to the Capitol, to the Joint Education Committee perhaps, and say, hey, we're moving the needle on retention rates. What we're doing with increased post-secondary funding is working, and by the way, it is. Stuff like that could be so powerful, right? Final thing I wanted to mention that I've errantly glossed over real quickly, the benefit of our longitudinal data system, our post-secondary longitudinal data system, is it's directly connected to our state longitudinal data system. Probably heard of KY Stats or the Kentucky Center for Statistics. What we're able to do with all of these data that we're working with is also track for any program at any institution, graduates anywhere in this state, what their outcomes in the workforce are, so long as they work for a employer that pays into UI wage benefits. So literally we can see from any program and any institution in the state over time what the workforce outcomes and the wage earnings are for our students. By deploying AI and machine learning tools into the work that we're doing, we're already starting to answer some of the questions that I led with at the beginning. Where do we need to start credentialing more students? Where are our shortcomings? Where could we put more investment in there? And then we'll be able to track over time, again, how those are translating to real workforce outcomes for our students. That's all. Thank you all so much. Happy to answer any questions. If you got post-secondary success questions, I'm happy to talk about that.
I have a question.
Yes.
I was listening to NPR's about a month ago, NPR's Science Friday, and the guest did the program. They said in 10 years from now, AI will be teaching the class, not the instructor. Who am I encouraging?
I mean, I think there's, a lot of validity to that. I mean, our institutions are dealing with that problem right now. More so from the point of view of students, sort of relying on AI to teach them instead of coming to class, also to do their homework. I think, the biggest thing, like I said at the onset, for us, we're not going to prevent that from happening. We're not going to prevent AI tools from impacting the classroom. So instead, how can we leverage it to make our classrooms better, right? And I think, again, conversations like this, but from my perspective, as with CPG, is we've got to be a part of setting up the statewide conversations to help answer these questions. I think that's the most important thing that we can do. I don't fundamentally believe that teachers, akin to what I was saying about nurses and doctors, will ever be completely replaceable by AI. Like, you have to have that human connection and ability for somebody to translate all that complex information to an end user, right? But it's something we've got to keep track of, especially again, from my vantage point. First question.
So to piggyback on his comment, the AAMC is already pushing for medical schools that the first 2 years or so are going to go to AI. Clinical trials, clinical experiences will be done face to face. Right? That's also happening in nursing, and it's also happening in DOs and in TA programs. So my question is your organization actually looking at the faculty and the instructors? Right? So you talk about workforce development and the replacement of workforce by AI, but are you looking at the faculty and the instructors at the institutions and how you're maintaining their success so that they stay on instead of disappearing?
In my work, not so much, Steve.
Yeah, so I'm in the Workforce and Economic Development Unit, and absolutely right. We fundamentally understand and believe that the student success is really only as great as the faculty success, right? We're not going to have as successful as these outcomes that Chris is rightly raving about unless faculty are supported in ways that they are able to take the time and space to read up about AI, to implement it in their classrooms, to understand how it's not just impacting their specific faculty work, but how it's also impacting the fields in which they do research and work. So yes, this is something that we're not only thinking about at our agency, but we're talking about it with other agencies nationwide. And to be completely frank and transparent, we're also thinking about it globally as well, right? So what are other nations doing that may be a little ahead of us or behind us in the ways in which they're integrating or not AI into their program development, but also their faculty and staff development as well.
So you have an idea of, for lack of a better description, melt of faculty and instructors out of public institutions because of AI?
No, I don't. And that's a great question. And that's something to definitely keep track of because, we talk a lot about workforce and economic development. And one thing that I think that we just generally miss, not just at CPE, but when we think about economic development, that our institutions are huge economic drivers, right? They're not just developers of the future workforce or, for civic and democratic engagement, but they bring people to the state, right? And at the same time, they can potentially be an economic driver loss. So that is something, we're a relatively newer unit at CPE, but that is, our unit is one that Dr. Thompson is focusing deeply on, not just viewing our higher ed institutions as ones of, knowledge production and that, but how are they driving economic development in their own beings in and of themselves, their own industry, right? Yeah.
Thank you.
So that's a good question.
We do have to stop here, but I love questions and I like talking to people about what we're working on and students in particular. My name's on the agenda. My email is my first name dot last name Christopher.Ledford@ky.gov. I would love to continue this conversation and answer any questions that anybody has. Thank you all so much.
All right. Hi again, everyone. You might remember me from a couple hours ago. And I am going to talk about machine learning overall as a concept. Fair warning, I guess, the rest of kind of the day today is going to be a little bit more technical than it has been so far. Not like extremely so, but what we want to do, I guess, is provide like kind of the foundation for how some of these techniques work. If we're going to be using AI and implementing AI in different ways, we want to make sure that we actually understand what it is, right? And how it works at kind of a fundamental level so that we can incorporate it the best into our workflows and pipelines and just understand kind of how it's doing what it's doing, how it like creates the answers that it does and things like that. So even if you're not like a computer scientist and you don't have that background and you're not going to be like personally developing any models, it can still be really useful to just have a baseline understanding of how these things work so that you have a better knowledge of how to implement them correctly. So this is a little bit of summary of some things I've already said, but machine learning overall is, getting computers to perform a task without being explicitly told how to do so. So rather than feeding in data and rules and getting out answers, we feed in data and answers and we get out the rules. And then we hope that we're able to use those rules, apply it to new data, and get more answers. And there is a lot of ways that machine learning is used in the world. So one easy example is like spam detection. So a lot of email providers have different classification algorithms that analyze like the subject line, the sender info, certain phrases to try to classify something as being spam or not so it can be filtered, right in your inbox. And so these models are trained with a bunch of examples of different emails that are labeled as being either spam or safe so that the machine can learn the difference between those. And it learns that, certain phrases are going to be more associated with spam emails. So why do they have to use machine learning for this? Well, the first spam filters that email providers had were more rule-based, and they checked for like specific keywords. So if the email says click here, then mark it as spam immediately. But the issue is that scammers can, change around their spelling and punctuation to then get around these filters. So they can put a 1 instead of an I or add an extra space somewhere. And now it has gotten through the filter and, is going into your inbox. The advantage of machine learning here is it's not checking for like specific keywords and phrases. It just looks more so at overall intent and structure. So does it have like an urgent tone? Are there suspicious links or bad grammar? Things like that are more indicative of spam without being, so dependent on specific like key phrases. Another classic example is, unlocking your phone with your Face ID. These models are able to learn the geometry of your face to unlock your phone, whereas a rule-based system would fail if your face was just at a different angle or you were wearing glasses that day or something. So it's able to generalize a lot more by using these machine learning strategies. And so when we talk about machine learning, that's a very broad word, and there's a lot of different ways that it's done. And the three kind of main categories of it are supervised, unsupervised, and reinforcement learning. So I'm going to talk through kind of what each of those are and how they differ from each other. So starting with supervised learning, that is the pretty like standard classic example of machine learning, where we have data that's already been labeled with correct answers. So with our spam detection, we have a huge, set of emails, and we've already labeled them as being either spam or safe. So when we pass it into the model, it knows which ones are spam, which ones are safe. So it kind of learns what each of those are more associated with. And there's a lot of different types of supervised learning. This is very common. We as a center have done a lot of supervised learning things. And I want to give a couple examples for these different types to kind of ground it more in the real world and show kind of the ways that these techniques are actually like being used and not just like hypotheticals. So, for example, classification, that's like the spam versus safe. We have a lot of projects with like diagnosing certain conditions like hepatitis C. That's a classification. Somebody either has it or they don't. Or predicting if a study participant is going to adhere to a remote alcohol monitoring program. We also have, projects with regression, which is predicting a number, as I mentioned before. So predicting like calcification scores, for instance, using CT scans to assess the risk of like heart attack or stroke. Then forecasting is pretty similar, but like looking more into the future. So like predicting how many opioid overdoses are going to occur in the next month in a given county in Kentucky. That's something that we have worked on. And then segmentation is more like images, identifying specific parts of an image. So we have had done projects with analyzing like parts of a rat's brain to determine like changes over time resulting from different treatments or effects. So there's a lot of different practical uses for all of these types of machine learning. But I want to go into more, well, how does a machine learn? What does that mean exactly? So typically the way that we would set up a problem like this is you iterate your model through what are called epochs, which are basically just like iterations or steps of the training process. A lot of machine learning at the end of the day kind of works with trial and error. So you give it a bunch of trials, and over time it starts to kind of figure out what it's supposed to do. So when you do that, your data set would typically be split into like 3 different groups. So the first is the training set. So you might have like heard the phrase already so far today, like your training data. So this is typically like a big majority of your total data, and it's what's used to actually train the model. You give the model your huge thing of emails and whether or not they're spam or safe, and that's all part of your training set. Then a validation set is a smaller portion that you kind of use throughout the training to make sure that your model is on the right track. So like after each epoch, for instance, you evaluate on the validation set, have it make predictions over that part of data and see how well it works. And then based on kind of what it learns from that, it then adjusts for the next epoch and keeps going. And then your test set is your last portion of data, which you kind of leave completely out during the training process. The model doesn't see this data at all until it's done, basically. And then you evaluate on that part of data to see how well your model applies to new data that it hasn't seen before. This kind of helps to ensure that your model isn't just memorizing examples, right? If we only ever checked it on the data that was used during training, then for all you know, the model could be just kind of memorizing each sample of your data and isn't going to generalize to any new results. So as a quick example of like how this would be run through, let's imagine that we have a model and we're trying to classify it between mops and dogs based on these images. So we have a big data set of a bunch of pictures of mops, a bunch of pictures of dogs, and we have them labeled appropriately, and then we split them into our different sets. So when we have our training set here and our model, in the first epoch, what we'll kind of do is feed in those images into the model, which will then try to kind of determine which features of the data are best distinguishing between those 2 classes. So it'll probably learn that if it's a dog, it has, an area of pixels that looks like a nose. There's an area that looks like a mouth. The mop has like a handle, and it's typically like found indoors in these pictures. And so at the end of the epoch, when we take in our validation set, now we test how the model will do with everything it's learned. So it might look at this dog picture and say, well, we have a nose, we're outdoors, there's no tongue, so maybe we're not 100% confident, but it predicts dog on this one. Then it looks at this mop and it says, well, there's no nose or tongue, but our handle's a different color than we're used to, and we're outdoors. We didn't have any outdoor pictures of mops before, so maybe it predicts dog this time. And this is why, it's important to have varied and extensive training data, like we talked about before with the huskies and wolves. So then in the next epoch, when it goes back to the training data, it's going to kind of adjust the features it's using based on what it learned through that process. So, focus less on where the object is and more about like what its shape is and things like that. So then the next time it gets to the validation set, we hope that it's going to improve on its performance. And essentially, we kind of continue this process repeatedly until we either hit like a set number of epochs that we defined, or the model just kind of stops getting better. And then we can bring in our test set, which will provide us like a metric on our overall model performance, so we can learn how well does our model actually do when we test it with data. So it'll look at these pictures and it'll make those predictions. In essence, that's kind of how any supervised model is trained, just by kind of repeatedly iterating, trying to improve every time it looks at that validation and learn as much as possible from the training data you give it. But I kind of skipped over a big step as part of that process, which is how is the model actually like learning the features itself, right? So how does it determine that for the dog images, it should look at the nose or the tongue, and for the mop images, it should look at like the handle? And that really depends on the type of model that you're training. And there's a couple different kind of classic, like very common model architectures that you'll probably hear about if you ever work in that space. The simplest of which is just a decision tree, which is basically a flowchart. So think back to our rule-based systems from beginning, but if we let the model basically decide the flowchart instead of us defining it. So it, is a series of kind of yes or no's based on all the images or aspects of the images that it finds. And these will be kind of determined by like what is maximizing accuracy. What split in your data splits these two classes the most evenly. Now, just having one decision tree means that you're going to be very dependent on those, initial steps. It's going to have a huge impact on your output, and it might be very influenced by only a couple features or a couple data points. So practically, the better way to use a decision tree is as part of kind of what's called a random forest model, which basically just builds a bunch of decision trees, all built on kind of different subsets of your data, different features, things like that, so that each tree is going to be a little bit different, but they're all built completely independently, and then all the trees kind of make a decision, make a prediction at the end, and you combine all of them or average them or things like that. And that can help improve your model significantly based on just using like one single tree. So that's a very common machine learning architecture that you may hear about. Linear regression is another classic one. This is meant more for like predicting a number. So if we were trying to predict a house price given the square footage of the house, we can plot all of our points and then use this linear regression algorithm to kind of iteratively determine what line best fits all of those points. So the function is kind of to optimize like minimizing the distance between the points and the line. And in this case, it's only 2 dimensions, but if you imagine we had a bunch of different features, you're plotting your line across a bunch of different dimensions to try to minimize the distance between all of your points. And then the last main like supervised learning model I want to talk about is the neural network. So this is a big, buzzword, something that a lot of people have probably heard of, but maybe don't really understand what it is. And the reason why neural networks are so kind of hard to understand is because they were designed in a way to make sense to computers, but not really to humans at all. So with a decision tree, we know how to follow a flowchart and understand what it means. When you look at a neural network, we don't really have a good way of really understanding exactly what it means, because it's basically just built up of a bunch of these like nodes that are all connected to each other in different ways. And each node has like a weight, which determines the impact of that node on, the overall model. So if we take in like our input data, for example, we would extract basically all of our features from it. So that's, each pixel or each group of pixels or things like that would all go into different nodes. Each node basically performs like a simple equation with the input data. The output goes to the next node, goes on and on. Basically, it just iterates through each node, and some will get activated, some won't get activated as much, but you end up with kind of a big equation that leads to a prediction. And then if that prediction is right, it's going to propagate kind of back through the network to reinforce which nodes were activated and how. So it says the model did well here, so the nodes and the values were good here. If it makes a prediction and it's wrong, it's still going to be back propagated through, but just to kind of adjust the weights and correct the errors in the prediction that it made. Now, the weird thing about neural networks is that we can't really map like an individual node to a feature. It's not really like you look at one node and it's like, well, this is the one that's checking for a nose, or one that's checking for if it's indoors or outdoors. They don't really map to anything that we understand. It's more or less just kind of a big abstracted equation that we don't really interpret, but that makes sense for the computer. And after enough iterations, it learns that these values are the ones that lead to the most correct predictions. In general, though, we can maybe correlate some of the layers of the network with overall concepts. So like our first level might be just looking at very simple lines and colors, and then the next one looks at more complex textures and curves and things like that. So there's a lot more models for supervised learning than just this. Those are just kind of some of the main big categories of them. And the correct model to choose for a certain use case just depends a lot on, like, for one, computational resources. A neural network might take up a lot more resources than like a simpler random forest. Same with the amount of data. You know, these models can scale really well to a large amount of data, but other ones that are more simple maybe can't. So there's a lot of factors to keep in mind when choosing a model, but if you have the resources, you can always try a bunch of them and just see what works best. The next main category here is unsupervised learning. So this is where we have unlabeled data and we want the model to basically find the patterns or structures itself. So rather than passing in a group of emails that are all labeled as spam or safe, we give it the group of emails with no labels at all and let it kind of decide how to separate those samples. So this is used for things like clustering, so segmenting customers into like different marketing groups, or for like health insurance. You can think of it for like real estate too, like clustering properties based on similar characteristics to make better recommendations to people. You can also do like association, so finding people with condition X also tend to have condition Y. Just in general, it's for any use case where you maybe don't necessarily know what the output should be. You're hoping to kind of discover something about the data. So as an example, if we just had like a plot with all of these points, how would we know how to segment this data into two different groups? So just looking at it, we can clearly see, okay, there's a big group in the upper left, there's a big group in the bottom right. Those are kind of two pretty distinct clusters of points here. But like, how would a machine actually know that? How would it determine that and match those clusters? Essentially, the way that k-means clustering works, which is one specific example of an algorithm that is used for a lot of unsupervised learning, is it will kind of randomly place two centroids, which are the middle of the cluster, and just kind of move them around until it matches what works best. So imagine that our two centroids start there and there, and we want to color each point based on what centroid it's closest to, so that decides what cluster it belongs to. So here, all of our top points are green, all of the bottom ones are red. Clearly, these are not the most optimal clusters, but that's just because we've just started. Now, the centroids kind of move around to the middle of all the points that are a part of their cluster. So if we were to average together all the green points and all the red points, where would that be? So they kind of move in more towards the center. Then we kind of repeat this process. We recolor the points based on where the new centroids are and keep moving it. So now, you know, some more of the left ones are closer to the green than the red, so they change. Same with the right group. And that kind of moves these clusters again towards the groups, which recolors them and gets them kind of in the right positions there. So just kind of iteratively, by changing those colors, we're able to clearly identify which two groups we have. This is a very common technique for a lot of clustering, like, you know, finding documents with similar themes. That's used a lot with like natural language processing and LLMs and things like that. But that all relies on a big assumption, which is that you know how many clusters you have. In that previous example, we knew that we wanted two clusters. That's how we knew how many centroids to place. So what if you don't know that? There's a couple different strategies there. One being like a hierarchical cluster where we pair points and then pair those pairs and move up and up. So think of like an evolutionary tree where we're clustering our species based on like the similarity of their DNA sequences. We could build out something that looks like that top diagram. We can also define like distances between points and make clusters that way, or we could just try a bunch of different values and see what works best. And there's a couple of different ways that you can define what like good clusters are by just looking at them or making certain calculations. And a subset of unsupervised learning is called self-supervised learning. This is a more modern technique where a model kind of turns an unsupervised problem into a supervised one by generating its own labels rather than having you pass external labels to it. So in these cases, the labels are kind of the part of the input data that gets held out from the model. So if you imagine we had like an input sentence and we were training a language model, the way that it might work is we hold out one of the words from that sentence, we give the incomplete sentence to the model, and we say basically fill in the blank, determine what word should go there based on all the context around it. That gives it kind of the label that it needs to predict, and it can determine whether it's right or not. And this gives language models basically the ability to understand how all the words in a sentence relate to each other by eliminating each word and seeing how it affects basically the meaning and the context of the sentence. This can also be done with like images, so forcing the computer to like generate a missing part of the image or to like unscramble the image like they're like puzzle pieces. This allows these models to understand the context and be able to generate accurate, sentences and images and things like that. And the last main type here is reinforcement learning. This is for training basically any kind of agent that has to like perform actions or make decisions. So think of like a chess bot or a robot or like a self-driving car. These things that like have to make determinations given the context around them at a certain point. And the way that those are trained are by basically repeatedly taking different actions in a simulation and learning which ones are favored or not by getting either rewarded or punished. So basically, they all just get like a number at the end, and that's their reward. And when they do something good, it increases the reward. When they do something bad, it decreases it. And then you can kind of boil it down to an algorithm of how do I maximize that reward? And in a way that then leads to the model kind of doing what we want it to do. So imagine we were training a self-driving car, and we wanted to teach it what's the right action to take in this situation. So we have the car on the road, we have a red light ahead of us. What should the car do? So in a simulation, it's basically going to try everything it possibly can just to see what gets rewarded and what gets punished. So first, it'll maybe just try to drive straight through the red light. And then we give it a penalty. We say, that's wrong. It loses points on that reward, so it learns, okay, that was not the correct action. That was undesirable. Maybe this time, it just drives off the side of the road. Also wrong. We can weigh each one depending on, how wrong it is. So we can give different amounts of penalties to emphasize more what it should do or should not do. Eventually, maybe by sheer chance, it'll try to just drive forward and then stop at the red light. And then we say, okay, that was good. That's what we wanted it to do. So now it learns that that's a rewarded action, and it will know to do that more in the future. But these models have to learn to take in information from their environment. So now the light has changed to green. If the car drives forward and just stops again, like we told it to do last time, this time it's going to get punished because that's not what we want it to do in this situation. So it has to be able to learn to take in other information from its environment based on, sensors and vision cameras and things like that, so that it learns it will be rewarded now because the light is green when it drives through. But of course, now we have a pedestrian. If the car drives through again, we're in trouble, and we're going to get a huge penalty because the reward for obeying the green light is less than the punishment for hitting a pedestrian crossing the road. So in the end, it basically builds up this huge table of all these different actions that it can take given all of the context around it. So it decides what's the stoplight, is there a pedestrian, and then what action should it take, and it kind of learns what the expected reward is there. This is how these machines are able to make decisions and decide what to do in each situation. But if you're looking at this and looking at like these rewards that we've defined ahead of time, you might have a question of, well, if we're just predefining every action it can take and every reward it should get, how is this any better than the rule-based learning that we kind of talked about from the 50s? And there's a lot of ways that this is addressed. So to keep people from having to define a reward for every possible thing a car could ever do on the road. So you can define, maybe just you make a reward for the final goal, And then through like an algorithm, every step that is required to reach that goal kind of gets an iteratively smaller reward. So if we want to stop the car, we don't need to define individual rewards for applying the brake and steering straight and everything like that, because we just have the reward for the final goal. Or we do the opposite. We define our rewards for very small steps and just let them be added up to create the rewards for the large goals. So instead of defining a reward for driving 1,000 feet, we just reward the car for every foot that it drives and penalize it every second that it stays still or moves backwards. Eventually, your car is going to drive 1,000 feet just from learning that. And the important thing with like machine learning here is that it can adapt to new situations by analyzing the similarity to previous ones. So it can essentially predict what the reward for an action will be based on all the actions it has taken so far. So for training a self-driving car, we don't need to train it on every single stoplight in the world for it to know what to do. We just need to train it on enough stoplights so that when it gets to one that it hasn't seen, it can look at it and say, okay, this is clearly a similar enough situation to the stoplights that I have seen before, and it knows what to do in that situation because it's been trained on other stoplights. Now, to implement any of these machine learning methods, you need access to resources, you need computing power to be able to run and train these models. And NAIR provides access to a lot of platforms that offer this kind of compute power. There's a lot that give GPU access, which is very helpful for training and evaluating models. A couple others I'll point out, MLOps is good for like tracking training experiments and like visualizing model performance, comparing between different models that you're training and seeing how well they're doing. Hugging Face is another good one for hosting and sharing models. So instead of having to necessarily train every model from scratch, you can find models that other people have trained and download them and use them for your own data. So there's a bunch of different ways that you can kind of improve the process of being able to use these techniques. So to wrap up here, machine learning is a very broad term here. It covers a wide range of models, systems, and applications. All of AI is essentially just a subset of machine learning. But at its core, it's just about, having a machine learn the rules of the situation instead of teaching it ourselves. And there's a lot of different ways you can do it, a lot of ways you can implement it, and a lot of resources out there to help you with that. And with enough high quality data, we can match human expertise in a variety of fields, in theory, with a lot of these techniques. All right, thank you. Do we have time for the demo? We want to do demo? Do we have time? Okay. We'll do a quick demo. It's fun. Let me pull it up. That is not it. So I just want to show a cool website. Oh, yeah. Oh, this is gonna take skill. Okay. So this is a website called Teachable Machine, which lets you basically, kind of for fun, but it helps you show kind of how these models work and how they can be trained easily. So if we get started, image project. Okay, so the way that this works is you can basically give it a bunch of images of kind of different categories and show it basically with like a live feed of a webcam how it can tell the difference between those two things. Does anyone want to come up here? Any volunteers in the audience? You don't have to, but you can have some images taken of you, and they'll be harvested and sold by Google, maybe. I don't know. That's a joke, I think.
Wow, that's the rap.
Okay, so we have a webcam up here. It's pointing somewhere. There it is. That's me. Okay. Do you want to just like hold down that button a little bit on the mouse? So basically you can hold down that button to like take images like rapid fire of whatever the webcam is seeing. So right now it is taking images of me. I can look at different angles. I can, try to move my head around to basically train the model what my face looks like right now. It's learning its best. That should be good. And then do you want to stand in front of the webcam? Get some pictures. You can model. I will go webcam here. All right. There you go. Wonderful. Love it. Love it. Perfect. All right. So now it knows what both of our faces look like. Forever and ever, maybe. And we just hit train model. And basically now on the resources on Google, they take in all of these images that or actually stay up here one sec. Sorry.
You're good.
It's going to train on all the images now that we've taken to tell the difference between these two classes. And then it will basically read in real time from the webcam to continue making decisions. So class 1 there is me. So if I stand in front of this thing, it will, in theory, know what class it is. So it spikes up to class 1 a little bit when I look at it. If you stand in front of the webcam, it jumps up to class 2 pretty confidently there. It knows you pretty well. So you can do this with a lot of different things, but it's just kind of a fun way to see how these kind of models can be used in like real time with very efficient processing. Thank you for volunteering. Alrighty.
Expo.
Yeah.
Let's see. I think you can like just take in, okay, so it gives actual like code too, which is pretty cool. So you can like implement that kind of model basically within your own workflow, read in new images and stuff like that. So that's a very, very simple example of how this could be done, but it works somewhat well. The more images you give it, the better it'll be and stuff like that.
So
yeah.
You can not have seen it behind the scenes.
I'm guessing it is. I know they'll have info somewhere of exactly what kind of model it is. Let's see. Okay, so you can tweak some different settings too. But it's a model that's hosted on like Google's like cloud platform that it just like in real time lets you kind of train an inference on. I'm guessing because it trains so quickly, it's probably a very simple like CNN that lets it go so quickly. But yeah, any other like quick questions? We're doing a panel at the end of the day, so if anyone has any like big long questions, we can maybe save them for that. But if anyone has anything right now.
Just had a quick question on your performance learning. When you were giving the example of the autonomous car driving, and you said values, how do you know the model knows what a value is? Do you have to define that a positive value up to 1,000 points is the best, and so that something that's 1/10 of a point is, or a negative is the worst?
Yeah. So essentially, it's kind of like an optimization function, right? So the model is kind of essentially mathematically trying to determine what's the minimum amount that it can do to get the maximum value of this number. So like it's easy for us to think of it as like a reward and a punishment because that makes sense to like how a human or a dog would be trained. But like to the computer, it's kind of just like the final number, and you can just define kind of ahead of time, maximize this number, and that's all it knows how to do. It's maximizing a number. It's an algorithm in the same way that like finding a derivative is, an optimization problem. So it kind of works the same way as that, where it just knows the higher that number is, the better whatever it's doing is. Yeah.
Do you ever, experience problems with overtraining?
Yeah, so overtraining can be a big problem, which is it's essentially where the model gets trained either there's a couple ways that it can happen. Either you like don't have necessarily enough data for what you're doing, or the model that you're using is maybe too complex for your use case, and it kind of like it overfits on your data, which means it memorizes basically the training data and then doesn't generalize to new data. So if you imagine like the neural network that I showed was just a couple nodes, a real neural network would be potentially millions of nodes, right? And the more nodes that you have in your network, the more that model is able to learn. Basically, if you don't have enough data, if I give it like 10 images of dogs to have it try to classify something, it has enough nodes in that system to just fully memorize what those 10 images look like. And then boom, during your training, you have 100% accuracy. Works great. The moment you show it any dog that wasn't in the training data, it has no idea what to do because all it's done is memorize what those images look like. So the more kind of complex your model is, the more data that you need to justify using it. because otherwise it's going to have enough power to just memorize whatever it's looking at, essentially. So that's one of the most like common problems with machine learning now, because having enough data is very rare. Nobody ever has enough data. And so whenever you try training with that, it can be very common for you to get really, really good numbers as you're training, and then as soon as you try to test it on something, it's bad. And there's a lot of different ways that you can kind of bolster your training data. So to take like the image example, you can turn one image of a dog into 100 images of a dog with different kind of transformations. You flip it, you crop out part of it, you change the colors of it. So all those kind of transformations that you can do to images, can help bolster your training data and make sure it's not just memorizing things. All right. Let me pull this back up. All right, and I'm going to hand it over to Baden Logan. Thank you.
So, let me adjust this. I'm going to be talking about generative AI and vibe coding. So one thing that I'd like to convey during this is that classification models are kind of the foundation of generative models. So say you have two classes, you have cats and you have dogs. And in this image on the left, these red dots represent cats and the green dots represent dogs. And you are trying to create a model that can classify these images. So if you give it a picture of a cat, it knows that it's a cat. If you give it an image of a dog, it knows that it's a dog. Now, one of the simplest ways that you can do this is just by using a linear classifier. So the idea is that you draw one straight line, you have a model train, and it draws one straight line between these classes. And so when you have new data, if it falls on one side, it's one class. If it falls on the other side, it's the other class. I'm also going to be talking about this perceptron up here. This is kind of the fundamental unit of a neural network. And it takes a vector of inputs, multiplies them by a weight, adds a bias, and then goes through an activation function. And the goal of these is to find a straight line that perfectly separates these two classes. So the issue with this technique is that it's very simple. You have one line dividing two classes, and if these classes are, say, like in a checkerboard pattern, it cannot divide them. The classification is going to fail. So those are really limited by a lack of depth. So the point I'm going to try to make is that these generative models have to really understand what the data looks like before they can generate new examples of it. So these very simple models, if all you can do is put points on either side of a line, it doesn't really understand the shape of the data. And to really generate new information, you have to understand the shape of the data. And this is where adding depth comes in. When you add more hidden layers, like more modern models have, you are able to represent more complex types of data and like really understand the class. So these classifiers kind of act like teachers for these generative models. So for example, I can talk about protein sequences. Before a model can generate a protein sequence, it has to be able to classify one. So every generative model has a classifier soul, I guess. It needs to know what right looks like before it can create something new. So when you train a deep classifier, the early and middle layers don't really see the raw, like the pixel values coming in or text. They are extracting high-level abstract features from the data, and these could be edges, textures, shapes, when you're talking about images, or they could be semantic relationships. So when you classify something like an image, you are kind of encoding it into a meaningful vector. Like, say you're classifying cats and dogs. If you're using a neural network to do this, at the end, the output could be a 0 for a cat or a 1 for a dog. Now, this is a really simple example. This is a very small vector, but it's a vector that represents what that thing is. Say you're classifying more things, many types of animals, cars, clothing. This vector, at the end, the output is going to be a lot longer. But it still represents what this class is. And another word for this is an embedding, and it's just a vector that represents the meaning of whatever you're classifying. So, autoencoders and latent space. So latent space is just an n-dimensional area where these vectors live. So embedding is a single point in this latent space, and you're actually able to do arithmetic on these things. So say you have a classifier that's trained on these words, king, man, woman, queen. So your classifier can identify these things. And you can actually do arithmetic with these things. So the vector for king minus man plus the vector for woman equals queen. And I actually have an example. I tried this at home. I want to show that this isn't just some abstract thing. I'm gonna move that back. I can't actually see that. So I found this really handy program called Comfy UI, which allows you to, sorry if that's really small, that allows you to mess with generative AI. And so I tried this where I encoded the word king, I encoded the word man and woman, and I added the vector for king, I've subtracted man from king, and then added woman, and then I went through this generative process using Stable Diffusion, which is a technique to generate images, and it actually did come up with queen, which I thought was pretty cool. So yeah, these let me move this back over. Or wait, I can keep it here, I think.
Let's see, arithmetic limited to plus minus.
I don't know. I think I've only seen it used with plus minus, but I think that multiplication would work too. I mean, the idea is that in this embedding space, the closer things are, the more similar they are. So I don't see why multiplication would be different. Although I don't know like what multiplying woman times a man would be.
I was trying to think of what square root of a woman.
Yeah, I'm not sure. But yeah, these vectors have semantic meaning, and the closer these things are, the more similar they are. So a cat and a dog would be this close, but a car would be way over here because they're very dissimilar things. And here's kind of a plot of that where you can see that's arithmetic. So when you have a classifier and you classify an image of a cat or a dog, you get this vector at the end. And these can be plotted, obviously. So what happens if you take a point in between cat and dog? What do you have? And just using regular encoders, you have nothing. It's a garbage point that has no real value because the classifier wasn't trained on the thing between a cat and a dog. And that's where the idea of VAEs come in, variable autoencoders. They map the entire latent space. So instead of these discrete points, you have probability distributions. So using a VAE, instead of having your garbage point between cat and dog, you have some sort of cat-dog hybrid. That's what that vector means. And then I have this note that if you use a decoder, you can convert the vector back into the original, the type of data that it was. So VAs versus encoders. So standard encoders are just discrete mapping. You put in a cat, you get an embedding for a cat. Meanwhile, the VAs use probabilistic mapping. You have something like a cat next to a cat. For standard encoders, the latent space has these dead zones where there are points with no meaning. Meanwhile, with VAEs, every point has some sort of meaning. It can just be maybe a combination of other things, or, that cat-dog hybrid. And with standard encoders, if you are trying to reconstruct whatever the data was, because there's one vector for cat, if you try to generate something with that vector, you just get a perfect cat. With VAEs, you are really able to generate interesting things because you can put pretty detailed descriptions of things in there, and even if the vectors that make up that description aren't actual points that it's been trained on, it can still come up with something. So these have applications in research. So you can use a VAE to compress sensor feeds so that they can be efficiently stored. And they have mapping uses. So you can use the latent space, like I said. Similar things are closer together, dissimilar things are farther away. You can see that you can embed your experimental groups and see if they're shifting away from your control group embeddings. And now on to generation. Say you have this vector, this embedding, you can decode it back into real data. So this says you can use a decoder to generate simulated experimental results to test your analysis pipeline before actual data arrives. So the next important part of this are generative adversarial networks, GANs.
Just a quick question.
Yeah.
Tell me if I'm off from now, but how does that kind of relate to tokenization?
To tokenization?
So are you using hard to give that to cat and dog? Are those tokens? So,
Well, when you're talking about LLMs, yes, those can be tokens.
not necessarily.
What?
But not necessarily.
So an LLM has a vocabulary made up of tokens. And these are all words, of course, because it's a language model. But yeah, some random string of numbers won't have a real token. But these tokens have IDs and they map to embeddings. So each token has its own embedding that could be put into this latent space. Does that make any sense?
Yeah, I just wasn't sure if that was just a standard thing you always did, because I know sort of the distance between tokens in that space is how some of those things work.
Mm-hmm. Yeah, so LLMs use tokens when you're dealing with images and you're not using a vision transformer. There aren't tokens. I don't think that's an idea that exists in that space. So generative adversarial networks. This is a technique where you improve the output of a generative model. And the idea is that this has two parts. You have a generator, and this is something generating data. Say it's generating a picture of a cat. Its goal is to generate the most realistic picture of a cat that it can. And then there's a discriminator that looks at this picture of a cat and tries to decide if it's real or fake. If it can catch a fake image, this goes back to the generator, and the generator is punished, and its weights are adjusted a little bit, and it tries to make a better cat. So here's a little chart that describes it. This discriminator is fed sample images from a training set, and then images from the generator, which is generating images from noise, and I'll talk about that a little bit later. The discriminator is being fed these images and trying to decide if they're real or fake. And this is how generators are able to make such realistic images now. So if you want to do something like this yourself, this is a very compute-heavy resource. So you would need an HPC cluster like Summit or Delta, and the Nair pilot offers these resources and you can apply for them. When you're doing research, this saves you time and computational resources. So the next concept I'm going to talk about are transformers. And this is the paper that came out in 2018 that Google published called Attention is All You Need. They came up with this idea called transformers. So when it comes to generating text, RNNs were a technique that were used before LLMs, but they had major issues. They were very forgetful, so when an RNN is generating text, it starts a sentence, but then when it gets to the end, it's already forgotten what it's talking about. It's something called the vanishing gradient. So when Google came up with transformers and this thing called attention, you could feed a string into an LLM, and then every word in that string gets compared to every other word. And so like you can see how every word relates to every other word. So it understands the meaning of that sentence. And so the next word generated actually fits and has semantic value in that sentence. Also on the subject of LLMs, there are things called LLM scaling laws. So I'm sure that you've noticed that some LLMs, like ChatGPT, are better than others. And that's due to these scaling laws. And there are 3 variables you need to know. Compute, which is basically just how hard the computer worked during this training. The dataset size, which is the size of the data set that was used to train the LLM, and then the number of parameters. And that's basically the size of the LLM, the size of the neural network. And the idea here is that if you improve any of these things by an order of magnitude, the model becomes noticeably better. Okay, so talking about image diffusion, so for generating images, the standard technique is called stable diffusion. And the idea here is that you train an image to remove noise from just a static image, a noisy image, until you have a high definition image. So the way these are trained is that, say you have this picture of a cat, over some number of steps you add noise. You add a little bit of noise each time. And then a model is trained to remove that small amount of noise over some number of steps. So for training, you would start on this side and add noise, but when you're generating an image, you start with complete noise, and then a model over however many steps removes noise until you have this image right here. So the idea that I'm trying to get across is that you have classification models, and when you try to classify something, your output is a vector that represents what that thing is. And these vectors live in this latent space. Latent space doesn't just have single points. Every point in there represents something, whether it's a cat or a dog or a cat-dog hybrid. Now, to generate something from this latent space, you just have to invert the classification model. So you get this vector and you feed it backwards through the network until you generate data based on that vector. And that's how diffusion models generate images and how LLMs work too. I'm going to move on to vibe coding. So vibe coding is creating code with generative AI, and it's become very popular recently. The term was coined in 2025, and it just describes a workflow where you fully give into the vibes and forget that the underlying code exists. So what you're doing is you are describing what you want the code to be like, or what you want your application to do. An LLM or a coding model generates it. You then go try to execute the code. If it errors out, you give it back to the LLM with the error, and you just repeat that process until you have working code. The use case for this are disposable research scripts, things that you can use quickly and you don't really need again. Quick data visualizations, front-end dashboards. So basically just really small things that aren't really hard to make. But there are pros and cons to this. One of the pros is that this is a lot faster. Also, it allows people who aren't experts in coding, like biologists or physicists, to code very quickly and make what they need. The issue with this is that inevitably there will be errors that you don't understand, and over time, the longer a coding model works on this, the more errors will pop up. That's compounding technical debt. There will also be security vulnerabilities because the model probably doesn't understand all of the code, and if you have several scripts, it's not looking at every script at one time. So it doesn't understand every single part of the code. This is also where spaghetti code comes in, and that's just where the code gets very messy and it's hard to maintain. So how are these trained? The data is sourced from public GitHub repositories, Stack Overflow, and technical documentation. And after all of these repositories, after all this data is collected, someone has to go through and clean it up. So if bad data goes into these models, the model itself will perform badly. So you need to get rid of the bad code, you need to get rid of duplicated code, and you just need to make sure that all the data going in is good. So the training objective for this part is to understand the syntax of code, and that's the grammar of how it works. It's making sure it knows that brackets need to match up, that if you're using Python, indentation matters, white space, and then fill in the middle. So if you just give a model code, it will know how to generate entire documents, but it won't know how to fix, say you like have a script and you want one function fixed. It won't know how to fix that. All it knows how to do is generate an entire script. So with this fill in the middle training, you give the model the front and the end of code, and it's able to fill in the middle. And this allows the model to edit existing code rather than just appending to the end or generating an entire script on its own. So after that, you do not have a coding model that you can issue instructions to. All it can do is, if you give it the starting line of code, it can just generate more, really, or fill in the middle. After this, you need to train it to follow instructions with supervised fine-tuning. And this is training on high-quality instruction solution pairs. So, for example, you would say, hey, write me a web server in Python. And then the model is also giving the solution and trained on that. And that trains it to follow instructions. So then after this part, it uses human feedback, where humans go through and rank the solutions that the model has come up with, and get rid of the bad, buggy code, and you leave in what you want. So you reinforce the model's taste in code and make sure all the code it generates works. And then another cool part is that, say you're using an LLM to write letters or something. Whether that letter is good or not is kind of subjective. Different people will have different opinions on this letter that an LLM wrote. But with a coding model, code either runs or it doesn't. So you can very quickly verify that the code a model produces is good by compiling it and running it. If it doesn't run, you punish the model for that. If it does run, you reinforce its weights. You give a reward for that. And that greatly speeds up the training time and reduces the amount of work because that step can be automated. So there are, of course, upsides and downsides to vibe coding. So the advantage to this is that it eliminates the syntax tax. So basically, you don't have to worry about the syntax as much. You don't have to learn how the language really works. You just focus on what you want, and then the model creates it, and it worries about the syntax. So the developer gets to spend more time on the design of what they want rather than the actual coding part of it and the debugging. This allows for faster test completion in controlled lab settings and just in a work environment. You are able to write code faster. And there are downsides. Technical debt increases very quickly. Security gaps are a big problem. The AI might not understand, the security that it needs to put in there. So there may be issues if you're trying to make in a large-scale application that the public is supposed to be using. And then the maintenance wall. If you didn't write it, you probably don't understand the code very well. If you spend a lot of time with code, if you see a bug, you probably know where that bug occurred and you can go and fix it. If you have AI write all of your code, if something breaks, you probably don't know where that issue is. You don't know how to fix it. So if you have multiple scripts, you just kind of have to feed stuff into the model until it finds whatever that issue could be. So I have this chart. The pros of this are near instant prototypes, but the cons are hard to find bugs. Low cognitive load is a pro, but the con is high maintenance debt. Another pro is that anyone can do this, but the con is security and compliance risks. The pros, it just works. The cons, why does it work? You don't know. Anyway, that is generative models and vibe coding. Thank you. And next, Mitchell Klesty is going to come up and talk about foundation models, LLMs, and computer vision.
Yeah, so I'm going to be building on some of what they introduced there, and we're going to talk about how it applies to large language models. But before I get started, how many people in here would call themselves technical? And like, who are the people that would do coding and actually use AI in like scripting and stuff like that? And how many people are not that? How many people kind of just use it in their day-to-day life without like fully understanding how it works? Okay, so about like 50-50 split. That's good. So first, we want to kind of frame this as what do we mean by large language models and how do we apply AI to language? So we know that human communication occurs in both text and speech. So us talking right now or something being written down or typed up is how we would be able to process that. But machine processes are really good at things like calculation, finding patterns, and data storage. And trying to kind of crosswalk between these things is what we call natural language processing. And there are a lot of applications of natural language processing, obviously, and that's kind of why we're all here today, is because the explosion of LLMs and AI in this space has made it so accessible and really kind of found the disconnect between people doing just research with numbers and connecting with how people interact and communicate with each other normally. So how do computers read? The answer is that they don't really read in the same way that humans do. So where we see something like hello world, to them that might look like this, which then breaks down into just a binary text string. So a bunch of ones and zeros is what they see as this text. And to computers, this doesn't really have any meaning other than a bunch of ones and zeros. They don't know exactly what hello world means. They don't know what message that conveys to people when they're reading it. So when we want to use computers to analyze things, what the initial approaches was statistical-based methods. So for instance, we might look at this sequence and do what's called a bag of words. So we just take a full sentence and we count up how many instances of each word were in there. And then we can make something like this, which is a word cloud. And you've probably seen this. These were really popular like 10 years ago. And this just highlights the most common words in there. Large is pretty big, models is pretty big. But you run into problems like stop words, like of and are pretty big in here, but of and don't really have a lot of meaning in terms of like what the actual meaning of this sequence was. So we don't really care about of and, so we would want to throw that out, right? The other thing that we can't see is that the order of words that happened in that sequence, they're not really tracked in this. They're just kind of like thrown up there and we don't know what that means. So it doesn't really tell us a whole lot, and the meaning of the text is not captured very well. Another approach that we have is called n-grams. So we could look at sequences or subsequences of the different sequences, and we could look at them a couple words at a time. So we split the sentence up into each of its words, and we might look at 2 words at a time. So we see this is a, and then a bird, a cat, a dog. So then we can use this for things like predictive text. If we see something like this, we might know that the next word is probably is. But then what if we see a? It could be a bird, it could be a cat, it could be a dog. So there's a big limitation there, obviously. The good thing about this is it gives us more contextual understanding than the bag of words method. So if we see something like read a book versus book a flight, we can tell if there's a difference between those words based on the context of the larger sentence. So if we see something like this is good or this is not good, we can tell that the this is good sequence has a more positive meaning than the this is not good, because we see not good versus is good. So it's a little bit more advanced in bag of words, but it's still obviously very limited. Next thing, as Vane introduced, recurrent neural networks. This was a machine learning technique that looks at sequences as inputs and then is able to learn that and look at each step, each piece of the data one step at a time, and be able to kind of track that through and make analysis on that. It keeps a memory of what's already seen, so each input token is then carried on to the next token within the sequence, and we can make predictions based on what we've seen previously in the sentence for a longer sequence than we can with some of the other methods. But this has a lot of limitations. The memory fades over long sequences, so at the end of this sequence, the question mark has very little knowledge of the what, whereas time has a lot more knowledge of the what because it's at the beginning of the sequence, and that makes this very slow and hard to scale in actual applications, because long sequences of words just don't really work and don't really train well. If anyone's ever tried to train one of these with, like, you put in Shakespeare's works or maybe Harry Potter or something and try to have it build something out, unless you have a really well put together set of data and model architecture, then it's just going to start repeating itself. It might, like, if it looked at this sentence and tried to repeat it, it might say what time is. It's not a fun process to try to train these things. So then, as Vane introduced, the Google paper Attention is All You Need was released in 2017, and this introduced the concept of attention and transformers. So through seeing a lot of text and getting a lot of information pre-trained into it, it's able to start understanding the relationships between words and sentences. So instead of looking at the sequence one step at a time, it looks at the entire sequence and realizes how each token relates to each other. Each one of the words or tokens attends to each other, is what it's called. And the stronger attention between each word is able to identify those relationships better. So in this example, we see the cat chased the mouse because it was hungry. After the model sees a ton of examples of text, it starts being able to pick out that it in this sentence has higher attention to cat than it does to mouse. So then we're able to know that it is referring to the cat in the sentence, and that gives us a good pronoun resolution. It also does things like remove word ambiguity. So instead of relying on just a subsequence of the word, or a subsequence of the longer sequence, like with n-grams, we're able to see the attention between bank and he sat by the riverbank attends really well to river, so we know that it's a riverbank and can kind of grasp that as a concept, versus she deposited the check at the bank. Deposited check and bank have strong tension between each other, so then that means that the bank in this is probably a financial institution. So then that kind of introduces the concept of transformers as what's called a foundation model. And foundation models are just pieces of deep learning models, which is then a subset of machine learning models. But what is a foundation model? It is an AI system that generally AI systems are very narrow purpose and you apply them to one specific thing, but then foundation models are built out to be more broad purpose. So while they don't have like super broad capabilities like Aaron was talking about earlier, you wouldn't want to take X-ray, a model that's trained on X-rays, to then apply it to self-driving cars. But foundation models might be able to do something like that, where they're able to be shown lots of images of both X-rays and things that cars might see. And then you could apply that same model to both tasks. But this requires a lot more training, obviously, and a lot more data than these more narrow purpose models. So the idea, though, is that you train the model once, and then it is able to do many, many tasks rather than the very specific thing that it was initially trained for. Most foundation models are transformer-based. That's not a exact rule, but generally the transformers work best for this out of all the other types of models. And it uses what is called self-supervised learning. We talked about this a little bit before, but essentially just as it sees more data, it teaches itself the relationships that it needs to know. So then it uses embeddings, like Vane introduced. Embeddings are just a high dimensional vector. They exist in that lane space, and the concepts that each input of the sequence, in this case for LLMs, it will be tokens, which end up being words. It kind of maps where those concepts relate to each other, and then is the math between that is able to be done to kind of make those relationships understandable to where the LLM may not know exactly what a puppy or dog is, but it knows that those are related. So then it knows that it can use that later when it needs to do analysis on those inputs. So when you take a foundation model and you want to apply it, what you want to do is you want to train task-specific heads. So these heads are more lightweight things that are able to do the specific task. So you transfer the learning that it got from the general data that it was trained on for the very specific task that you want it to do. So for instance, with the breast cancer detection versus the self-driving car, you would have a head that was able to look at the different images that were able to make decisions for the self-driving car and then apply the embeddings that were generated by the foundation model to that head. That head then uses something like a classification model for a specific decision or whichever type model it may be for the specific thing that the self-driving car needs to make. For the breast cancer images, it might look at the x-rays and then segment out a tumor or something within that. So then you take the embeddings, like I said, of the foundation model for the specific image, apply it to a segmentation model, a classification model, whatever it may be, and then that is able to do the thing you need to do. So again, tasks you can do are very wide, but the kind of general rule of thumb is you're just producing the embeddings, and then each feature of that embedding, so each number within that vector, is then used as a feature in another traditional ML model. So when we want to train a large language model, what does that look like? We all know how ChatGPT and models like that work, where we're able to put in an input, and then we see the text being spit out as as it generates the thing. We can see the text just flow out of it. So the first step that we need to do is collect and pre-process our data. So to do that, what we want to do is scrape sources from the web. Hugging Face datasets is a very popular source of this, but any website, any existing source of text, we just want to be able to take the information from there that will be most relevant for whatever we're training on. For general purpose LLMs, this is as much text as we can get that has accurate information. It's very important that the information is accurate and we're not training the model on something that is not correct, obviously, because we don't want the model to learn and be able to predict things that are not true. Makes sense and is pretty intuitive. But the other thing that you can do with that is personalized data. So maybe you don't just want to train the model to be like completely broad, sweeping, and knowledgeable about everything. Maybe you have very specific information for your business or for your university or whatever it may be that you want the model to learn. You can then take that and you can convert that into a data set that the model is able to read in and learn from to be able to do the same things that it can do with anything that you could ask ChatGPT or any of those open models to do. It could then be given information about your specific instance or your specific information. So tokenization, how does that work? Tokens are words or word-like units, and they are what become the unit of input for the LLM. Yes?
On that last slide, you had Hugging Face on that?
Yep.
Can you describe what Hugging Face is?
Yeah, so Hugging Face is kind of a repository for models and data sets. So it's a very common place for open source models. If you were to just you go look at it for a specific model, like the LLaM models are really common open source models. They are able to put their weights on Hugging Face, and it has really good storage for you to be able to just go and download that model. So it's very common in AI to post your models if you want to make them open source to Hugging Face. It's the same way that you would with GitHub, but it's for models and data sets like that. Does that make sense? Thanks. So for tokenization, tokens are words or word-like units. And like I said, they're the input sequence for an LLM. So if we have this sentence, John couldn't eat the pizza, pretty much every word in this is a new token, except we see things like could and apostrophe T are broken up, and the period is its own token. So it's not exactly like every single word is a token, but it's roughly that. And the way that it generates this is it looks for common sequences in the training data set. So you have your input training data set, and it looks for what are the most common phrases and sequences of text that exist in that data set. And then from there, it builds that out and it finds what is the most common two-word phrase in this, or two-word subsequence in this. Two-letter, not two-word. And then what is the most common three-letter, four-letter? It expands that out until it gets to a point where it has a very well-defined vocabulary. Generally, this ends up being like a token as a word, but then some words get broken up, like could and int get broken up there. Punctuation gets broken up, stuff like that. So all of these tokens are then put into the model's vocabulary, and that is the sequence of every single thing that it knows. So based on your training data, the vocabulary has every single possible instance of what it knows, and then you can build out the entire vocabulary with the tokens that exist. The tokens are then given IDs based on where they exist in the vocabulary, and that ID is what is passed into the model. So if we look at this sequence, the first president of the United States was George Washington. Each one of these words has its own token ID that's associated with it, and then there's an embedding layer for those token IDs where it maps the token to an embedding. So when we want to pre-train the transformer for the LLM, we initially assign these embeddings for each token ID as a random value. So it's just a random set of numbers in the vector for each token. But then we start training it, and we want to update those weights so that the vector values have some actual meaning and aren't just complete garbage. So we might want to provide a subsequence of this, like the first president of the United States was, and then predict George as the next token that we want to say. So we provide the embeddings for each of those words, and we then pass all of those embeddings into the attention layers. The attention layers does some kind of complex matrix algebra on the passed-in embeddings, and then they attend to each other. So each of the embeddings within this sequence is going to adjust the other embeddings within this sequence, and they are going to learn from what is in the sentence. The final token in the input sequence that we have is then passed to an output projection layer. This is a classification model, like Vaden was saying, how classification models are the heart of generative AI. This classification model then looks at the entire vocabulary and produces a probability for which token is most likely to be the next token in the sequence. So for the entire vocabulary, what is the probability that it is going to be the next token? So in this example, our model is saying that George is the most likely next token. We then check and we see that's a match. That the next token that we wanted it to be was George. So then we can reward the weights in the attention layers and the embeddings in the embedding layer. So the embeddings associated with each token then get adjusted slightly to associate what they've learned from the sentence, and the attention layers are updated to kind of make sure that they know what they're doing and are providing the correct calculation to each of the embeddings. But what if we think that John is the next word? Well, obviously there's a mismatch there. We do the same thing, except instead of updating them with a reward, we punish them. We update them in a way that makes sure that the embeddings know that they did the wrong classification there. So what do we have now? for any input sequence, we can then take the whole architecture of this model, pass it through, embed, and get the classification for what we predict the next token will be. This means that we can then generate text until we tell it to stop. So for any given input, it is now mimicking the training data to the best of its ability to predict the knowledge that it says and complete the sequence of what we have. And when we finish once we've completed doing this and we've trained on enough data, it gains what you can call knowledge, but as Aaron introduced earlier, it's not really knowledge. It really depends on how you define knowledge, I guess. So it doesn't know what it's saying unless you want to say that. It's a really complex topic of the model doesn't really understand that George Washington is the first president. It doesn't know what that means, except it is able to spit that out. So because it's seen it so many times, it's a complex debate. But what we're able to do here is then after enough training, if we see the sequence of 16th president of the United States, the LM can then guess Abraham, pass Abraham back into the sequence. We add that onto the sequence, pass it to the LM again, and then it predicts Lincoln for the next token. So then we have the final sequence of the 16th president of the United States was Abraham Lincoln. Problem here is that all it's doing is completing input sequences, right? So it has no conversational ability. We couldn't talk to it. We couldn't have it serve as a chatbot or assistant, but obviously we want to do that. So what do? We do what's called instruction fine-tuning. So fine-tuning in itself is just further training on a small specialized data set. So we take the pre-training of just throwing a bunch of text at it, and then we create more specific information that we want the model to learn, and we pass that into the model afterward. And based on its ability to handle text and have a general knowledge, it's then able to learn better from this specialized data set. So we want to use what's called instruction fine-tuning, which is fine-tuning on a data set which has instructions and turns of user and model interactions, right? So we start off with a user message. When we pass that to an LLM, we want to give us an assistant message. So if I say, hi, how are you? I want the LLM to say, I'm good, how are you? Well, so we can wrap this with user start tokens and user end tokens, and then assistant start token and assistant end token. So when I provide it user start token, hi, how are you? User end token, the model's now able to know that I, the user, was saying, hi, how are you? And it's able to tell me, I, the model, am saying, good, how are you? So then we can take that and we can create a kind of merge of the entire conversation. It's a sequence of user messages, assistant messages, and now it was my turn again. I said, I'm good, who was the first president? And it's able to respond with the assistant start and end token wrapping around to acknowledge that it was talking, and it says George Washington was the first president. So then you can do something which is called adding a system prompt. So if I provide instructions that say talk like a pirate, and I ask, hi, how are you? It might say, yar, I be good, or something like that, where it is talking like a pirate, following the instructions that I provided it. This system prompt is how you can provide kind of general information to the LLM about how it should act or specific circumstances that it should follow. This is where you put that. It's not part of the turn of the conversation that the user and the model are having, but it is instructions that you want the model to follow. So from this, we can then also create a data set of messages and generate a full sequence of this and do the instruction fine-tuning. And the LLMs will then be able to respond to any input sequence that is a conversation between the model and user, and this is how they act as chatbots. So when I want to train additional information in to do things like being able to help with coding, I might look at a Stack Overflow query. So this person on Stack Overflow was asking, in Python, how do I delete an element from a dictionary? And this is something that someone answered, and it was upvoted. Everyone loved this answer. And the model is then able to be taught based on the input sequence of the person is asking, how do I delete this? Here's my stipulations for what I want to do. And then the expected sequence that we want to generate is the output from from what the answer was on Stack Overflow. So we create this in structured format that is then able to, at scale, provide us coding knowledge into the LLMs. So do this for lots and lots of different questions that are on Stack Overflow. All of a sudden, it knows how to code. Do this for the U.S. medical licensing exam, and it's provided with medical education knowledge. Do this with Archive, Google Scholar, places of research papers are published, and all of a sudden it gains academic research knowledge. One thing that's important to note here is a concept called context length. So this is the maximum number of tokens that a model can process at one given time. So every interaction between the user and the model is a full interaction of the entire history. If I'm having a conversation with ChatGPT and it is responding to something I said 3 messages back, that's because when I hit enter, it sent the entire chat history of everything that I put in to the model, and now it is generating us the output sequence from looking at that entire turn-based chat, right? That only works up to a certain point. So the number of tokens that any given model can process differs based on the architecture of the model, but once you exceed that token limit, it will not work. So it'll either error out, or it will you'll be forced to truncate the original messages, something like that. So this is the total input and output. So the input sequence is, again, everything that I have had in that conversation history, system prompt, and all of the messages between the user and the model. And then the output message that is being produced, the sum of the tokens that are in that turn of the conversation must not exceed the context window. The context window or context length has kind of grown over time. So some of the initial ones were only a couple hundred tokens. It grew to 1,000, and then it ended up at 8,000, 128,000, and now we have some that are 10 million plus tokens. The kind of development of this is pretty fantastical. It was a pretty extreme growth where within 6 months we went from 8,000 tokens to 128,000, and then all of a sudden we're at 1 million, and now some can do 10 million. But the one thing that is important to keep note of here is that a lot of times companies will kind of game this system. So the model is able to handle 10 million tokens, but it probably can't actually handle, like if you put 10 million tokens of context into a message, it's not really going to remember. There's a steep fall off after a certain point. So that's something to be aware of when you're developing these applications, is what is the actual context window? What is like the thing that they're saying? And at what point does the model just kind of fall apart once you start throwing that many tokens into it? So this is kind of below the weeds, or in the weeds, but hopefully this kind of opens up the black box of why LLMs do things that they do, because kind of understanding why these models work and how they work is obviously going to be helpful for developing your applications. And even if you're not an application developer, it's a good thing to keep in mind for how things work and being able to understand like why there might be problems that arise that you couldn't have foreseen if you don't know how the things work under the hood. But what resources are required for training something like this? You need data, lots and lots of data to train. You need a ton of computational power, and you need time. For very small data sets, you can train something on a single GPU, and it might take a few minutes or it might take a few hours. Those models are not going to be very performative on anything very broad. They're going to have very specific use cases, and they're only going to work for a very small data set. Kind of medium range models can require a few GPUs and can take a few hours or a few days. But as you start getting to larger models and frontier models, the requirements on both data, the computation, and the time kind of becomes limiting for everyone. You're not going to be able to train them at that point. To put that in perspective, the amount of time that it is estimated would have taken for training ChatGPT 3.5, if you use an NVIDIA V100 GPU, which has 32 gigabytes of memory, it would take you 355 years to train that, and it would cost you between $4.6 and $5 million. What is estimated how OpenAI trained it was with 1024 A100 GPUs, which was the top of the line gear back in the day when they trained this. that has a 1,920 gigabytes of RAM, and it's estimated that it took them 34 days and $2 to $4 million to train.
What is the cost encompassing, like the power?
Power usage, and this is not including like purchasing the equipment. This is just the power to train it. Yeah. Yeah. So, lesson from that is that you probably don't want to be training LLMs for the most part. You want to be fine-tuning and using existing LLMs. Lean on what the companies that have the resources to train stuff like that have, and then kind of fine-tune them for your specific use case. So how do you customize those models? Well, we talked about fine-tuning. That's one approach. There's methods called LoRa for training LoRa adapters where you are able to fine-tune the model further for new information. Another thing that Dr. El Maghrabi introduced this morning was RAG, Retrieval Augmented Generation. This is a more popular and more simple approach. So essentially what it is addressing the problem where LMs hallucinate, and they kind of just make up information and they're very confident about it, where they don't have the full context that they needed for answering that specific question. So what you do is you take the user's query, you find what information is going to be relevant to that query and answering it, and then you provide that into the context of the model. And then once it is able to see the input query with the context in the same conversation, it can generate that output with that context in mind. A really popular way of doing this is called vector database and embedding search. So you take a large document store, you chunk it up into smaller documents, and you embed them using the transform models. That creates a set of points with which exist in vector space. You can think about it like in 2D, but obviously these are very, very high dimensional vectors to capture the meaning of each of the documents. So then when you have a user query, you can then also embed that using the same model into the latent space. And you can find which documents are most related to that query. So then those documents can then all be grabbed, extracted from the vector database, and put into the context, provided alongside the user query to the model. And then the output that is produced will be aware of that context that is provided. So for instance, you could say that your company has a lot of specific information in a document database that you want to be able to pull from, specific resources or something. You could embed all of those resources as small chunks of text, and then take the user query, embed it, search for which ones are most important, add those to the context, and then the LM would be able to process that information as well. Another way that you can do this is what's called tool calling, and tool calling is the basis for what we know as agents. This is registering external capabilities or tools for the LMs to call on, and a lot of times you'll hear the word agent, and that's kind of a buzzword, but really what agents are applying LLMs to existing capabilities, which are the tools, and applying things like RAG and other methods as well to make the LLM serve a specific purpose and have access to specific capabilities. LLMs in and of themselves, unless you're using a multimodal model, are entirely text-based. So they're only able to know like what text is being input, what text should I output. These tools that you provide are then able to provide more capabilities to them so that they're able to actually perform actions and do specific tasks. So if I were to ask the weather, or ask the LM, what is the weather today? It might say it's sunny and 86 degrees. Obviously that is not true for today. So this is a hallucination. We know that this is not true. But what would we need to answer what is the weather today? We need to know the location, the date, and the current weather for that date and that location. So we can provide the LM with a weather lookup tool. So this is just some code that exists externally that the LM is able to provide text for what the inputs it needs and that it needs to call that specific tool. So the weather lookup tool is defined as needing a location and a date, and the LM needs to be able to tell the tool that it needs to run, right? So if I pass what is the weather today, I need to give it the inputs, location, and date. So maybe I expand my query to what is the weather in Lexington on January 12th? And I pass that to the LM, and then it spits out, I have January 12th as the location. January 12th, 2026 is the date, Lexington as the location. And then from there, I'm able to call the weather lookup tool. So then that tool generates that it is cloudy with a high of 26 and a low of 21, and it provides that back to the LLM as context. And then it spits out, it is cloudy with a high of 26 and a low of 21. But what if, oh yeah, sorry, that's right. So what if I don't want to say that? I don't want my user to have to tell me where it is and what the date is every time, right? So I can provide more tools for user location lookup and what is the date, just essentially the simple capabilities of knowing basic information about the user. And instead of the user having to tell me that, I'm able to call on those tools as well. So the LM does what's called orchestration. It decides it needs to do multiple steps instead of just one single tool call. It needs to look up the user's location, look up the date, and then provide that to the weather lookup tool. And then it will be able to have the full conversation without the user having to tell it the location or date. Another strategy, like we said before, instead of looking up that information is pretty easily available. We don't need to look that up every time. So we can just take that and provide that as a system prompt on top of the user or on top of the message. So maybe every single message that we have provides some basic information about the user. And we tell it the user is in Lexington, Kentucky, and the date is January 12th, 2026. If you're ever talking to ChatGPT and all of a sudden it seems like it knows more about you than what you have just told it, this is how it does that. It takes that information and puts it into the additional context in the system prompt, and then it's able to pull that when it needs to for the things that it's generating. So these are some of the building blocks of language AI, and really what you need to do is think about for your specific applications and your use cases, how can I leverage these tools to apply them and make the best use of AI? So yeah, with that, I'll hand it back over to Vaden for computer vision.
Can I ask a quick question?
Yeah.
Tokens, are they harmonized across languages and symbols? So the token IDs. So there's always a period, 916 you had up there. Doesn't matter what language model you're using.
Yes, so each language model has its own way of tokenizing things. Each language, even with the assistant start and end token, those will be different for every language model architecture. So the way that it does it is it takes in the training data and it looks at the sequences of ASCII characters. So those are like the base characters that we provide. And it just combines them into the most common sequences to create the tokens. And then from there, it is able to produce that. That differs based on how each different architecture trained the things. So each different model has its own tokenization, but then it'll cover characters between any of the human languages. It's really common. A really common task for transformers is actually translation. So the way that embeddings work, if you're able to embed a sequence with in English and you want to convert to Spanish, for instance, the way that the attention between each of the embeddings of the tokens work makes it very easy to then translate sequences into other languages. So you just encode the entire vocabulary of whatever human languages you want, and that's able to be translated between them.
What about doing symbolic languages? Doing Chinese or the characters? Is that the same?
Yes. So the Unicode representations of those different languages all exist as just the characters, obviously. So then if we have enough training information, we are able to convert the tokens or the characters within those sequences into tokens that can then be used with attention the exact same way. So that's how most modern translation systems work, is with transform models.
Thank you.
Yeah.
At one point you mentioned a high dimensional vector. Just for sake, some of us who don't work with this, what are we talking about order of magnitude as high dimension?
Generally, numbers you'll see are like 768 or 1064 or 1024, sorry. Those are the general numbers, yeah.
Okay.
Thanks.
Hello. Okay, so I'm going to be talking about computer vision models. So, what are computer vision models and where are some places that we see them used? Here we have a picture of a city street, and you have some sort of segmentation model identifying the bicycles, the cars, the trucks, the traffic lights. Here's an example where it's a picture of someone's back and it looks like the dangerous looking moles are being picked out. And here's a model that can identify breast cancer. And here's a very classic OCR model that was trained on the digits 0 to 9 and can identify them. So how is this done? There are two main architectures that can identify what's in an image. There are convolutional neural networks. This is more of a classic technique. And then the more modern technique is vision transformers, similar to what you heard about in Mitchell's presentation about transformers and attention. Vision transformers use that technique, but with images rather than actual words. So each technique has its own strengths and weaknesses. CNNs are a lot smaller, so they're data efficient. And then also because they're smaller, they're computationally efficient. It doesn't take much power or space to run them. They're also excellent for local, close together features. And they have a strong performance even without massive scale training, unlike the vision transformers. They do have some weaknesses. They have limited global context. So if you need to identify an image, but to identify it, you have a feature in the right corner and then the left corner, because those two things are far apart, it will be a lot harder for the CNN to identify what that image is. And then they have a much more rigid architecture. Vision transformers built off the transformer architecture. They have some strengths. They have superior global context. So, I don't know, say you have a picture of a dog or something, and to identify it, you need to look at either ear. You need to see that it has two ears. A vision transformer will be better at that. They're scalable, they're flexible, and because they're based off of LLM technology, they are ideal for multimodality. So you can, describe something with text, and it translates really well into the vision world. They use the same latent space and embeddings, but it does have some weaknesses. As you probably know, LLMs are very large, use a lot of power and a lot of memory, and vision transformers being built with the same technology are similar to that. They are data hungry and computationally expensive. So I'm going to go into each of these and explain how they work. So convolutional neural networks. How can a program determine if this picture is of a cat or not a cat? You could look at the ears, how far apart they are. You could look at the stance of the cat. It looks very similar. So yeah, you could maybe tell that these are both cats. But what if you get into a situation like this where the cat's in a completely different pose? This system that you had before completely falls apart. Or it may look like this. It could be completely different. And this rule-based system won't be able to identify it. So how do these convolutional neural networks work? They use something called filters and kernels. And some of these filters, like in this top row, they may identify colors in an image. And then as you go farther down, things get more complex. Some layers identify lines, and then as you get further down, they identify textures and even more complex things. So here's an example of a convolutional neural network that identifies horses, zebras, and dogs. and I'm going to step through and kind of show each part. So the left side of this diagram represents the computer looking at the image and trying to extract meaningful patterns. So the input is this raw image of a zebra, and then this yellow square that you can see over the zebra's leg is called the kernel. And it's kind of the eye of the computer looking at this picture. Now what it does is it slides over the image pixel by pixel and tries to scan for specific things that it's been trained to look for. So in the case of a zebra, some of the identifying features are these lines on it. A CNN would be able to find those lines and use it to identify that it's a zebra. So after this, you have a few layers of convolution. And what this does is this process creates feature maps as the kernel scans. And this is a map highlighting where it found specific features like these vertical stripes. And then ReLU, this is an activation function that helps the model learn nonlinear patterns. So essentially deciding if a feature is active or not, whether it's there or whether it's not there. And then between each step of this process, you can see pooling. And this reduces the size of the feature map. So you can see the yellow square on the zebra image kind of reduces down to 1 pixel in the next layer. And the same thing happens in that layer to the next layer. Essentially, this eye, it looks at a block at a time, but that becomes 1 pixel in the next layer, and this pooling makes it smaller and smaller. This simplifies the data and keeps only the most important information while reducing the computational cost. So as the data moves through these 3 stages, convolution, pooling, convolution, the network moves from detecting the simple straight lines on the zebra to more complex pattern, like the texture of the zebra fur on or the shape of its leg. So then you get to this flattened layer in the middle. So the data changes format. The 2D grids, these feature maps are flattened into a single long vertical list of vector. And this is how it's prepared. The visual data is prepared to be processed by the final classification network, the final neural network. So this neural network is kind of the brain of the model. So the right side acts like a traditional neural network, and it uses those extracted features to make a final decision. And then you have some fully connected layers. Every node here connects to every other node in the next layer. And this web of connections analyzes the high-level features to determine what object they form. Like I said, as the data passes through the neural network, it is able to identify more and more complex features from the image. And then finally, you see this softmax activation function. This final step converts the network's raw output scores into probabilities for what the class of this image is, what is in the image. And then the output is just probabilistic distribution. Here, the model is 20% confident that this is a horse, 70% confident that it's a zebra, and then 10% confident that it's a dog. And that's how CNNs work. Now, if you want to train something like this by yourself, there's some NearPilot resources. NCSA Delta AI, this is a compute cluster that deals with images. And then a couple more like sets. C-Haven is for synthetic data generation, because obviously you have to train these networks with data, and this helps you generate it if you can't find enough for yourself. Okay, next I'm going to move on to vision transformers. So unlike CNNs, which scan pixels with sliding windows, vision transformers treat an image like a sentence of words. So, for the first step is to split this image into a grid of fixed size square patches, like 16 by 16 or something. In this case, the image becomes a 3 by 3 set of patches, and then these patches are flattened into a vector, and then fed into the model in sequence, just like words in a text translation model would be fed in. Okay, yeah, like I said, the image is converted to patches and then vectorized. And then the result of this is an image sliced into 9 fixed size squares called patches. Instead of one picture, we now have a sequence of 9 smaller images that is easy for the model to digest. The next part is linear projection and embeddings. The linear projection yellow block and the column of blue boxes labeled 0 to 9 is there. So each square patch is enrolled into a vector, and then we pass these vectors through a linear projection layer. This converts the raw pixels into embeddings, which we've talked about a lot. It is a numerical representation of the meaning of a word or a picture. And then one thing to point out is that extra blue box at the top labeled 0. This is the class token, and it's where the final answer will eventually be held. And then we have positional embeddings too. And this step adds, you can think of them as coordinates to each patch, so the model knows what order they are in and how to reconstruct the final image, or how the image was before it was separated into chunks. So these embeddings are then fed into a transformer encoder. So this transformer, we heard a lot about them in the last presentation, but attention is applied. So each patch of the image is compared to the other patches, so you can see how they attend to each other. And this helps you understand how each part of the image relates to each other part. So say you have a picture of a dog. I'm going to use the ear example again, but this ear of the dog relates to this ear of the dog. They both belong to the same dog. So next we have a dual output in this model. The far right shows the MLP head, and then we have a score cam. So the score cam shows a heat map of what the vision transformer looked at, what it decided was important using attention. And in the case of this cell, it's the cell itself, obviously. That's important for deciding on what it is. And then you have the classification, so basophil, neutrophil, just a different type of cell. And I'm going to show you, I actually have images that kind of show you the difference between vision transformers and convolutional neural networks. You got to pull this up. So given a picture of a dog and identifying it, this is what a convolutional neural network would see. Like I said, it struggles with global context. So the part that it decided was important was this huge blob in the middle, just the dog. That's how I identified the image as it was scanning across. A vision transformer is different because when it scanned this image, it saw this. Instead of one big blob, it looks like the ears of the dog to decide that it was a dog. And then it looked at the end of the stick and then a few other things and deciding that it was a dog. So this just shows that while a CNN struggles with the global context, a vision transformer can look at the entire image and make decision based on each patch and how they relate to each other. And I'm going to try to get back to the slideshow.
Question.
Yes.
So is the vision transformers, is that like an array of sorts?
I'm really not an expert on transformers, but vectors are fed into the transformer. the embeddings are. But the transformer itself is not just an array, no.
Okay.
Yeah, sorry I couldn't answer that better, but transformers are not really my specialty, unfortunately. Okay. So in summary, the differences between these two models is that vision transformers create patches from an input image and then treat each of those patches as words in a sentence and see how they relate and what the meaning of the entire sentence is, the entire image. Create embeddings from those patches, perform attention, and then output the result of what it thinks it is. And then CNNs do the other process where they scan the image, and then pass the features through a neural network. So in order to do stuff like this, there are some more NearPilot resources. The Sage Edge computing platform. This is good for edge deployment and real-time vision. Like if you're showing a live video and you need to see what's in it, like I could show a video of this room and it could identify all the people in it. And then there are some compute clusters that are good for training. And then the NeoCortex CS2, which is good for training these models from scratch. And anyway, that is vision transformers and CNNs. Yes.
For vision transformers,
Mhm.
do you have a certain number of pixels once you've decided your path pattern? Do you have a certain number of pixels overlap or anything like that, or how do you tile it out?
So the CNN does the overlap, but the vision transformer doesn't do any overlap at all.
Oh, okay.
Just like an LLM doesn't overlap the words in the sentence, the vision transformer treats each patch like a word in that sentence and just sees how they relate to each other.
Thank you.
Yes. Are there any other questions? Okay, thank you. And I think we have a coffee break now.
Everybody, we're going to go ahead and get started with the final presentation of the day, which is on AI pipelines and how you can actually put some of this into practice. So first off, what are AI pipelines and why are they important? Pipelines are just kind of standard processes and standard processes that are used for application management. So standard things that you're going to be doing that you want to repeat and you want to have a set kind of protocol of how you do them. You can build a pipeline that will then let you flow through everything. Integrating AI with your unique data and system is going to be critical for developing a specific pipeline to do the things that you want to do. And for that, you need to know how to deploy the appropriate resources, not put too much into it because that can get extremely expensive, and not put not enough into it because that can cause the system to fail. The kind of key thing I want everybody to keep in mind while we go through this is that each project is going to have very unique needs. So one person may only need like $20 of OpenAI tokens, whereas someone else may need a whole HPC cluster to do the things that they want to do. This is going to be kind of a broad presentation because of that. So just keep in mind that everything is very relative to your specific needs, and your specific needs may change over time or between different projects. So just kind of understanding the whole ecosystem of what goes into this is very important so that you know what you're doing going forward. And then something else that we want to know is we want to be able to identify where AI is useful and where it isn't. A lot of the time, applying AI to specific things, especially with language models, can get extremely expensive. And if there's better ways to do things that are not AI, you want to do that. So we need to just figure out what the best way to use AI is and how we can best implement them into our projects. So the full AI project lifecycle starts with concept development. So that is just identifying what problem you want to solve and how AI applies to it and being able to fully flesh out that idea. Then we need to know what data we have, and we need to explore how we can prepare it for AI, both in training and in processing, and then what needs to be done to make it AI ready. Aaron talked about what those principles of AI ready data are, and we just kind of need to morph our existing data into that form. Next, we want to prototype the model. So what purpose should it serve? This is very related to the concept development, but specifically, what does the model that you're going to build do, and how does your data apply to that model so that you can achieve that goal? Building out the pipeline is the next step. So once you have the model kind of identified, you need to be able to train it and then deploy it within the system. How do you connect it to the larger architecture of the system that you're building? And then how do you interface with the model is a big part of that. If you need to make this accessible to the public, then how do you do that? If you need to make it accessible to specific researchers in your department, how do you make it accessible to them? How do you make this deployable in a way that people can use, you can use, whoever needs to use it can access it like they need to? Evaluation, how does the model perform? You need to know, is it doing well in specific areas? Is it performing poorly on specific inputs? And then how do you adjust the model to address those issues? And then you also need to think about how the larger system performs alongside of it. If you have a model that takes 3 minutes to respond and it's supposed to be in the middle of a user interaction, then that's probably going to be very cumbersome on your users if they have to just sit and wait for the model to produce something. So you need to think about what is going to be the overhead of the model and how it performs within the whole pipeline. Security and privacy checks are very important in a lot of situations. If you have identified data that should not be released publicly, you need to make sure that your data is very protected. You need to kind of wrap the entire pipeline and system that you're building in security. Make sure that users are not putting in information that is then going to be existing on your database that if someone were to get into that database, it would be bad. Or if you are violating their privacy rights, you want to make sure that everything within the system is kosher and all good. And then you get to deployment. So at this point, you want to actually deploy the system, and you need to know how much load you can expect both on the model for how much inference resources are going to be used, and also on network. So you need to make sure that you have the proper resources on the network to be able to actually host the things that you're trying to host and make available. You need to know where you're going to host. So can you use cloud resources to host your application? Does it need to just be something local on your machine? Does it need to be available within an internal server? You need to think about all that. And then cost is a big part of that. So maybe you need a cloud web server, but then you also need a massive compute instance to actually host a model and run it. How much is that going to cost you over time? Those are all very important things to think about in deployment. And then once again, you need to do security and privacy checks ongoing after deployment. So you want to make sure that anything that is being deployed, whether it be publicly or internally, is still under the same protections that it had before deployment. And you need to make sure that no matter how you're deploying AI, you are properly wrapping it in security and privacy checks. Next, you have monitoring. So this kind of goes in with security. You want to be monitoring your security, but you also want to be monitoring the performance of the model and the pipeline. So you want to look for any choke points that exist within the pipeline. Maybe the model is slowing things down. Maybe your RAG system that you're pulling extra information is taking too long to actually retrieve that information. If that is happening, you need to identify it. Maybe the model is producing bad results on specific user inputs. You need to be able to identify that and put everything together to track how you can adjust. And then finally, iteration loops. So the things that you've learned from the security and privacy checks and the monitoring that you're continuously doing, you need to be able to apply those or identify what needs to be done to make any issues that you find no longer issues, and you need to identify what you can do to make the system just better overall. So all of this stuff is kind of standard for most software development projects and not just AI. So what makes AI unique? We need to consider where AI fits well into the workflow. How does introducing AI benefit specific individual features of the pipeline versus if I could do something that wouldn't be as costly as a lot of AI solutions currently are? And again, keep in mind, not every problem requires an AI solution. If something else works just as well to solve the problem, if you have just a very simple analysis of text, you don't need to always pass that to an LLM because the LLMs can be very costly over time. But maybe you have something that is too complex for very, very simple analysis, and an LLM would work great for it. Maybe you want to be able to classify a picture of a dog, and a CNN would be more it would be more easy to classify a picture of a cat versus a dog versus using a vision transformer. Finding those cost-benefit analysis and identifying what the best use cases would be is very important for this when you're doing things at scale. So components of AI workflow that make AI very unique versus other software development projects are that AI need data. So you need to be able to handle your project-specific data and wrap it all in together. And you need to be able to support model inference. You need to have a way to actually make it available throughout the pipeline. You need to evaluate the performance, like we said, and you need to know where the performance issues based on the specific kind of issues that come up with performance issues with AI occur and how you can address them. Each piece of this pipeline is dependent on the other piece. So while you may not really necessarily care about the monitoring, or you don't necessarily care about how the model is hosted, or maybe you only care about the data pre-processing, each part of that is going to be important to every other part of the pipeline. So you need to make sure that you are keeping it all in mind when you're doing your specific part, because how well you do on your part affects the rest of the pipeline. So starting off with data ingestion, you need to think about what data you're going to need, how users will supply the data if you're interacting with users, how are you going to collect data? Maybe you're not interacting with users at all, you're just collecting data from the internet or from a specific source. And then how can you structure the data so that you can be adaptive and reusable with it? Sometimes your goals change for the project midway through the project. Sometimes how you want to use data is going to change, and you don't want to have to recollect the data. You don't want to have the users interact with your system again. Having the data in a format where it is moldable and adaptable for many different goals is going to be very effective, so then you can use it for other purposes as well. So one thing you need to consider here is, do you need to make a public-facing interface for the model? So do you need to have web hosting set up so that you can make the model accessible to the broader internet? Do you need to build out an API, an application programming interface, for your system or your users to interact with the model and connect with the system? Do you need to build a network that is able to connect into the HPC resources that are used to host these models? And you also need to consider how much data you're ingesting at any given time. This is going to have network load considerations and storage considerations. Do you need to store every single user interaction? Do you need to store all of the documents that were pulled for a specific RAG request? Do you need to keep track of all that? These are all things that need to be considered at this step and how you manage that data. So again, some oversights and problems that people have are not considering that. So the downfall of not considering your network constraints, maybe too many people request your thing at one time, and then it causes the entire system to crash. Maybe too many people make too many requests, and all of a sudden you're out of storage and you have nowhere to put the new incoming data, and your system crashes. So lots of problems that can happen. You just need to be aware of what the scale of your data ingestion is going to be and how you can be adjustable for that.
I have a question.
Yeah.
So, do you want to first determine whether to make your RAG internal or external?
So a lot of the times it depends, again, on the application that you're doing. So usually when you have a RAG system, you don't really expose the RAG, the vector database polling or whatever your specific RAG is. You don't expose that directly to the user, but the kind of conversation that happens between the LLM receiving a request that it needs to make a RAG pull from a vector database and then actually retrieve those documents, that is all part of a conversation that happens internally to the system. So then how you handle the storage of that data, do you need to track like this, the user requested this, these were the specific documents it retrieved. So then you're able to like identify, did it do a good job of retrieving the documents? Did it do a poor job of retrieving the documents? Why did this query do good or bad? That's something that happens internally. And to the user, all they see is like, I said this, the model said this, right? So it's very dependent on your case, because you may also want to expose the vector database. And in that case, you have just a direct access to the vector database. Obviously that has security concerns. but it's, again, very, very dependent on your specific application. Does that answer the question?
It did. I was just curious because, of course, when you hear all of this information, you know, your mind just goes in various directions. So I was just thinking, you know, as far as a college or university, you know, FERPA is a big deal. And keeping all of that data secure and not exposed to the general internet.
Yeah. Yeah, so that's one of the biggest considerations for this, and it discussed earlier in the morning as well, where like this technology is so new and there is so many new possibilities with how we can use this type of technology. And really what we need to do is just wrap it in the existing security layers that we have. So something like the vector database searching, you don't want to make that available to the users directly most of the time. But what if there's secure data in that vector database that it's able to search, and then that's included in the query, and then maybe the model just spits something out, right? And it spits out something from the vector database that wasn't supposed to. Those are security concerns that, like, if you just have a standard setup for it, you maybe are not addressing. But that's the thing that you need to consider. Is there information in my vector database that I don't want leaking out to the public? How do I make sure that I'm not doing that? It's hard to say exactly because we're throwing a lot of information at everybody today. This is such a broad field, and how you apply it is so unique in every individual case. But we're just highlighting, these are all components that everyone needs to think about when you're applying this, right?
Yeah. So basically, as you're building your AI agent, you're setting up governance.
Yep.
Every step of the way.
Yes, exactly. Yes. Cool. So moving on to data preprocessing. There are a lot of data sets that exist right now that aren't AI ready. So this might be medical images that have no labels or annotations. This might be just large bodies of text that exist, and processing those into something that can be used for actually training a model or doing inference with the model is sometimes a difficult process. So you need to consider how you prepare that data for training. How do you make it perform best on inference? Do you need to use all of the data that's there, or can you cut it down? Maybe you have a query that would take 128,000 tokens, but you could cut it down into 7,000 tokens if you use something intelligent with RAG. Maybe by searching the whole section for it, you're able to identify the specific components with RAG that you actually need, pull out those documents, and then do analysis on that. These are all kind of important things that once you are able to get the pre-processing of the data done properly, it saves a lot of time, a lot of money on the inference or training, and makes things flow a lot smoother. So some common oversights and problems here that you have are not storing data efficiently. So again, if you have a huge block of text that you don't need all of, you can just pull out the relevant pieces. Then you can use something like vector embeddings to cut down on that, and you're not storing nearly as much text as you had. You need to make sure that the data is easily accessible. So you don't want to have a RAG system, for instance, that takes 20 seconds to respond. You want it to be as quick as possible, and so that as a piece of the pipeline, everything is moving smoother and faster. So you need to figure out, how does that fit best into my pipeline? And then again, going back to the garbage in, garbage out kind of principle, this applies to both training and inference. If you are not providing good data to your user or to your system, then you are not going to be able to expect good results. So just need to make sure that everything that you're putting in is in good form and doing the things that you want to do, make your data work for you. So for model inference, there are a lot of considerations here, and they start off with what type of model you're running and what type of resources does that need. For LLMs require a lot of GPU memory to host, and this is different based on the size of the model and the exact architecture of the model. The big two kind of factors here are the number of parameters and the precision or quantization of the model. So the number of parameters, those are the internal weights of the model. So how many weights are within that model. For instance, Llama 3 8B versus 70B versus 405B. That's 8 billion parameters, 70 billion parameters, and 405 billion parameters. DeepSeek V3 is one of the models that has what's called active parameters. So 37 billion of the DeepSeek parameters are active at any given time. And then 671 parameters are in the model total. So then the other parameters are activated based on the specific query. The model is able to intelligently determine which parameters are actually needed and activate those, load them into memory for inference for a given query. Gemini 3 is estimated to have about 20 billion activated parameters and 1 trillion total parameters. So obviously, extremely big model. Precision and quantization, this is a kind of in the weeds topic, but essentially what it means is how many bits are in each parameter. So you have floating point 32, floating point 16, and int 8, int 4. Those tell you the total number of bits within each parameter, and then bytes per parameter is just that number divided by 8. So then what that means is precision and quantization, what that means is the number of bits per parameter is just essentially the the precision means that how clear the model understands the information, how well it is able to find the relationships between the weights. The embeddings are kind of shrunk when you go to the lower weights. Or sorry, the embeddings aren't shrunk. The weights are shrunk when you go to the lower precisions, and then it makes the actual calculations that it's doing a little less accurate, but generally it's not that much that you're going to see a significant drop off. So quantizing a model down to a lower precision is pretty good a lot of time for assisting with lowering the memory requirements. So the required VRAM, or gigabytes of memory within the system, the rough equation is the number of parameters times the bytes per parameter divided by a billion, or more simply, the number of billion parameters times the bytes per parameter. There's also a little bit of overhead on top of this. So when you are hosting these models on inference servers, if you want to add tool calling, which is, like we said earlier, the basis for agents, that's going to add some overhead. If you have some KB cache parameters, that is going to add overhead. There's a lot of different things that are a little bit too technical for this right now that just add more. So roughly the required gigabytes of memory that you need are billion parameters times the bytes per parameter plus a little bit. So for hosting ALMs, for instance, an 8 billion parameter model at floating point 16 requires about 20 gigabytes of VRAM. A 400 billion parameter model at FP16 requires 850 roughly gigabytes of memory. A 1 trillion parameter model requires about 2 terabytes of memory. And to put that in perspective, these are some of the available GPUs that can host these models. So an NVIDIA A10 has 24 gigabytes of memory, so it could host an 8B at floating point 16, and those cost about $2,000. If you rent them from the cloud, they're about 50 cents to $2 an hour. A100s have 40 or 80, depending on the specific model that you buy, and they cost between $10,000 and $17,000. H100s, H200s, price goes up as the memory goes up, and the cloud rental cost also goes up. So you might think that the cloud rental cost on this is significantly better than purchasing it yourself, because $2 an hour sounds a lot better than $2,000, obviously. But really, the math is not super great. When you have one GPU at $2 an hour, that works out to about $1,500 a month. For A100s, H100s, and H200s, a lot of times if you're going through cloud providers, they will only rent them at 8 GPU clusters per source. So if you have 8 A100s at $1 to $4 an hour, that can work up to $24,000 a month. 8 GPUs of H100s and H200s a lot of times will be around $60,000 per month. So cloud resources, extremely expensive for this type of computation, but buying the equipment for yourself and hosting it and running it on your own infrastructure, also extremely expensive. So very important things that you need to take into consideration. If you're doing something small, maybe you only need a few hours of compute time on a cloud resource, and that'll save you a lot of time. If you're doing something more long-term, but you don't need more than 24 gigabytes of memory, maybe you spend $2,000 on an A10. Sorry, go ahead.
I was just going to say, does that consider total cost of ownership? Does that comparison? And when I say that, I'm talking about your, human overhead and maintenance and things like that.
Yeah, so the cost is listed up here. Yeah, the cost is listed up here is just the cost to purchase the equipment, but then obviously you have some overhead. So if you were to put an A10 just like sitting on a desk somewhere, the kind of energy cost for that would be high, not high enough to be comparative to what you would pay over time for using a cloud resource though. Yes.
Just to be clear, so you're talking really about inference here.
Generally talking about inference, but training is also like with these resources, the cost is going to be the same.
So a single query against one of these models.
Yeah.
I mean, I'm just sort of trying to get a ballpark.
Yeah.
How much is that costing? Was it like a single query is one of the models? Is there
very little?
Is there any way to be profitable with that?
Yeah. So it really depends on the application, obviously. So like Jim said, there's quite a bit of overhead with owning your own equipment, especially once you get into the H200s, H100s, A100s, stuff like that. That's going to require probably an HPC center somewhere where you are hosting the equipment. You have big storage racks, and it's not something that most people are going to be able to buy themselves. Yeah, so really one request is not that expensive. One request costs less than a cent, a fraction of a cent. But once you start scaling these things and you start requiring more memory for more users, it gets to the point where you can't host everything on a single A10. You couldn't host a small model that was for the entire world to be able to use, or the entire state of Kentucky, or the entirety of a city to be able to use on one A10. That's probably just not going to work because you're going to have too many requests. But if you have a small research lab where all you have is like 3 people and they're probably not going to be hitting the model at the same time, using an A10 is going to be perfect because you can use a small model that doesn't require that much memory, and you're not going to run into issues where too many people are hitting it and causing it to die, right? So for training as well, if you don't need that much memory to train your specific thing, then something like buying an A10 might be good. Maybe if you have a larger research group that has grant money or something for a larger cluster, you could buy 4 A100 GPUs on a machine. It really is super dependent on your resources. Cloud is exponentially more expensive over time, but there's a significantly higher start rate on how expensive equipment is to purchase and own yourself. And then there's the overhead of, do I need to put this into a large cluster? And something like that is only going to be really possible for large institutions. So like at a university level, you'd probably be able to set something like that up. But at a personal level, you probably wouldn't be able to set up an H200 cluster. Does that make sense?
Yeah. And for me, it's teaching. So
yeah.
Really small.
Yeah. So for very small models, you can host some of that on specific GPUs that come just in your personal laptop, right? So yeah, and that'll be perfect. But for training large models, you're gonna need a lot more than that, obviously. For hosting at scale, you're gonna need a lot more. And that's just the trade-off that kind of comes with the territory of this. So yeah. But also there are narrow resources that are specific to help with this. So there are large compute instances, and there are cloud services that allow for you to host specific models and make those available. And we'll kind of get into those later. But the other option that you have on top of that is what's called Models as a Service. So that's the OpenAI API, Claude API, and Gemini API. And there are other options as well, but these are the main 3 at the moment. And what these do are they're just services that exist out there in the public that you can purchase an account and purchase a set of tokens, or you pay for the amount of tokens that you use, right? So you're able to have a set number of requests that you make. The number of tokens that have gone into the request and come out of the model are tracked, and then you pay for however much you use. The cost on that is obviously based on the token usage, and it's a lot more scalable for small scale efforts where you don't have enough money to pay for a cloud service. You don't want to go through the hassle of setting up your own inference server. You don't have enough money to pay for large GPUs. So using these existing models that are available through API, it's kind of the easy button for a lot of these applications, just connecting to the existing services. You don't have to worry about maybe the model goes down because I didn't put enough resources into it. Maybe the power got shut off on my system. These systems exist as pretty stable ways to communicate with LLMs. They just come at a cost if you use them to an extreme amount. So yeah, so the thing that you need to do here is you need to think about how many tokens am I going to be using per month. That's obviously extremely variable based on how many users you have, what your exact pipeline is. So it's kind of hard to estimate all the time, but once you calculate that, you'll be able to calculate what is my monthly cost of running an application with this as the back end. So there are also near resources available for this. There offers you to apply for a specific amount of tokens from each of these providers, and then you're able to use those models through the API. For vision and more traditional machine learning models, those are generally for inference a lot more lightweight. If you're training, you're still going to have, oftentimes for vision especially, you're going to need a lot more GPU power, but for inference, vision is pretty light. For traditional machine learning even, you may only need a CPU. You may be able to do that on pretty much any computer that is out there right now, just with the way that the computation is able to be run. Obviously, it'll be accelerated and faster on the GPU, but a lot of times you don't even need GPU for some like simple classification models. So,
when does it become intense enough that you need a tensor?
It really depends is the answer. And I know that's kind of a cop-out answer, but that's the answer to pretty much every question in this, because it really depends on what data you have. Yeah. Mm-hmm. So the computation on the GPUs are like very specific for matrix calculations. They do matrix calculations very well, linear algebra, and a lot of times more simple classification models don't have nearly as much matrix algebra as something else would, and GPU or CPUs are powerful enough to do the matrix algebra involved at a rate fast enough to make it acceptable. It's when you apply it to the GPU, a lot of times it's going to accelerate significantly more. But if you might have a model that only has so many parameters in it and makes a decision, and it takes like a second versus a like microsecond on a GPU. So do you care that it takes a second? Maybe you do, maybe you don't. It really just depends. Yeah. So then you need to think about how many users can you expect, and do you need to run multiple models in parallel? This will be important for especially large scale LLM systems. This is important. So if you have an agent running that is going to be accessible to a large number of users, you might have a set amount of incoming data and the LLM is able to handle that. But if your user base grows and your incoming data grows, then your output may not be able to keep up with it. So at that point, your LLM might even crash and burn, and the whole system starts failing. No one's able to contact the LLM because it's running out of memory, which then would require you to go in and reset everything. But then if you are able to scale your LLM, if you say that you have cloud resources that you are connected to, and it scales that once it has so many requests, once the memory being used within the LLM is to a certain point, it'll spawn another instance of the LLM and run a second model in parallel for you. Then that would allow your resources to grow and be adaptable for that incoming level of data. So common oversights and problems here. Obviously, there's going to be a lot just because of how wide this field is, but underestimating the user load is, if you have a large application that has a lot of users, this is something that you really need to focus on, making sure that you're adaptable for that. Not properly testing the model. This is something that can really bite you if you haven't checked all the inputs. And this is extremely important for LLMs and being able to kind of wrap good protections and governance around LLMs, because you don't want the LLM saying something that is not reflective of what you would want it to say, right? So Aaron had the Air Canada example earlier where they were held liable that they were responsible for what their LLM agent had said to a customer. You don't want the LLM to be saying things to your customers or to your users or whoever it may be that don't accurately reflect what you want, because at that point you are going to be held liable in a lot of cases for that. You don't want to have a health AI bot that gives bad information to a user and tells them you should take this drug at this rate. That's not something you want an LM to be able to tell it if it has any chance of getting that wrong. So need to be able to properly test the models and make sure that they are doing what you want them to do and are being governed well. Using RAG and some of the other techniques, tool calling, accessing specific information, that's where this comes really in handy to kind of prevent hallucinations. Post-processing, this is how you interpret the output and how you present it to the user. You want to do this in a friendly way that makes it very easy for them to understand. And do you even need a user output? If you do, how do you make the output readable for them, and how do you report confidence? Maybe you don't care about confidence, but maybe you want the user to know that the classification that we're presenting, we're 80% sure on, or 90% sure, 50% sure. That's something that you want to present to the user sometimes. So think about that. And then limiting network load is also important. You want to make sure that there's as minimal traffic across the network so that you're not being flooded by too many requests. Common oversights or problems. If you report the raw output, that's a lot of times not the best practice. You want to make sure that you are only showing the users what they actually need. And logging and storing useful information from the output of the model is very important because it lets you do better evaluation. And if you don't do that, then you can't do evaluation on your model. So for evaluation, this is where you actually measure the correctness of the model output at deployment time. So after you've deployed the model and you check that it actually works well, you want to be able to be sure that it is still working well. You want to sometimes receive human feedback. So that's where on like ChatGPT, you might see the thumbs up, thumbs down on the response, or maybe it spits out 2 responses and it tells you to pick which one's better. That is what is happening there. They are reinforcing or cutting down on the amount of time that the users have, the amount of value that it puts in specific answers that it provides. You also make sure that you're handling incorrectness well, and that you're identifying and addressing any sources of incorrectness there. So again, common oversights problems. You are not continuously evaluating the model, and you might miss up on opportunities to evaluate the model, or to improve the model, sorry. And then monitoring of the system and the pipeline, that means that you're ensuring uptime. You're ensuring that the system doesn't crash and burn and it has no way of coming back up. You want to make sure that users are not being met with maybe the model's been overloaded with requests and it crashed. You want to have ways to address that. Identifying pipeline errors and choke points. The choke points within the system may be resulting in like delays in model output. It may be that your responses are taking 1 minute to for a user request to send an output, and maybe the RAG part of the system is taking 40 seconds of that. So how do you speed up the RAG part to make it not 40 seconds, and all of a sudden the request only takes 20 seconds to respond? So important things there. You want to ensure balance between each phase of the pipeline, track what's useful and important, and don't over monitor. So you want to be able to monitor to allow for good evaluations of the system, but you don't want that to be your downfall because it's stalling the pipeline in specific places because you're looking too deeply at things. So deployment strategies, your 3 big ones are local deployment, cloud deployment, and API services. For local deployment, you host your models on your own hardware. This requires you to own hardware. You need to be able to deploy and host those GPU equipment. That equipment needs enough virtual memory for your model. You need to set up inference server software. So some popular examples of that are VLLM and SGLang. Those will be able to run your model. So those have very common protocols for you to point it at the weights of the model. It will set it up and run it, and then it presents an API for you to be able to hit that and make requests, and it responds. And then managing those servers can often be quite cumbersome. You have to make sure that the power is turned on to the model. You have to make sure that you're paying for the electricity. You have to make sure that the software is running properly. Lots of overhead on it. And it can often be too much for some people, but some people may have the technical capabilities to run it. For cloud deployments, you can host your model on cloud hardware like AWS, Google, Microsoft Azure, and many more. These are available as NAIR resources. So if you go to this site for the NAIR resources page and select model inference services and cloud and commercial cloud, there are inference services that you can host models on and set up. The other option is the model as a service API services. So access through the tokens like we talked about. OpenAI, Anthropic, and Google all have some of those. There are others that exist, but these are the more popular ones. And these are also available as NAIR resources. So again, choose model inference services and then service/other, and that will provide the API systems that work for that. So then have a couple graphs here for kind of what we talked about with the cost trade-off benefit of using cloud, local, and model as a service. These aren't exact numbers, so don't take literal meaning, but this is a very rough estimate of kind of what it looks like. Local compute, you have a very, very high start cost of what you need, and then you have a somewhat low, depending on the exact requirements for your system, cost over time. Cloud starts scaling extremely quickly to the cost over time, several months, is going to be extremely expensive. And then model as a service systems, they are significantly less expensive, but especially when you start having large user load, that is going to significantly go up over time. A lot of people, even with the low costs of how much those are, if you have too much information to process, it just becomes too expensive for a lot of people. And that's just the unfortunate reality of AI in today's day and age. But the next thing you consider is storage. So all of these systems have data storage requirements. Whenever you're going to be doing anything with AI, obviously data is important. So keeping track of that. The cost of local compute is going to go up some because you need to have the storage that you need. For instance, for vision models, there might be terabytes of images that you need to store. So how do I purchase the terabytes? How do I get them securely and reasonably well in terms of access time connected to the compute cluster so that I'm able to access them? Cloud costs for storage are incredibly expensive, so be careful with that. It is often very inefficient to store things in the cloud, but maybe that's the route that your institution or company wants to go. Just be aware of what the cost for large object storage in cloud is. And for models as a service, there aren't really even storage considerations there, so you need to figure out your own option for that, so be aware of that. And we're going to move now into the panel, so yeah.
Well, thanks everyone for listening to our presentations today. Now's the time to ask any of these guys questions that have come up, or if you want to talk through specific ideas, this is a good opportunity. So they're around to answer questions. Or do you all want to stand up here? Sure, yeah, there are chairs. It's easy enough to hear.
Do we need this for a video? Yeah.
Any question?
Yeah, so I have a question. So thanks for all the presentations today. I think it was very informative. But there is one thing I think is missing in the presentations. And you touched a little bit upon some of the ethical and legal and social issues in terms of how AI can be used. But there are also other costs with AI, right? There's the cost of power, there's the cost of water, there's the environmental responsibility, and the sustainability of, as these grow larger and larger, those costs are only going to increase, right? And noise pollution, these sorts of things. So I was wondering, so maybe in the future, this might be something that you add to your presentations as you go around the state, but maybe if you guys could comment a little bit upon those.
I think that's a very valid point. I know that is a big consideration with AI and a big reason why people kind of discourage AI use in some ways. And definitely something we'll think about adding. Like I said, this was our first event, so feedback is really helpful as well as we continue to go around and do these things.
I know, in my opinion at least, it's what I tried to hit on last talk. It's very important to know when AI is helpful and when you should not apply AI because of those costs. Like, that's a big thing to take into consideration. Every time that you put a query in and use a cycle, that's using some amount of electricity and some amount of water for the cooling. And at that point, at what point when you put it at scale, is it just not worthwhile to do an application with AI? I think that there are a lot of times that people just want to throw AI into everything, and you need to kind of identify when that's actually useful and when it's just not worth doing. So it really depends.
I agree on that. I'm serve as a reviewer for NIH, and I see often people want to put AI in their research. I'm like, but just a simple regression model would be much easier. You want to put AI in because that's the hot word right now.
It's a big buzzword, and I think a lot of people use it very frivolously right now because we haven't really come to terms yet, I guess, with like what it's actually costing to run those kinds of things. But yeah, exactly like you said, like things like image generation, take up a ton more power and water and everything than, like you said, training a neural network or a random forest or like something simple is going to take up a lot less. So, the simplest solution that does what you need is always the best way to go.
So regression models were AI, what we're hearing.
Yeah, exactly.
I have a question.
Yeah.
So when we talked about preparing data for AI, we talked about how it's biased, and we talked about the story of like Amazon and hiring and how we later discovered it was a bias. So my question is probably like, if there was bias in hiring at Amazon, how did we only find out through the AI? And like, especially with the rules for AI being so like uninterpretable, like especially with large models, we don't know what rules they are using. So if we are building AI models, like how do we find if they have bias?
Yeah, that's a good question. I think with this, specific example, you can always, let's say you have like a language model that's trying to do it, and you can give, explanations as to like why it made a certain decision that it did. And I think what you can find too is that certain like trends might become exaggerated in the response. So for example, if you look back at all the past Amazon hiring practices, it's probably not likely that like a man was hired instead of a woman in every single case. But if it happens in a majority of cases, then the AI might learn, okay, this is the preferred way, and it will do it 100% of the time. So even if it like wasn't, as noticeable necessarily in the real data, the AI can kind of amplify that because it determines that this thing is favored, most of the time. So why not use it all the time? That could be a potential problem, or a way that it could be identified, as it can kind of amplify some of those problems. But that is also why explainability is so important with the models that we develop, and understanding why it does the things it does. Like, I think in this case they had trained it to like highlight certain parts of the resume that were like key indicators in why it made the decision it did, and that was probably how they identified that was the problem, because it was not highlighting the things that they wanted it to be highlighting, obviously. So building in systems like that is also very helpful for explaining why decisions are made.
And having a balanced training data set is also really important. So if, say that you want to have a classification model for two types of images, the cat and dog, for instance, and you only see cat 10% of the time in the data set, you want to kind of balance it out to where the training data set is 50% cat, 50% dog. Because if you show it dog 90% of the time, if it just guesses dog 90%, 100% of the time, that's right 90% of the time, right? So then it completely floods out the cat assumption. So then the example with the Amazon, assuming, let's say that it happened 20% of the time, they chose male or female candidates specifically because of that. Then if you have that balance, then it's going to just pick male, and then 8% of the time it's right, so it thinks that this is doing the good job. But if you balance it to where it had an even choice, and maybe only 20% of the candidates that were picked were female, so then you only show it 20% of the candidates that were male, have them balanced, then that bias kind of gets flustered out. I don't know if that applies properly to that example, but the point came across.
So I have a follow-up question. So if we are bringing neural model for predicting diseases, in that case, do we also need to have a balanced data of people without disease and people with the disease?
Yeah, generally you want that, and a lot of times you can run into issues with like lack of data on specific areas. I don't know if that's what you're kind of getting at, but like the answer is yes. Generally, you don't want to show it. Maybe 8% of people don't have the disease and 10% of people do, or 20% of people do. Then you want to balance that so that it would be 50-50. But maybe you only have like 5 cases where people have the disease. At that point, Eric, do you want to talk about some synthetic?
Yeah, there's a couple of ways that you can try to address it as well as you can. Kind of 2 big ones. The 2 simplest ones are basically oversampling and undersampling, where oversampling is you duplicate whatever the minority class is a bunch of times in your data set. So if you only had your 5 examples of somebody with this disease and you had, let's say, 100 healthy patients, then you just kind of repeat those same 5, maybe add in some noise to try to get up to that level. Obviously, if you have very little data to start with, that doesn't always work well because you're kind of extrapolating from a very small sample size. So then undersampling would be you reduce the number of healthy patients down to basically match the number of real patients that you do have that have the disease, which then of course is cutting out a large portion of good data that you have that might be useful. So 2 other things you can try also are, 1, synthetic data generation. There's models out there that can try to duplicate overall trends without actually duplicating just the raw data itself, which can help a little bit. But again, if you're doing that off of a very small sample to start with, then you get a lot of repeats. And the other thing is there are models that you can like apply weights to each class. So you can say that like, if your model's predicting disease or no disease, you can basically define ahead of time, hey, getting the disease classifications right is more important than getting the non-disease ones right. And it will kind of know how to balance that essentially when it runs. So it will either reduce false positives or false negatives, basically, depending on which one is more important to your use case.
So when you're talking about balancing the class, does it have to be like half and half, or does it have to be like reflective more of real life? So for example, in a clinic, if only 20% of people come with a certain disease, then should like 20% of our data be of people who have the disease, or should it be more like a bit?
So generally, it depends on the data set. For the training data, the one that you were like initially feeding the model, you kind of want that to be as close to balanced as possible so that the model basically treats both classes evenly. So that way, like Mitchell said, if 90% are healthy, if the model just predicts everyone's healthy, it's right 90% of the time. Balancing the training data helps with that. When you're testing your model, then you want to test it on real data, though. You always want to test your model in the real proportions of data. Because if you test it on 50-50 balanced data, it's not really reflective of the real world, and it might not really generalize in the way that you hope it will. And so then you end up, and this is a very common problem, and it's a problem that I've had with projects that I've worked on. If your class is very, rare, then when you're predicting on real data, it overestimates it a lot because the training data that it's seen is a lot closer to balance. So you end up with a lot of false positives. And so that's where, weighing the classes and things like that can help, but it's a tough problem without kind of a perfect solution, unfortunately.
Do you shuffle your data?
It depends on the use case, but in general, probably, yeah. Like, it depends on if there's some kind of on a temporal component maybe to your data, if you're measuring data over time versus if each sample is just a random patient, then yeah, you can go ahead and shuffle it, and that will help. But sometimes keeping the order is important.
There's a question in the back of the room.
Yes, I have a question regarding environmental aspects and the energy use. Of course, we know that now we need a lot of energy, but do you think that the algorithms or the approaches will be much more efficient in the future? I mean, not that far. Like with DeepSeek, there was a lot of buzz that it was much more efficient. So eventually, we won't need that much energy, and also quantum computing can make it much more efficient. So maybe we think about energy use. I mean, maybe our worries are really not warranted at this moment, because maybe in 10 years it will be much more efficient.
Yeah, it's definitely possible. With LLMs especially, there's kind of an amount of just required memory. So like the idea that you have a model that performs just as well on as like a 400 billion parameter model with 5 billion parameters to where it needs less memory.
Quantum computers are much, developed. They are already, they have like 1,000 qubits right now, which is still very small, but the development in this area is really also moving up. So, we are thinking about normal computing at the moment, but soon we may have other technologies available.
Yeah. I don't think any of us are particular experts on that component of it, but I think there's always going to be a high cost on the energy. I do expect it to go down over time, just because that's the trend of technology like this, is that it will get more efficient over time. But how much more efficient? I don't know. The kind of trend in building the amount of data centers that we have right now, the increasing price of RAM and stuff because of the companies that created selling entirely to the AI companies, that's causing an immediate problem right now that I don't know what the solution is going to be. I'm sure it obviously will work out in some way, but what that ends up being, whether it be we get quantum computing and it completely solves everything, and we make some new technology that makes it like super easy to do all this computation, and then it requires no energy or very little energy. Maybe that happens, I don't know, but I think that there's probably always going to be some amount of overhead, and thinking about what we do right now to make it to a point where it's sustainable is, I think, very important. So it's something that needs to be considered with thinking about all of this.
Also, the trend right now is people want to follow scaling laws, which say the more compute you put into training, the larger the data sets, the larger the models, the better it will be. So people seem to be not trying to make smaller, efficient models, but making models as large as possible because they think they'll get better. So as long as that trend continues, I don't think that power consumption is going to drop significantly in the near future.
The information amount is limited. Yes, we generated a certain amount of data globally. So there is an upper limit at the moment.
Yeah. But we're also generating a lot more data. Like every time a computer scientist goes into their IDE and uses AI, they are generating more training content.
But soon there will be a replication of the same data. You won't generate a completely new data.
Sure. I was curious about what your thoughts of the panel are on the term GeoAI, some of the types of mechanisms that different research has taken to try to integrate spatial awareness, spatial cognizance into the types of applications that AI are being used for. To speak a little bit to that.
I'm not aware of that term. Maybe you guys.
I've heard it. The closest thing I have as far as like geospatial kind of considerations is for a project that we work on that I think we mentioned before called Radar, which is essentially looking at opioid overdoses in counties around Kentucky and trying to like predict that. And so obviously there could be a big geospatial component of that, where looking at trends in one county might affect the trends of another county, looking at nearby counties and things like that. I would say what I have personally done on it has been very limited, in the sense of like, oh yeah, you can build out, like a distance matrix or something to map counties to each other, figure out like lagged trends between different areas to try to find like sequences of potential like overdose spikes and stuff like that. We've built out like hotspot analysis, for example, to like map overdoses to like specific regions and say these regions are seeing increases, these ones are seeing decreases, like identifying things like that. But that's kind of the limit of my practical experience with any kind of like geo AI.
So I know that NVIDIA is doing some things with large models that are aware of physics and space and spaces, and it's all connected with robotics. So it's a little different area, I guess, maybe. Than
Yeah.
talking about.
Which is crazy to think about.
The question at the University of Louisville, Office of the Provost, and one of the highest priorities is student success, reducing, increasing graduation rates and retention. And so I'm just really curious about the positive aspects. I mean, a lot of people across the university are grappling with how to use AI in the classrooms, promote it, what are the ethical uses, of it. One of the things I'm thinking about, and curious about your thoughts, is how across Kentucky with education deserts, health desert, like every desert you could quite imagine. How do you see AI as a positive force in addressing inequalities and helping those from underserved, underrepresented communities have access or solve problems in the communities, where they're centered, and just really improving access to education?
Yeah, I mean, I think that it's obviously impossible to keep students from using AI. So it comes to like, well, is it fair for some people to obviously have access to AI while others that don't necessarily like at home? And so, I think I've seen like schools providing access to, with like tokens or accounts or something like that, that at least make sure it's equitable. Like if some students are going to use it, then everyone should be able to at least. So I think that's definitely important in schools to make sure that it is fair. And, in terms of using it for good, like I mentioned, chatbots can be very helpful tutors, can help people, study and understand things. So I think, you don't want people to be able to just use AI to answer everything, but using it as a tool to help understand is good. And while you can't necessarily force that, there's things like, requiring handwritten, assignments again, right? Because even if somebody is using AI to answer their entire homework for them at home, even just the process of copying down answers into a written format will help at least a little bit. I know when like we talked about vibe coding, like if I'm generating code with, AI and trying to use it, I always try to look at the code and still write it line by line instead of just copying and pasting huge blocks of it, because that way at least I know what it's doing when I'm typing it instead of just copying it and never looking at the function again. So things like that, I think, can allow AI to like still be helpful even when somebody might just be using it to do their homework for them, which is something that's pretty hard to stop, unfortunately.
So I'll ask a kind of similar question, because as a faculty member, we're now required to put in to our syllabus what is an appropriate use of AI. We don't get any guidance on what that should be. And in my own, and a lot of times that really focuses on either generative AI, where they're generating results, or the language learning models, where they're interpreting, say, a manuscript or something, right? And so for me, it's a matter of using those tools to get them, to gain knowledge, but not at the cost of critical thinking. So I was just wondering if you guys had any advice on, when we're putting together these appropriate use of AI in the classroom, maybe what we should include or shouldn't include, or maybe what tools we should allow or not allow as part of that.
I think that's an interesting question, and I can say all of us are students getting our graduate degrees. Aaron recently got his in data science, and have definitely, compared to like my undergraduate experience, syllabi did not include mention of AI at all. And now every semester just started, teachers always have a thing that they are saying at the beginning of class, at least in my experience, about their policies on AI. And again, in my experience as a student, it varies. Some teachers have stricter rules and set up their class in more discussion-based ways, and others, recognize it's a tool and they, just want people to cite it if they use it. So I've seen it kind of on a spectrum, and maybe you all as students in your programs, you've probably seen professors say different things about it.
I think, in my opinion, accountability is the most important part. So these are tools that exist and are probably always going to exist in the future. And it's important that people know how to use them effectively, but it's also important that they know that they're accountable for what they submit. So from a computer science background, in classes, whenever I have ChatGPT or something generate code, I am accountable for what I'm submitting. I can't just say, hey, ChatGPT, here's the answer, or here's the entire homework, give me a script and I'll just immediately plug it in. I have to go through and test that it works. I have to make sure that I am okay with what I'm submitting there. And if I do a write-up on it, I have to make sure that the write-up is accurate and follows everything. A lot of that can be automated with AI, and with AI now, like when in day-to-day work, we often do things like that where we have it generate portions of scripts and make a report or assist with writing papers and stuff like that. That's something that's always going to be true in the future. And I think just like highlighting to students that they're accountable for the things that they submit is important, but also assisting them with being able to actually use the tools effectively, and it helps them learn as well for so many topics in computer science. If it wasn't for AI, it would take me like 3 times longer, if not more, to figure out anything about it, because I just have no basis for starting, and I can Google and look at on Stack Overflow or something, but that only gets me so far, whereas AI can give me a full report. And yeah.
Is there value in that taking 3 times as long to get to that result that you got?
I think it depends.
The time, is that part of the
Yeah, I think it depends, because sometimes you can just be running around and not finding the things that you need, whereas AI could point you directly at the thing that you need. I might ask it a specific thing and it says, these are the steps that you should do, and I can read that and be like, oh, okay, I understand why. But I do know from working with students who I feel really bad for, because they were a couple years younger than us, and I feel so old talking to them because I grew up learning how to code without AI, and they always had AI at their fingertips for it. And so many of them just don't know anything about how code actually works. And I have to teach them these things, and they're like, oh, well, it's not important. The coding models will get so good. And then I won't have to do anything. It'll just be me telling it what to do, and I can orchestrate the AI to do whatever I want just with language. And I think that that's you're losing the valuable skill of just debugging, because if you just copy paste a traceback into AI and say, fix this for me, you don't have to hunt down where that bug is and fix it. You lose that skill of finding out the things and researching for yourself and figuring out how to solve problems for yourself. You don't get experience with that. And it's a really hard thing to do, because I feel really good about my abilities to do that. So it feels like AI just takes that kind of cumbersome effort of actually doing that and going through and figuring it out. It just makes it significantly easier. But then the people that don't have experience with that, they never learn how to do it. And then if they need to, then they're going to have a hard time. So it's a really hard thing to balance. I think just ensuring that people know that they're accountable for what they produce is the best thing for my skill level, in my opinion, with stuff like this, where if a teacher told me that I couldn't use AI on something, I wouldn't feel like I was being forced to learn about it more. I would feel like I was just being hindered in how quickly and how effectively I could get something done. Whereas for some students that don't know more about things and have never had the experience of having to debug and critically think about what's going wrong, or in other fields haven't had the, maybe for literary analysis, they've never had to fully read through a book and do literary analysis on it, because they can just put in ChatGPT and copy paste an answer. I think that there's going to be different levels of how you need to enforce AI policies, and it's so broad and hard to define at this time, and I don't know the answer.
Much like the things we've said a couple times today, it depends. And I think, we can share our thoughts as students. Obviously, we can't give official recommendations or anything. We're not faculty or have that experience, but hopefully this was helpful to hear about. We will be sticking around. If you want to come up and chat, I wanted to remind everyone about the resources that are available if you want to check them out. Our webpage is the place to access those, and of course explore the Pilot resources as well. And thank you to all of you for being here today, and stay safe. I hear there's a snowstorm. Thank you.